Welcome to the class on high-performance computing in C++. Let's start by a brief outline of what this class is about and why should you take it. High-performance computing in C++ is a huge subject. You could spend 10 years and still not learn everything there is to learn about it. We only have about 10 hours. We're going to focus on taking the most from your hardware in terms of performance, and within that, focus on concurrency. There are other subjects that we might cover, but we'll focus on concurrency and specifically on multithreading, local concurrency. We're not going to talk about distributed execution in this class. And I haven't said a word about C++ yet. That's because while all the example code and all the code we'll run is written in C++, it's not really that C++ specific. If you can read C++ code, even if you don't write your own programs in C++, you can learn from this class and take advantage of your knowledge in your work. So who should take this class? The truth is, modern CPUs are incredibly fast. Modern computers are amazing devices. For a lot of tasks, they have plenty of computing power. But some people just can never get enough power. Usually, if you write scientific, engineering, finance, modeling, simulation, any other compute-intensive applications, you can use all of the computers in the world and still not have enough. Some people need their own data center just to store the number of zeros on your power bill. If you are in this world, you probably already tried to improve your performance. You probably wrote a concurrent program, maybe a multi-threaded program, and maybe it was even successful. That's okay, you can still learn something new from this class. Throughout the class, I will be throwing up summary slides on sort of takeaway points. If you remember nothing else from the class, these are the things I want you to remember. Why do you want to take this class? Modern processors are very complex systems, and that's not all that goes into your computer. There is memory and other stuff that could be even more complex, and you don't get computing speed for free just because you have all these complex things. You have to learn how to use them well to get good performance. To learn how to use them well, you have to understand them, and that understanding is never done. The processors get better, computers get better, new architectures emerge. You have to learn how to learn, and that's what I'm going to try to teach you. Now, how did we get into this mess that we have to learn how to use hardware? Well, this isn't the first time. If you were in the business long enough, you know that in order to write efficient code, you had to know your hardware. There was a time like that. The processors were very slow, and average performance was not good enough. Memory was very small, and you had to manage it carefully. Compilers were not very good, and you had to do the critical bits of your code yourself if you wanted them done well. Things got a lot easier as the hardware capabilities improved. Most programs written today are fast enough without significant optimization. You don't need that much compute power to read your email or browse web. There is tons of memory for most applications, and the compilers are actually quite good. So good, in fact, that you probably would not be able to write the entire program in assembler and outperform the compiler. As a result of all of these advances, the programmers could now focus on writing better programs instead of writing the programs that could barely meet their performance needs. So you can now focus not on how to do things, but on what do you need to do. And that's a good thing. And why was this all happening? Well, it was all made possible by improved CPU scaling. Over decades, CPUs and other ICs got larger, and they also got faster. The clock frequency got faster, performance got faster, everything got faster. And then it stopped getting faster. I won't go into reasons for why this is happening, but there are multiple reasons: technological, manufacturing, and so on. But the bottom line is the processors are still getting larger. That is not slowing down, but they are not getting any faster. Sometimes they're getting slower. So if the processors are getting larger but not faster, what happens with all the silicon? Well, the first thing that happens, all of these large CPUs have more than one core. This is nice, except you actually have to write your program to take advantage of them. Some cores, even though they're single cores, can run within one core multiple hardware threads. The threads are not going to happen by themselves, you have to create them. Caches have got much larger and for the most part make up for slow memory, but you have to use them right. Sure, some silicon still goes to better, faster instruction processing, and that still happens mostly by itself, but not entirely. In addition to faster instructions, we now have more complex instructions that can do a lot of complex computations very fast, and compilers know some of them, and others you have to write yourself. So we're kind of back in this world where you have to know your hardware to write very efficient programs. What do you have in that hardware? Well, lots of stuff. This is a Nehalem CPU die. You can actually see how little area is occupied by the compute units, that's execution units in top corner. That's all your math. The CPU is supposed to be doing computations. Well, that small portion of the CPU can do all the computations you need. Everything else is for something else. And some of these systems, they just work when you run the CPU. Others, compiler will make them work right. Some of them you have to be taken care of explicitly, at least if you want large performance. And there are a few more that it's just good for you to know to be able to write good programs, even though they mostly work by themselves. So the bottom line is the free lunch of programming, when you could just write your program and wait a year for a better CPU and it would get faster, that's over. So now, to write efficient code, you have to know your hardware. As a result, high-performance computing, and we're focusing on concurrency, so concurrency at the extreme level is hard and mostly has to be done at the low level. Some languages, some libraries provide high-level abstractions, some of them even work, but still you can do better if you do critical things yourself. Memory is huge, very large, but accessing memory is expensive. So again, you have to take care of managing your memory accesses. Compilers don't really give you full access to everything your processor is capable of, which means you may have to go beyond the language that you're using. And as a result of all that, very similar programs using very similar, even the same algorithms, very similar data structures, with subtle differences in how they're coded, can perform very differently. And the goal of this class is to help you understand why they perform so differently and how to get your program to be the faster one. This understanding, this is the focus of the class. This is very important. I'll give you a lot of knowledge. You'll learn more about the hardware than you probably wanted to know, and that's all very useful. Right now, you can take this knowledge and apply it immediately to your work. But even more important is learning how to gain that knowledge when the world changes. Remember that time when going was good and performance was free, and we could focus on writing good programs? Well, we still have to write good programs. That's not going away. And that's because all programs have to be read by someone, possibly you. Programs are primarily tools of communication. And it's not communication between you and compiler, it's communication between people writing and reading those programs. They still have to be well written. So you have to understand hardware, you have to write programs that take advantage of hardware, and you can't go back to unreadable low-level programs of 50 years ago. So we're going to do a lot of low-level programming, and in this class we're going to do it primarily so we can actually figure out what the hardware does, how it does it, and what impact it has on performance. Just because a program is low level doesn't mean it has to be written badly. Any program can be written well or not, and that's true for low level programs as well. So you're going to learn about using all your computing resources, such as CPU, memory, caches, more efficiently. Some of the big sections of this class will teach you how to work with CPUs interacting with memory. It's a very complex system. There are very fast cores that have a series of caches that progressively getting slower. There is a lot of magic CPU has to do in order to maintain all those caches. And underneath it all sits memory that could be hundreds of times slower than the CPUs. And in order for you to have good performance, you have to somehow avoid being affected by this slowness of the memory. So we'll spend quite a bit of time studying that. Now, that was all for one CPU, and that looked scary enough. Now we have multiple CPUs, and they have their own memory, and they can interact with the memory of each other, and that interaction sometimes costs you a lot of time. So we have to learn all of that. Finally, still on the subject of CPU and memory, if you have multiple CPUs, you could be doing operations on memory at the same time. One processor writes, another processor also writes, could be writing in the same location, they could be reading, and what happens before, what happens after, what does each CPU see? All of this falls under the category of memory model. We'll have a whole chapter on that, because that's important to understand for you to learn how to write correct concurrent programs and not pay too much performance for that correctness. After we get all these bases covered, we're going to study concurrent data structures and log-free and log-based programming and how to avoid data races, undefined results, sudden explosions, and other interesting things. Throughout it all, we'll pay great focus to getting good data about performance. We're going to learn how performance is measured and how to use the results of these measurements to guide your optimization and your development work for better performing programs. We'll see a lot of performance data, and we'll learn how to collect and how to use it. So this is the plan. We will learn how to get the most of your computing resources. Yes, there will be log-free programming in this class, and we'll learn about how to keep your work grounded and data-driven so you only do things that really help your performance. If that sounds interesting, then this is the class for you. In this class, we will explore the issues of memory and their impact on performance. We start with an overview of memory architecture and how the performance of the program is impacted by the interaction with memory. When it comes to memory and using it in the program, there are two major aspects. The first one is how do you get memory, which is commonly called memory allocation. This is handled by the operating system. An application can take over significant portions of memory allocation. Hardware comes into play, but mostly it's the operating system and the library. The second big class of issues is how to use the memory. Once you got it by some form of allocation, how do you use it for reading and writing data? This is primarily determined by the hardware. The overall efficiency of your program will depend on how good your software is at making the best use of the hardware. The OS has some role to play, but mostly it's between the hardware and you. In this class, we will be focusing on the second issue. Let's assume that the allocation is not that frequent. Somehow, one way or another, you got the memory you need. Now you're using it a lot to store data, and that's where your performance is. So let's proceed to explore the memory system. Conceptually, memory is very simple. You have the processor, you have memory, the processor reads and writes data into memory. That's all there is. That's all there is in theory, logically, at a very high view. In practice, the memory system is a lot more complex. First of all, the processor actually does not access the main memory directly. There are several levels of caches, which are different kinds of memory between the processor and the memory. The processor writes into the closest cache, which is commonly known L1 cache. There is then the second level of caching, and on most systems these days there is the third level of caching, and finally the data trickles down to the main memory. If the processor needs to get some data from the memory, it has to be first brought into L3 cache, then L2 cache, then L1 cache, and finally it gets loaded. Now, all of this so far has totally ignored the issue of multi-core or multiprocessor systems. If we have several processors on a shared memory system, the main memory is shared between all of them. Some of the caches will be unique to the CPU that owns them, and some will be shared between some or all CPUs. This detail of what is shared between whom varies a lot from one platform to another, depends on how many CPUs you have, the class of your hardware, and so on. But the general picture remains L1 cache will be per core, main memory will be shared between all CPUs, and caches in between will be shared between some smaller group of CPUs. Why does it have to be this way? Why is it so complex? The reason is that the memory that is used to build the caches is different between different caches. Specifically, L1 cache is made from the fastest memory. The CPU, of course, operates the fastest. The registers in the CPU run at the same speed as the processor. L1 cache is usually just as fast or maybe a little bit slower. L2 cache is slower, but there is more of it. L3 cache is quite slower compared to the previous ones. There is even more of it. And the main memory, you have gigabytes, maybe even terabytes of the main memory. By comparison with the CPU, it's extremely slow. Your CPU may run at 4 gigahertz, main memory could be less than 1 gigahertz. So that's the reason for this complex system. Once you have all these caches and all the multiple CPUs, in addition to just the transistors needed to form the memory cells and all the caches and all the transport between them, there is a whole lot of hardware that deals with cache coherency. It's still a shared memory system. It wouldn't do you any good if different CPUs were totally unaware of each other and proceeded under illusion that the other CPUs don't exist at all. So somehow they have to have more or less the same view of the memory. A lot of cycles, a lot of silicon, a lot of power goes into making that happen on the most common CPU architectures. All of that isn't free. It takes time to move those bits up and down the memory hierarchy. It takes time to populate the caches. It takes time for the results to trickle down from caches into the main memory. So it makes sense intuitively that your performance of the program would depend on how quickly you can get data into the memory and out of the memory where you need it. This is all intuitive, and the first rule of software performance is never guess about performance. We're going to have to measure the efficiency of the memory system. So let's proceed to explore this. The main idea here is to measure how long it takes to read and write different amounts of data into memory and out of memory. There is an underlying assumption here. If the data fits into the cache, then the hardware will keep it in the cache. It's a sensible assumption. If it wasn't so, why would there be a cache in the first place? We will be able to detect whether that assumption works or not. There are a lot of questions we can explore here. For example, I said that larger caches are larger. Well, how much larger? How big are caches in the first place? You can read the specs about your hardware system, but you can also measure it. How much faster is faster? How much faster is L1 cache compared to L2? Not difficult to measure, we're going to do that. Does it matter if we access memory in different order, from small addresses to high addresses, sequentially, randomly, with some step? Does it make any difference for performance? What's faster, reading data from memory or writing it back into memory? Does it matter if we write 1 byte at a time, or 8 bytes, or maybe 64 bytes? We're going to start measuring all these things. A note on measuring. We'll have to measure very small time intervals, basically individual accesses to memory. This is not an easy task. In general, this is known as microbenchmarking, measuring very small pieces of code. Could be one store instruction. Such short time measurements are noisy, they have to be repeated many times, and in particular with memory, the hardware tries to make itself more efficient for a particular use, so it will get primed for whatever you're doing, and it will get faster once it adopts to your current memory pattern. So all of this complicates collecting the results. A good microbenchmark library will take some of this into account and free you from making at least some of the mistakes common to benchmarking. We will be using a Google benchmark library. You can download it from this location. The first time we'll use it, I will go through some of the elements of the library and how to use them. After that, it should be familiar to you. Let's begin with the simple benchmark of reading and writing memory. Here is our benchmark code. It includes the Google benchmark header. And to use Google Benchmark, you have to write these benchmark fixtures. We're going to test memory speed using different size words. So we will write a fixture as a template, and the word could be an int or a long or maybe a byte. And this is a fixture to test writing into memory. We're going to allocate some memory. I use POSIX memoline on a large enough value, so I don't have to worry about alignment issues. You may want to test how alignment affects performance of your particular hardware. For the purpose of this class, I'm just going to enforce very strong alignment and not worry about it. We're going to write into memory a value. The same value probably doesn't matter which value we use. We can test whether this assumption is true or not. The way the benchmark works is the body of the benchmark sits inside this loop with the function keep running that is provided by the library. It will keep running the microbenchmark until it collects enough data to produce a result with sufficient accuracy. The compiler is very good about detecting redundant writes. In particular, it will probably figure out that we are writing the same word into different locations in memory over and over. Once it detects that, it will optimize most of it away, which is usually a good thing. In the microbenchmark, you actually want to measure how long it takes to do this many writes, however many writes the benchmark library will want to do. Google Benchmark Library provides this do not optimize function that wraps around the code you want to benchmark. It prevents compiler optimizations. Similarly, we have a reading fixture that does the same thing, only it reads the value from memory, runs this pointer p over all of the memory we allocated, and reads the value, stores it in a sink. We're going to ignore the sink. In order to actually run the benchmark, you have to instantiate the fixture one or more times. And you do this using this benchmark template macro if your fixture was a template. Ours was. So here you see we can run the benchmark fixture for long, int, short, and so on. We're also using the SAC or AVX long types. These are 128-bit and 256-bit integers. In order to use them, we have to include these headers for SAC. And if this machine had AVX, I would have also included the AVX header for 512-bit words. This particular machine doesn't have AVX. Finally, it needs main, so benchmark main provides us the main that automatically runs all these benchmarks. That's basically all we need to do to benchmark, and what we're going to measure is actually this code inside the loop. Well, we're going to measure the whole code inside the loop. What we're after is this piece within the do not optimize clause. I have already prepared a makefile, but it's a standard compilation with a C++ compiler. Let us pause for a second. Compiler, we're compiling optimized. We want to measure the fragment of code itself within the do not optimize. We want that to be optimized if it's possible. For such a short fragment as we have, there won't be any optimization. We just don't want any optimization between the repetitions of this fragment. In particular, we don't want the compiler to eliminate redundant repetitions. And here we see how it runs. It runs multiple sizes. How does it know which sizes to run? I'll show you in a moment. And it tells us for each size how long it took to run and how many iterations it had to do. Let's see where it got the sizes from. In order to instantiate the benchmark fixture, you could just give individual values, or you could give a range of arguments. Inside the fixture, this call to range x retrieves the current value. So using range multiplier and range, I specified that I want to run on a range of values from 1024, doubling up every time until I reach 2 megabytes. What happens to that value? Well, that would be the size of the memory that I'm allocating. So what do we have here? 1024 bytes, 1 kilobyte, writing and reading, 2 kilobytes, 4, and so on up to 2 megabytes. Now this is strange. The reading and the writing took basically the same time. Well, if you know something about memory speed, if you've read anything about it before, this should startle you. This isn't right. This isn't how it's supposed to be, not what everybody else tells you. Now would be a good time to take a break, and you can think about a solution to this puzzle. When we come back for the next section, see if you got it right. Welcome back for the second section of our overview of memory performance. Let's jump in right away We had ourselves a little puzzle last time. Let's see what it leads us to. What could be the problem? Well, maybe on this machine reading and writing is the same speed, but what else could it be? This is our benchmark fixture, and this, within the keep running loop, is what we're measuring. In addition to measuring the write, we're actually running the entire loop inside. So could it be that the time we measure is actually not so much the time of the write, but the time it takes to iterate over the loop? Well, there is only one way to find out. We have to manually unroll the loop. Let's get to the writing fixture here. So here is our loop, same thing, but inside the loop we now have this repeat macro, which repeats the content, in my case, 32 times. And every time I write, I also advance the pointer manually inside the macro instead of in the loop. There is no advancement here anymore. There is underlying assumption that the memory size is divisible by 32 advancement in this case, and it would limit the sizes I can use, but I'm running large powers of 2 for size, so it's not a problem. If you were doing other sizes, you would have to be more careful here. So what I have done is manually unrolled this loop 32 times. And I've done the same for reading fixtures and so on. Let's run that test. It's faster. It was about 60 nanoseconds. For 1K, now it's 38. Let's see if reading got faster too. Now reading is a lot faster. Okay, so now we're close. We're getting something sensible. Now, is 32 times unrolling enough? Or maybe we need more, or maybe 16 was good enough? What you would do is change the unrolling, try 16, try 64, and see if these numbers change. In my case, 32 provides enough unrolling. The loop overhead is now insignificant. So here are the numbers in nanoseconds, how long it took to write 1 kilobyte, 2 kilobytes, and so on, and to read the same. Of course, this is for this much memory, so for 2 megabytes. 2 megabytes, 74,000 nanoseconds. If you want to know per byte or per word, you have to divide by size. This kind of shows that it's faster to read than to write, and it, of course, takes longer to operate on larger sizes, but it would help us to have a picture or a graph of these numbers to actually make sense of the data. So what have we learned? First of all, having a microbenchmark library does not free you from the unfortunate necessity to still use your head. Use common sense, use prior knowledge. If the results don't make sense, they probably don't make sense. Try to figure out what's wrong. In particular, having been burned once, consider benchmarking overhead. Look exactly what it is that you're measuring. We have also seen that there is significant difference in memory access speed. Reading, writing, very different. The numbers are different. There's a big difference in those numbers. We'll see a graph in a moment, but we've seen the numbers. And here is our first plot. In this case, I was using 128-bit words, so this is an SIC2 type. Reading and writing of the specified size in kilobytes, 1 all the way to 32 megabytes, and I converted the values into bandwidths, megabytes per second. You can see that reading is significantly faster than writing. You can also see that bandwidth for both reading and writing drops down quite a lot when we start operating on large ranges. It's a lot faster per megabyte. Of course, it's a lot faster to write 1 kilobyte than to 32 megabytes, but this is per megabyte, so already normalized on size. A lot faster to write the same kilobyte over and over than to write 32 megabytes and then go ahead and write the same 32 megabytes again and again. From this plot, we can actually figure out the hierarchy of caches. There are 3 steps here corresponding to the 3 caches. The first step occurs at 32K. L1 cache on this machine is 32 kilobytes. As long as we write up to 32 kilobytes of data, it all fits in L1 cache. It doesn't ever have to leave it. So we're just writing into L1 cache over and over. L2 cache on this machine is 256 kilobytes. So if we write more than 32K but less than 256K, it will fit into L2 cache. It will miss L1 cache. Such an event, by the way, is called a cache miss, and it will fit into L2 cache. Larger memory ranges still would miss L2, but fit into L3, all the way up to 4 megabytes on this machine, and beyond that, we're hitting the main memory. There is something interesting going on here. After we miss the cache, we don't have a sharp drop. We have these slopes. It kind of gets slower, slower. Eventually, it plateaus out at a new speed. So what's going on here? And the same is for writing. This is what's called prefetch. Prefetch is a function of the hardware. And what it does is it figures out that you're about to access the memory that is outside the cache. How did it figure it out? Well, we were accessing the memory sequentially. We started from byte 0 and went all the way to 1 megabyte or 8 megabytes or whatever we were using. Not hard to predict that after byte 10,000, there will be a byte 10,001. The hardware notices this repeated memory access pattern and starts prefetching the data that you haven't accessed yet, pulling them into a closer cache. So let's say we're writing 1 megabyte of data. While we're still on the first half of it, the hardware is already pulling the data that is close to the point we're writing, but further ahead. We haven't touched that data yet. The hardware is already pulling that data from L3 cache into L2 cache. So by the time we get to that data, it will be mostly in L2 cache and accessing it will be faster. Now, it doesn't make L2 cache larger, so you still have some penalty because the data actually cannot fit into L2 cache. In order for the prefetch to pull something in, it has to also pull something out. That takes time. But the time penalty you get for exceeding L2 cache isn't immediately as bad as going all the way down to L3 cache or from L3 to main memory. Only if you are accessing a lot more data than fits into the cache, basically prefetch cannot keep up. And then you're using just the main memory at its speed. If you're accessing a little more data than L3 cache, prefetch keeps up pretty well, so you're paying a bit of a penalty, but not too much. What have we learned so far? We have learned that the closer caches to the CPU, the faster they are. We have seen that they're quite a lot faster. They're also, unfortunately, quite a lot smaller. It doesn't take much to jump to conclusion here that a program will run a lot faster if all of its data can fit into a cache. Unfortunately, not all programs can operate on such a small size of data. We have also learned that prefetch actually works. If the hardware can figure out your memory access pattern and you're not exceeding cache size too much, the prefetch will make your program a lot faster. You may have noticed that in the plot, I have had a lot more data than I'm showing here. 1K, 2K, 4K, I had a lot more points. I also went to higher values, but that's easy. But how did I put more points in the middle? In addition to the range, you can actually specify the values yourself directly, and that's what I had to do. So instead of saying range, you can just say arg and put the number. Arg, another number. Yeah, it's repetitive. That's why I'm using the macro. So I put all these args into a macro, and I'm using this macro at the end of all of the template fixtures. This time, I can run with these arguments for all the different word sizes. And I'm going to run just the writing portion. I can separately run the reading portion. So I'm going to benchmark how long does it take to write all these different sizes of memory, writing one char, 1 byte at a time, short, 2 bytes at a time, 4 bytes at a time, and all the way up to 256 bits. Well, you can already see that for writing the same 1 kilobyte, 1 byte at a time takes a lot longer. It was 38 nanoseconds before on the same machine. We're done with char. We're now to short, twice as fast. For the same kilobyte, 151 nanoseconds. It'll get faster as we use larger words. This actually makes sense. The operation itself takes certain time. Specifically, it takes 1 cycle or maybe 2 cycles, depending on the hardware. But if you're writing only 1 byte per operation, then you need more operations than if you're writing 4 or 8 or 16 bytes per operation. So the larger word you can write in one operation, the faster it's going to go. See, the same 1 kilobyte, 4 bytes at a time is 80 nanoseconds. Getting even faster for longs, that's 8 bytes at a time. Now we're into SIMD instructions, 128 bits, 16 bytes at a time. Remember how long it was for a long, 38 nanoseconds for 1 kilobyte. 19 if we can write 2 longs at once. Now that's interesting. The same 19 for 256. This particular result will not be repeated on every piece of hardware. This is a relatively old processor using 32-byte SSE instructions does not appear to run any faster. This is not universal. Newer processors will be faster at 256-bit instructions and even faster at 512. What is this void type? Well, what I did was actually specialized the void fixture to run the library version of memory copy. I'm just calling libc, using memfill in this case for write, to see how fast the system library can do it. Well, it's a little slower than SSE, but it's faster than longs. Whatever they're doing inside is pretty good. This is in general true if you need something that a system library provides, like copying some bytes from one place to another. Call memcopy, it will be pretty close to optimal. Putting all this scrolling data together in one big chart, this is what we see. Again, this is for the particular machine. You can see that writing is a lot faster if you write more bytes per operation up to a point. On this machine, 128 into 56-bit operations don't buy you any additional advantage. Going from long to 16-byte SSE instructions does buy you quite a lot, almost doubles your memory bandwidth. We can still see the cache size jumps, and they're all in the same places, so that doesn't change. But the speed of memory transfer changes quite a bit. What else have we learned from this exercise? Of course, that reading and writing more bytes per operation makes it faster. This is a case where you really should be using longer words. So here are our takeaway points from this section of the class on memory and its effect on performance. Let's take a break. See you in the next section. Let us continue our exploration of memory architecture in the next section, which deals with memory access patterns and their impact on performance. Earlier, we have seen this graph where the steps in memory bandwidth clearly indicate the three levels of caches and their sizes and their speeds. I have also explained to you that the reason memory bandwidth doesn't just drop off after we exceed the size of a particular cache, but decays slowly, is the prefetch, the hardware pulling in memory that is about to be accessed into the faster cache because it anticipates the access. Now, the prefetch is clearly visible in the transition areas between, let's say, L2 and L3 cache. But does the prefetch just stop working after this transition area is over? Why would it? Why can't the hardware continue to predict that the next byte, the next word, is going to be accessed and keep pulling it until 2 or 3 cache? Well, in fact, it does. We just don't see it here. Is there any way for us to discover that the prefetch continues to work? The simplest way would be to turn off the prefetch. Can't quite do that directly, but there is a way to defeat it. In the process, we're going to learn something extremely valuable for performance optimization. The same thing, of course, will happen after we exceed the size of L1 cache. The prefetch probably works here. How would we detect that it does? Let's construct another benchmark where we're going to, again, write. We will keep using all the tricks that we have learned so far, in particular manual loop unrolling. We're going to write sequentially, and we're also going to write in a random order. So instead of just advancing the pointer, we're going to take random increments from 0 to n, where n is how many words we have in that memory range. The idea here is that we will try to defeat the prefetch. If the prefetch works by figuring out access patterns and predicting them, we're going to try to create an access pattern that the prefetch cannot predict. There is no way the hardware can guess what the next word would be, therefore it cannot pull it into the closer cache, therefore it would have to fetch it directly from the main memory. Let's run this. This is our sequential access. We didn't have to rerun it, but it's good to have both benchmarks in the same test. In case you change something and you don't know that you've changed it, you would see that the numbers for sequential access have changed. Wow, look at this. Sequential access, 38 nanoseconds for 1 kilobyte. Random access, 84,000 nanoseconds. And it keeps getting worse and worse. Is that seem too much to you? When something is too good to be true, let's re-examine it. Yes, we have defeated the prefetch, but we also inserted this rand call. And this isn't cheap. We're actually benchmarking the call to rand, not so much the memory write. If we don't want to do that, we have to get rid of the rand call, at least within the benchmark loop. Now, we still want random memory access, so the trick is we have to put the rand call outside of the benchmark loop. And here is how we're going to do it. We're going to pre-compute random indices. There are as many indices as there are words in our test memory range. And then when we run the benchmark, we're just going to use the next random number that is already pre-computed in our index buffer instead of actually generating the random number on the fly. Is this going to be faster? There is a slight noise in every benchmark. The previous one for sequential access was 38 or 39 nanoseconds. This one is 40. If we run it again, maybe 38 again. Random access, much faster. At least for small sizes, it is much faster. It's the same 38, 39, 40 nanoseconds for smallest size, but it's almost 10 times slower for 16 megabytes. Now, that's still not as bad as benchmarking the RAND, but we have seen that what you benchmark matters and has to be examined very closely. What do we benchmark? In sequential access, we just benchmarked writing into a pointer that was being incremented. In the random access, we have this index. Well, computing index probably takes time. More importantly, storing the index takes up some of the cache space. So in order to be fair, we would have to measure sequential access using the same index technique. It just wouldn't be a random index. Well, we can do that. Here is yet another benchmark fixture. We'll call it no rand. It's exact copy of the rand fixture, only instead of storing a random number, we will store consecutive numbers into the index. Otherwise, we're using the same memory access, so we will now see if there is any overhead for indexing. We're now running sequential access using index, and random access was the same index but random. We can see the overhead of the index, not much really at small sizes, basically the same within noise. A little bit of overhead at larger sizes. This is probably because index occupies the cache, so effectively we have less of it to use. And random access does run slower than both indexed and non-indexed sequential access, especially at large sizes. Let's put it all together in the graph. Again, we will need more points in the graph than the simple range of numbers doubling up every time provides. We're going to need manually specified points to have a nice accurate curve. We can do this with this manual arg. And this is how our data looks like when plotted. I went to a larger machine that actually supports effectively 256-bit words. It is faster on 256-bit words. I wanted to get to larger memory sizes to show the differences better. So I went to 64 megabytes ranges, and it is a newer processor. It supports 32-byte SSE instructions. Let's look at the differences. This is memory bandwidth. The overall number is also a little higher. The newer processor, faster memory bandwidth. At small sizes, when we are inside L1 cache, doesn't really matter. Indexed access has a lot of noise in the measurements. These numbers are not entirely reproducible, but the trend is about the same. So these sharp spikes go up and down, depending on basically the mood of the hardware. Just varies a lot. Still, 32 kilobytes is L1 cache, 256 kilobytes the second jump for L2 cache. Why does the jump start to occur before the size of L3 cache? We're draining the cache to store the index in addition to the words we are writing. So effectively, we have less cache. L3 cache is 8 megabytes on this machine. Let's focus on this difference between sequential and random access. Let's say for the data in L2 cache. So all of the data fits in L2 cache either way, but for sequential access, we have a lot more bandwidth. That is the prefetch. That's the prefetch into L1 cache that is still running, even though we don't see this slope of slowly decaying bandwidth as we see right near the jump from L1 to L2. That slope leveled out. But the prefetch is still running, and the prefetch gives you this continuous speed up over the raw speed of L2 cache. So the random access line gives you the bandwidth that L2 cache is actually capable of. And the sequential access line actually gives you the bandwidth of the prefetch trying to fetch as fast as it can from L2 into L1. It's doing a pretty decent job. It's about 1.5 times faster. The same thing happens between L2 and L3 caches and L3 in main memory. So the prefetch works everywhere. As soon as you exceed the cache size, it gives you the overall speed boost, makes it seem like your second level, third level caches are a bit faster than they really are. So again, this is the prefetch into L1 responsible for the speed gain. So what have we learned? Most importantly, we have learned that sequential access is a lot faster than random access. This has to do primarily with the prefetch, with the ability of the hardware to predict memory access patterns and optimize fetching data into cache to give you maximum memory bandwidth. By making your access pattern unpredictable, you defeat that portion of the hardware and you get the actual cache speed, which isn't nearly as fast as the higher level cache. We have measured so far the memory speed in bandwidth. How much is 10 megabyte per second? Well, that's a little hard to say. Let's convert it to nanoseconds per individual operation. So again, if it's 64-byte integers we're reading and writing, that's nanoseconds per operation, per writing or reading 64 bytes at a time. The horizontal axis is the same, the vertical axis is essentially inverted, and we see that it takes a lot longer to write into the main memory once you exceed the L3 cache size than to write into L1 cache. It takes particularly longer if you have defeated the prefetch. So the random access line basically is the speed of the memory as it really is. And the prefetch tries, but there is very little it can do. For sequential access, there is 4 times speed up at large sizes. That's the prefetch giving you essentially the speed of L3 cache. Well, not quite the speed of L3 cache, but a good portion of the speed of L3 cache, even while you're writing into the main memory. We have seen that index uses the caches, so you effectively have less than 8 megabytes of L3 cache. By the way, 1 nanosecond, 5 nanoseconds, how much is 1 nanosecond in terms of computing? How much can happen in 1 nanosecond? Well, we have to compare it with some computing operation. Simplest operation is just addition. So how long does it take to add? Well, we're on the roll with benchmarking here, so let's just put increment inside a do not optimize wrapper in our benchmarking fixture and test how long does it take to increment, let's say along. 2 nanoseconds per increment. Takes 2 nanoseconds for a basic arithmetic operation. 8 nanoseconds is significant. Several adds could be done in this time. So what have we learned? Not only sequential access is a lot faster than random access can be slower than computing. The memory speed can dominate your program. This could be a major impact on your performance. Obviously, you would want to know about this and you would want to optimize it, and you want to avoid having your program dominated by the slow memory speed if you can. This one curve here will have huge, major impact on your algorithms and your data structure designs. Let me give you a very simple example. Let's say we have 1 million numbers, well, maybe they're longs, 8-byte numbers, and we want to access them all sequentially. We can store them in an array. It'll be 8 megabytes worth of memory in an array, so we're going to do sequential access, and this is the speed we're going to get per operation. 8 megabytes fits exactly into L3 cache on this machine. Let's say that you have chosen list as your data structure. List, in addition to the data itself, will have 2 pointers per node. Let's say pointers are 8 bytes each, same as long. So now we have 24 bytes per node, 1,024 megabytes of data. Not only we have 3 times as much data, so we are further to the right on this axis, where 3 times more memory, we're paying penalty for that. But list is actually scattered randomly in memory. Even though we're accessing the elements sequentially, we're accessing the memory randomly because the order of allocation is unpredictable. You call malloc for each element of the list, you get address from anywhere. So now you went from accessing 8 megabytes sequentially to accessing 24 megabytes randomly. This unfortunate choice of data structure cost us a little over 10 times in performance. This is perhaps an extreme example, but as a part of a larger data structure, you might very well end up making such a design choice, and this is the price. The choice of algorithms and data structures will critically affect both the data size and the access patterns. And both the data size, the memory size, and the access patterns have major impact on the performance of the program. Could be an order of magnitude easily. So you should be very much aware of the access patterns and how well your data fits into cache and how likely you are to miss the cache, how often is the cache miss, and what is the cost of a cache miss, because if you miss the cache, that wait is longer than a single arithmetic operation, longer than several arithmetic operations. It could be longer than the entire processing, the entire computing you are going to do on this element if your program is not very numerically intensive. So keep this in mind when you're designing your data structures. Welcome back to the next section of our class on memory architecture and performance impact. We're now going to talk about multiple CPUs. Remember this memory bandwidth chart? We have seen them before. All the caches and the prefetch. We've seen the cache impact. All of that was for a single CPU. Remember, I have shown you the memory architecture diagram. There is usually more than one CPU these days, or at least more than one CPU core, and they're all accessing the same memory. They're not, however, all accessing the same caches. Some of the caches are shared, some are not. So far, this is what we have covered. Just one CPU accessing its caches, the shared caches, and all the way to the memory. But that's not all there is to the memory system. Now let's look at multiple CPUs and how they all work together with the memory. We can use the same Google benchmark library, and this is our memory writing fixture that we have already seen before. The only change we need to make is when we instantiate it, and the random access fixture and so on. In these arguments here, we have to specify the number of threads. Now, this is just a macro. Where does this number 1, 2, and 4 go? Here. So all the arguments, like a range or manual selection of arguments, this is all the same. We just add this parameter threads, and this will run the benchmark on multiple threads. Now, it runs the same benchmark, so all it does is it runs this code here on 1 or 2 or 4, however many we specify threads. Let's do it. So it's running one thread, giving us the numbers we have already seen before. The word is long, so 8 bytes, the same 38 nanoseconds. We're now running 2 threads, and it takes 19 nanoseconds to write the same 1024 kilobytes instead of, how long was it? Twice as long? Yes, twice as long. Writing 1 kilobyte, one long at a time, on one thread takes 38 nanoseconds. On 2 threads, it's twice as fast. Now, this is good. That's what we expect. 2 threads writing the memory should be twice as fast. 4 threads, well, faster than 2, but not really. For 1 kilobyte, it's actually the same. For 2 kilobytes, it's a little faster. Now, look here. For 16 megabytes, this is a large size. 1 thread, just a little bit faster on 2 threads, and the same speed, even a little slower on 4 threads. It looks like we're not getting much speed up from threads. What's going on here? To get more data, I don't know if I would call this better data, but at least more of it, I had to go to a server class machine and run the same benchmark. On this machine that I was using to demo this program, really, even 2 threads don't give you much speed up. Large server class machine, lots of memory, multiple CPUs, 64 of them. A little better. So look what we're getting here. This is the memory bandwidth per thread. Let's start with small sizes for where L1 cache is. We're getting the same bandwidth for 1 thread. For 2 threads, we're getting a lot of noise in the bandwidth for 4 threads, but the peak values are about the same. Within L2 cache, that's the first step right here. Again, same bandwidth for 1 and 2 threads, less of it for 4 threads. Similar for L3 cache, except the drop shifts. So 8 megabytes of L3 cache for 1 thread, we have the drop at around 8 megabytes. It's for 2 threads, it's like we have less cache, and for 4 threads, even less. And the main memory speed, once we go beyond all the caches, well, it's slower per thread for 2 threads than it is for 1, and even slower for 4. On this machine, L1 and L2 caches are per core. They're not shared with anybody. L3 cache is shared, and of course the main memory is shared. So we really do get less of an L3 cache per core when all the cores are trying to use it at once. That's why we have the step of L3 cache move to the left. Well, that's memory bandwidth per thread. Let's add up all the memory bandwidths together, total memory bandwidth. So it goes way up in the area where L1 cache is, so I cut it off for high number of threads. It just scales with the number of threads. So L1 cache is per core, so we get twice as much bandwidth for 2 threads than for 1, and again, twice as much for 4 threads. But look here, total bandwidth for 1 thread, total bandwidth of the main memory for 2 threads, more, not quite twice as much, but more. Total bandwidth of the main memory for 4 threads, exactly the same. 4 threads all writing together aren't giving us any more memory bandwidth than 2 threads. It gets better when the memory accesses are cached. 4 threads writing into L3 cache give us more aggregate memory bandwidth than 2 threads and more than 1 thread, although, as we've seen before, we effectively have less of an L3 cache because it's shared. What we have seen here is we have totally saturated the main memory bus with just 2 CPU cores writing at full speed. On this machine, it takes just 2. Depends on the hardware exactly how many. And we haven't actually had anything interesting going with concurrency here. These were just completely independent threads, could be independent processes. They don't know anything about each other. Each of them has its separate region of memory. There is no sharing, there is no locking, there is no interaction between these threads at all, except that they're using the memory controller. And they have completely saturated the memory bus. So the main memory is not fast enough to feed the data to all CPUs at once at the maximum speed. Well, that's one explanation. Another explanation would be that our CPU isn't fast enough, can't run at full speed. Again, benchmark to the rescue. On this same machine where we have seen even 2 threads give us barely any speed up, let's see if incrementing a number on 1 thread and 2 threads and so on makes any use of threads. Again, this is a very basic parallelism. There is no interesting interaction going on. Each thread has its own number and it increments it. We're just checking, making sure that we actually do run 2 threads at the same time. Maybe somehow we run just 1 thread at a time, and that would explain why we aren't getting any more memory bandwidth. Let's run. It's faster for 2 threads than for 1, but we're getting zeros here. It's too fast. Well, we can leave it at that, or we can actually try to find a way to get these numbers accurate even for such a small value. Well, the simplest thing to do is just put more of these operations. We keep the compiler from optimizing them. Don't do the loop here. Loop overhead will be larger than the operation itself. Just manually unroll it. Well, now that's better. Remember, this is 4 increments, so 2 nanosecond is individual increment. Twice as fast on 2 threads, twice as fast again on 4 threads. Nothing more after that. Not surprising, this machine only has 4 cores. Would go faster if we had more. Okay, so threads do run in parallel at the same time, at least up to 4 threads on this machine. So we really do saturate memory bandwidth with somewhere between 2 and 4 CPU cores accessing memory at the same time. So we've seen that the memory is not fast enough to feed the data to all CPUs. Well, what can we do to improve performance of our multi-core programs? Just from the point of view of memory usage. Use less memory, of course. Easier said than done, but sometimes it's possible. And if you can use less memory, you will speed up the program. Remember from the memory bandwidth charts for multiple threads that the problem wasn't nearly as bad for cache accesses. And that's because caches, of course, are either not shared at all, they're per core, or if they are shared, they may be shared between fewer CPUs. On a large system, you may have L2 cache shared just between 2 cores and L3 cache between all of them, or maybe not even all of them. Try to keep your data in cache. Not only it's good in a single core program, it's even better in a multi-core program. How would it look like in your design? Well, let's think of how a cache-efficient memory access might look like. We have several CPUs. I just have room for 2 on the slides, accessing main memory. And they need to access all the data in the main memory over and over again. Let's say that we're accessing a lot of data, a lot more than the cache size. Doesn't really matter which cache for the purpose of this illustration. if it would be L1 cache and you could fit it into L1 cache, of course, you would get faster results than if you can only fit it into L2 cache, but whatever cache your data fits in. What can we do? Instead of sweeping through the whole memory range at once, we can do multiple sweeps over the cached region, then go to the next cache region, then the next, and so on. When we switch from one region to another, of course, there will be a lot of cache misses. But because we are accessing the same memory multiple times, the second round of accesses will be a lot faster. The data is already in cache. This all sounds very intuitive and very clear, but again, remember the first rule of performance. Even though it may seem intuitive, it isn't. You really have to benchmark or profile your program to see if memory accesses are really critical for your performance, and if changing the memory access pattern to stay longer on the same cache location actually benefits to you. In general, it will benefit more the multi-core programs. It may even make single-threaded programs slower because there is usually some overhead for shorter iteration and many iterations. So remember to benchmark. Remember to profile your programs. Never guess about performance. Rule number 1 of performance, never guess. This being said, there are things you can learn and in general apply. Here are our takeaway points from this section. Several CPU cores, how many will vary, but not many, will completely saturate the memory bus if they go at full speed. You can help to remedy this situation by using less memory, by taking advantage of the fact that the caches are not shared between CPUs, or not shared quite as much. If you do nothing, beware. The total memory bandwidth you have seen is enough to feed just maybe 2 threads. So in the extreme case of a fully memory-bound program, your scaling could be limited to as low as 2x. You add more cores, you run more threads, and the program doesn't go any faster. Making your program cache efficient can break through this bottleneck, and you can take advantage of much larger aggregate bandwidths you get from the caches. We have concluded our class on memory exploration, but it is a much larger subject. We haven't fully covered it, of course. We have touched just the general and the basic parts of it. So if you're interested in understanding how memory access affects your performance, here is some independent study. If you're fresh out of college, you may know it as homework. You can explore a lot of interesting things about memory. We have seen how effective prefetch is for sequential access. What if it's sequential access with a stride? Is it still efficient? Would it recognize more complex stride if you access every third and every fifth word, let's say? What about reverse access? We have always been accessing memory from 0, 1, 2, 3 up to n. What about n, n-1, n-2 down to 0? Is it the same speed or not? What happens if we change the direction of memory access in mid-access? We go all the way from 0 to n, then all the way back, then all the way forward again. Would it be faster, slower, the same speed? There are a lot of interesting things you can learn this way about your hardware, about how memory works, and about how to write efficient programs. The general techniques you learn this way, they can be valuable to you. Go on, satisfy your curiosity, and come back. We'll see you in the next class. The question of measurement of time for the purposes of measurement of performance of our programs is essential for any work on high-performance computing. You cannot quantify what you cannot measure. In this chapter, we will dedicate some time to exploring how we can measure performance of C++ programs and what are the different options here. Before we can start to talk about performance, we should remember the first rule of performance, which is never guess about performance, always measure it. Performance is often counterintuitive. Even assumptions based on solid prior experience often turned out to be incorrect. There is, however, the second rule of performance, which is your measurements must be relevant. What do you mean by relevant? You could say, well, it's relevant to your application, it's relevant to your environment. Remember that performance should always be measured, but also measured correctly. Now, there are several ways to measure the performance. You can measure the performance of the entire program or parts of it. If you want to measure parts, it usually requires that the program be instrumented. That instrumentation can be done by hand, by inserting timers into the parts of the program which you want to measure, or there are some tools that at compile time or at link time will automatically instrument the program by taking measurements of functions or loops or some other groups of instructions and sections of code. Profiler tools, some of them do exactly that. They instrument the entire program and then build the performance profile. Some don't need compile time implementation, use only link time implementation or instrumentation or no instrumentation at all. On the other hand, there are microbenchmarks which measure performance of small code fragments in separation. So you take just your small code fragment, put it in a microbenchmarking framework, and it runs it over and over, measuring the time, gathering the statistics. It uses some kind of timers, either explicitly you put the timers in if you write your own microbenchmark framework, or you can use one of microbenchmarking libraries, then they have it done for you. Now remember, we talked about relevance of measurements. The first part of relevance is what exactly do you measure, what is the performance to you. In the context of high-performance computing, usually it's the throughput, which is you have a certain amount of computing to be done, how long does it take? So operations per second or hours per simulation, whatever the case may be, but that's not the only metric. In power-sensitive systems such as embedded or mobile systems, power utilization may be more important, or at least amount of computation per watt of power could be important. You could, in some cases, measure power directly, although CPU utilization may also be used as a proxy for power measurements. Now, there are many other metrics. For example, real-time and low-latency systems are actually more interested in latency than in throughput, especially in the latency tail. If something is very fast, but 5% of the time it takes very long time, that's not a good situation for real-time systems. So in addition to the metrics, you have to select representative for your situation programming environment. It has to be, of course, on the right hardware. The problem size has to be correct. For example, if you are measuring how long it takes to sort some collection of data, you will find that sorting 10 elements and sorting million elements are very different things. They're limited by totally different factors. So you have to know how many elements you typically sort in your real application. Realistic input, so on. Now, assuming you have done all of that and selected the measurements and the context for the measurements that are relevant to your application that you're trying to improve, the question then becomes, how do you measure time? And we will start with the lowest level stuff, which is the timers themselves. Now, timers, of course, measure real time or CPU time elapsed from one point of execution to another, so they actually measure the duration of time. You can use them in microbenchmarks if you just run the same fragment of code over and over again and measure how long it takes. You can put timer calls into your program and measure how long some function takes or some loop takes. It's up to you to instrument the program, so you have to have some information about which sections of the program are worth instrumenting and which are important. If you don't, you usually start from the high level. Let's instrument, the top functions, however many of them you have. You find what takes the longest, you delve into it, instrument portions of it, and so on. If you use some benchmarking or profiling tools, they'll have timers hidden away from you. But sometimes the most direct result is the simplest, the most straightforward. Put your own timers, get the result. So I want to teach you how to do the timers. Doing timers in the context of microbenchmarks is somewhat different than doing it in a real program. In your program, you just put the timer calls directly into the program at the beginning or at the end of the function usually, and accumulate the time. Microbenchmarks measure a very small code fragment. Usually you have to run it many, many times and accumulate the total runtime, divide by the number of iterations, primarily because it's easier to measure large time intervals. There are libraries that help you both run the code many times and do the statistics. There are a couple things you have to worry about here. First of all, the compiler can detect that you're running the same chunk of code over and over, presumably with the same result, and can figure out and optimize it. In the most extreme case, the compiler can just figure out that the last iteration is the only one that matters, because the result is always the same, and optimize everything just to one iteration. In the more extreme case, the compiler can figure out that you're actually not using the result and optimize everything away. There are ways around it. Now, the hardware also has certain capability to optimize performance of repeated instruction, but your view on it is somewhat different from the compiler optimizations. The compiler optimizations you want to have the same as in your real program, which is you don't want to compile without optimizations completely, but you also want your fragment that you're measuring, the fragment of code, you want it to be optimized just like it was in the actual program. Now, the hardware can often optimize predictable computations. It's not that it figures out that you don't need something. It still has to do the instructions. But things like prefetch, memory prefetch, branch prediction, and caches are all operating basically in the assumption that whatever happened before is going to continue happening in the near future. This can work both for you and against you in microbenchmarks. Now, you can discover that your microbenchmarks are too predictable, and so your measurements are not entirely accurate. On the other hand, you may discover that in your real program, the hardware is in some sense primed for the execution of your code because you already operated on that memory before in some other portion of the code, whereas in the microbenchmark, you're starting from cold memory, which is why microbenchmarks usually also prime the execution by doing a couple iterations that are not counted. The timers we're going to be using are the hardware high-resolution timers, and on Linux you get to them through the clock get time system call. We'll see the code in a moment, but you have to choose which clock to use. There are several clocks running. In particular, there is a real-time clock. That's just the actual what's called wall time. There is the process CPU time. That's the time for the entire process. There is also CPU time per thread, the thread that makes the call. If you measure the process CPU time in a multi-threaded program, then no matter which thread you're calling from, you will get the entire CPU time for the whole process for the duration that you're measuring, not for the thread that calls. The thread CPU time will measure only for that thread. The timers have resolution, which is typically 1 nanosecond, and there is another system call that tells you what that resolution is. On x86, it's usually 1 nanosecond. It does not mean that you can measure 1 nanosecond interval. What it means is that if you make calls to this timer, you could get, like let's say you make them on different threads, you could get values that are 1 nanosecond apart. But if you make 2 subsequent calls right away to the timer, you will never get 1 nanosecond, at least not on any current CPUs. The timer itself takes somewhere between 50 nanoseconds and 150 nanoseconds. So it means you can't use it to measure performance of just one instruction, unless, of course, you repeat that instruction over and over, because typical instructions are 1-2 nanoseconds. Sticking these timer calls into your program, you have to be judicious about it. They're not free if you stick them every 50 nanoseconds of your own code. They will severely distort the runtime that you're trying to measure. These timers are reliable, easy to use. Let's take a look at the code for the timers. As I said, the timer itself is right here. That's it. That's the timer. You need some header files to use them. All your programs must be linked with this library, the librt. Since we're doing our work in C++, we should package these timers in a C++ manner. So here is one way. A timer class. So I have the timer class here. As I said, there are at least 3 clocks. There may be more on particular operating system. This class, you specify which clock you want to use. The use of all clocks is exactly the same. You call the clock get time with the clock. It's really just an integer. This is what's called time spec. It's a struct. It has 2 fields in it. Well, let's look at this one here. For example, it has seconds. So the one field is seconds, and the other field, it has nanoseconds. What this function does, it puts the number of seconds into the seconds, and whatever is left from the whole second, it converts to nanosecond, puts into the nanoseconds. If you want to compute duration between 2 different time values, between 2 different time specs, this is how you have to do it. You subtract the seconds, and then you subtract the nanoseconds, convert everything. Well, let's say we want the result in seconds as a double. Multiplied by 10 to minus 1, convert it all to seconds, return as a double. So the construction, it captures the time at the moment when the object was constructed, and then you can call time anytime, and it'll tell you how long it has been in seconds since the object was constructed. This is, by the way, how you get the resolution of the timer. As I said, it will typically return 1 nanosecond. Don't be fooled. Doesn't mean that you can get 1 nanosecond measurements accurately. You can't. We'll see some benchmarking in a moment. You will be repeating these 3 clocks over and over in your program, so let's just wrap them up in derived classes. Here is high-resolution real timer, derived from high-resolution timer. All it does, it passes clock monotonic to the constructor. Everything else it inherits. Here is high-resolution CPU timer. This is the process-wide CPU clock. And here is, of course, high-resolution thread timer, thread-specific clock. Now, this just returns the time since the object was constructed. You may want to accumulate the time you spent in a certain function over multiple calls to this function. For that, you just write another object that has, let's say, start timer and stop timer calls, and it adds to some value that it accumulates the difference, let's say in this case in seconds, it's a double. This way you can accumulate the total real time or CPU time spent in some function or some loop or some other portion of the code. Now, if you happen to write such code, remember that code is never correct until it's tested. How would you test timers? Well, you trust the hardware that timers themselves are accurate. So it's the question of how do you test your own code? You can measure how long the time call takes. Here is how we can have some idea that, at least we're not returning total garbage. For example, if we use a CPU timer and we time a sleep call, there shouldn't be any CPU time passing, but should be some real time passing. So here is we time the sleep call with a real timer. Here is we time it with CPU timer. On the other hand, if we use the same CPU timer, here is the CPU timer, and what we time is some real computing, doing some computations, that should run up some decent CPU time. Remember that this should be linked with LRT. Our tests are done, finished with the expected results. So let's have a short break, and then I will show you another timer which has a certain aura of mystery around it. Now I'm going to reveal for you the secrets of the TSC timer. x86 has another interesting timer, which I probably wouldn't talk about if there wasn't so many misconceptions about this timer. You may discover it on your own and start using it, and I want to show you what it really is, and if you need to use it, I want to show you how to use it. Mainly, I want you to know the accurate information about this timer because you can read a lot about it. It sounds kind of like magic. That's the TSC, timestamp counter. It's basically a hardware counter on the processor that measures the number of clock cycles elapsed since some time in the past. Ultimately, the way to get it is by using an assembly instruction, rdtsc. There may be an intrinsic provided by your compiler. It has very high resolution. It's 1 cycle. It's low overhead, lower than the high-resolution timers, about 15 nanoseconds per call. It has pretty high variation, probably mostly due to caching both instruction and data. It has some other problems. High variation is a good reason to be cautious around it, but it has serious other issues. Now, the reason you might be using TSC is primarily if you want to try to measure a very short duration. Because if you are measuring either a long function or you're running a short function 1 million times and measuring that, you can use the high-resolution timer. The cost of the timer is not particularly important. The only time when you care about 15 nanosecond per timer call versus 50 is if what you want to measure isn't that long. That's where you have to be aware. So first of all, this rdtsc is not a serializing instruction. What it means to be a serializing instruction? It means if you have a serializing instruction, it means that all instructions before it will finish before that one runs, and all instructions after it will not start until it finishes. In other words, it flushes the pipelines, which is a very bad thing to do on the modern CPU. It severely degrades the performance. But if you want an accurate time measurement of just few instructions, you have to make sure that those instructions actually don't run before you get the TSC counter. Similarly, you can get some other instructions running, getting mixed in with your TSC measurements. The way to avoid this problem is to use another instruction called CPU ID. Normally, it's used to return the identification codes of the processor, like what's the model number, which version, which stepping, and so on. In this case, we don't care about any of that, but CPU ID is a serializing instruction. It also isn't free. Now, you have to be careful with inline assembly. These instructions operate on registers in an implicit manner. They change registers. So normally, assembly instructions, they change the registers which you give them. So if you say load into register EIX, well, EIX will change. These two will change registers which are not in the instruction itself. So you have to mark them as clobbered. We'll see that. Results are in clock cycles, not in nanoseconds, which shouldn't be a problem normally because you know what's the clock frequency on this CPU, unless you have clock scaling. Before you use this timer, you have to turn off power management, which is the clock scaling. Another possible problem is that, in general, computations migrate from one CPU to another every now and then. Operating system does that. It used to be a big problem because different CPUs just had totally different TSCs. On pretty much every CPU you find today, if it's not more than 3 years old, TSCs are synchronized between different cores fairly accurately, although moving the computation may take some time. The easiest is to avoid this problem altogether by forcing the thread affinity to one CPU. Then you don't have to worry about it. All right, let's see how the TSC timer actually is used. This whole thing about carefully using it is so important that I actually went ahead and wrote the comments. As we said, it's not a serializing instruction. You need to call CPU ID. There are actually two instructions that you use, one to read the timer at the beginning, one to read at the end. The one at the end is half serializing, so that's okay. So let's look at the code. As I said, inline assembly, can't avoid it. Here is your CPU ID to serialize it because our DTSC is not serializing. There is nothing here to tell you where the result actually goes. You just have to know it goes into these registers. So these two will be affected. What you don't see anywhere here is that all of these will be clobbered. This instruction will basically change the values in these registers. It uses them to store its own temporary results. So what does it mean for us? It means that the compiler should know that when we call this function, the start, all of these registers can change. The compiler should either not keep anything persistent in these registers or stash it away. The compiler doesn't inspect the assembly. Well, it does, but not that closely. In particular, the compiler will not know, just by looking at this instruction, that these registers are clobbered. You have to tell it. If you forget, you will get strange errors where the compiler may choose to save some totally unrelated variable in one of these registers, and the value will change. Very hard to debug. Here is how you read the timer at the end. As I said, this is half serializing, so you can get the value. Then you can call CPU ID, but now outside of the timing measurement. So that's fine. Again, there are clobbering registers, and you can get the result. It returns the unsigned 64-bit integer here, but it tears it apart between two registers. As you can see, it returns half of it in AX, half of it is in ADX, even though they are 64-bit registers, but it uses 32-bit in each. That's just the weirdness of that instruction, so you have to put it all together. You can try to run our DTSCs without the serialized instructions. It'll be somewhat faster, although not on all CPUs. On some CPUs, it won't be that much faster. It will be less accurate, but in some cases, it may be worth it, and we have to benchmark whether it's faster or not, which we will do a little later. You also want to know how long the clock cycle takes. We have a function for that. This time, you actually have to use a high-resolution real timer together with the TSC timer. Doesn't matter what you do to get the clock cycles elapsed. The clock cycle is running whether you're computing or not. Here, we're going to sleep for some time, and then we're going to take the real time and the TSC time, and this tells us what was the nanoseconds per cycle. That's pretty much it for the TSC timer. We'll see how they're all used and how they relate to each other performance-wise in a second. Let's run some benchmarks and see basically how long the different timer calls take. We can do some measurements on our timers. Primarily what we want is to measure basically what's the shortest duration that we can measure. We make two calls to the timer and we see what's the difference. Now, there will be statistical variation between these measurements, so we're going to accumulate over several attempts and get the average. In case of our TSC timers, the same thing is done with start and stop. And before we start any measurements, we're going to detect how long the clock cycle is and report that. So we can convert everything from clock cycles to nanoseconds. Okay, what do we see? The clock cycle on this machine, 0.3 nanoseconds. We spent 1 second waiting, and we had 3.4 billion cycles. The TSC timers, the fast timer on this machine, the fast one, remember, it's somewhat of a misnomer. It's the one that doesn't call CPU IDs. Actually isn't any faster than the accurate one. So on this processor, we would always use the accurate TSC timer. Why not? The real timer here is actually pretty fast. It's faster than the 50 nanoseconds I promised you. On this processor, it's 27. The CPU timers are both a lot slower. They're over 100 nanoseconds each. So that's, again, the duration between two subsequent calls to the timer. So if you make 2 calls at the beginning of the function and the end of the function to get these times, you will never get less than 100-something nanoseconds, even if your function does nothing at all. So timing very short functions using the CPU time is just a waste of effort. You will never get accurate measurements. If you can get real time from somewhat shorter functions, or TSC, which is also real time, you can get from a bit shorter functions. But still, you have to be mindful that it takes about 15 nanoseconds per call, so you don't want to instrument very short functions even with this timer. Well, now you have all the timers that you can use. And then let's go talk about how to not use them quite so often, use some higher level tools. Let's have a short break, put the tricky TSC timer aside, and then I'm going to show you some of those tools. Let's very quickly review some of the profiling and benchmarking tools that are available to you. This is not going to be exclusive, but it will get you started. So while we're still on the subject of measuring very short times, this issue mostly comes up in doing microbenchmarks. You could write your own, similarly to how we just benchmark those timers, just run something for 1,000 times or 1,000,000 times, measure how long it takes. Or you could use one of these microbenchmarking libraries. They do the measurements for you, they do the repetitions for you, they don't handle the optimization issues. The code that you put into its measurement fixture, you still have to worry about the compiler optimizing it. So you have to take care to basically trick the compiler into not optimizing away the result. There are different ways of doing it, and as we go through other chapters of this class, you will see many examples of it. In this class, we're going to be using the Google Benchmark library, which you can download from GitHub. A very similar function-wise library is Nonios. In my opinion, no particular reason to prefer one over the other. They're very similar in functionality and quality. Use whichever one you like more. Stepping up from microbenchmarks, we can talk about measuring real code, measuring whole functions, or entire programs. And this is where we get to profiling and benchmarking large volumes of code. These days, the most common and the most accurate and the best way of doing it is using profiling tools which operate on hardware counters. What are the hardware counters? All modern CPUs have several counter registers that count certain events while the program executes. They just count them in real time. It's just basically additional amount of silicon on the transistor that is dedicated to these events and counters, so it doesn't cost you anything extra. There are events such as instruction being executed. That's an event, could be counted. CPU cycle, that's an event. You can count those. A cache miss or a cache hit, that's an event. Instruction cache or data cache. Branch predictions correct, branch predictions incorrect. Pipeline stalls, there are probably hundreds on a modern CPU of these different events. What exactly you have depends a lot on the CPU, and when I say depends a lot, I really mean depends a lot. 2 CPUs from the same model, like 2, for example, Ivy Bridge, CPUs from slightly different revisions could have slightly different events available. There are hundreds of events, but there aren't nearly that many counters. You can find 8 counters on recent CPUs, 4 on slightly older CPUs. When you set up a profiler run, you select 8 or 4 or however many counters. You have that many events to be monitored. All counters can monitor all events. There are very few restrictions. Some events just don't go well together, but never mind that. Special case, you probably will never run into it. For the most part, you can select any group of events, just limited by how many counters you have. I told you that counting is free, meaning it doesn't slow down your program. Reading the counters at the end of the program is also free, so you can just run your program and ask, okay, how many instructions were there? How many cache misses did I have? That may be useful. For example, if you don't know why your program isn't performing as well as it should, you could just run it, get a total measurement, see, okay, do I have a lot of cache misses? Do I have a lot of instruction cache misses? Do I have a lot of pipeline stalls? And then you can drill down into that. But that's useful only at the beginning. As soon as you start profiling, you would want to know, okay, this function or even this line of code, how much time did I spend in it? How many cache misses did it have? And so on. This requires that counters be read often during program execution. That's not free. So running the profiler, especially with high sampling frequency, it's done by sampling. Just the profiler tool will just grab the values of those counter registers every millisecond or however often you tell it and dump them to disk. So that is not free and can slow down your program. There are lots and lots of profilers for you to choose from. Start from this one, Perf. It's available on most Linux systems, just comes with the system or at least can be installed as a part of the system install. There is a very similar profiling set of tools called Liquid. It has some additional capabilities that Perf doesn't have. In particular, you can turn profiling on and off from inside the program, which can be very useful because if you have a large program and you're only interested in one function, yeah, you can profile the whole program with Perf and then select only the data for this function, but it may be hard to filter out the data. You get a lot of extra data that you have to sift through. Liquid just lets you collect the data from the point you tell it to start to the point you tell it to stop. It has some additional utilities, like it can pin threads to CPUs and a few other things. The Valgrind tool, which is often used to detect memory leaks and memory corruption, has its sister tools, CallGrind and CacheGrind, that are actually designed for performance measurement. Specifically, they are measuring cache misses, branch predictor misses, things like that. So they are less generic than Perf or Liquid, but they're also accessing the same hardware counters. Google performance tools are also based on these counters. You can download them, they're free. They don't give you access to all of the counters, but they give you your CPU profiling, how long each function, each line of code, how long it spent. It requires link time instrumentation. You have to link with a certain library that they provide. None of these tools need compile time instrumentation. A commercial tool from Intel called vTune is a very good tool available on both Linux and Windows. For the most part, it works with all compilers, like it will work with GCC. Some things it does better if you compile with Intel compiler, but mostly it will work with other compilers as well. It's a very good tool. You have to pay for it. One thing of note is sometimes you have to compile your code in a special way for the profiler. Now, first of all, you want to compile as close as possible to the real program. You want to measure relevant measurements. So your profiling should be of the program that is compiled in the same way as your real program. In particular, if you turn off optimizations, that profiling run is totally useless. It may show you that most of the time spent in some function calls or some code that the compiler can optimize to almost nothing, so that doesn't do any good for you. However, the profiler should also give you results that you can analyze, so you have to have some compromises. For example, very often you want debug symbols so you can annotate back to the source, and that requires that you compile both with debug and optimizations. If you have never seen it before, it may seem a bit strange, but actually the debug flag, even though by default it turns off optimization, doesn't actually have to. It just changes the default optimization, doesn't actually turn it off. So you can set optimization level explicitly and still turn on the debug flag. And all the debug flag really does is it keeps the debugging symbols so you can find out which line of source code corresponds to which instruction of the code. Optimization, of course, moves the instructions around, so the correspondence will be only approximate. Now, some profilers need additional options that they use to properly establish call chains. You should read documentation on this profiler. And some profilers have libraries that you must link in. Most commonly, you would replace the malloc library with the special version of malloc that came with the profiler, so you can profile memory-related things. I can quickly show you an example profiling run, for example, using the same timer benchmarks that we have. It's not going to be terribly interesting, but it'll give you an idea of how it looks like. So the program ran, printed its normal output. Here is what the profiler had to say. wasn't heavily CPU using because it was mostly sleeping. You can see there were this many cycles. We didn't use much memory. The pipeline wasn't utilized very well in this code, which is not surprising considering we haven't actually done any computations. That's basically how you start your real program. You look at these results, pipeline stalls, page faults. You can ask for cache misses. This is just what we get by default. You can choose which events to measure. And then you drill down into the problem parts of the profile. This is all I wanted to show you about timers and profilers in general. We will become much more familiar with specifically microbenchmarking tools as we study in detail performance aspects of threads, locks, and lock-free concurrency. But for now, to become more familiar with these tools, take some piece of code that doesn't have quite the performance you want and run a profiler on it, see if it gives you any surprising results. And throughout other chapters of this class, hopefully I can give you some suggestions for how to improve that performance. In this lesson, we will begin considering the subject of threads, and we start with an overview. First of all, what is a thread? The classic definition is a thread is a sequence of instructions executed independently. This has immediately several implications. First of all, thread must have enough of a state to be executed independently. Typically, a sequence of instructions which is executed has a program counter or its equivalent, the current position in the sequence. It has a stack, it has registers and other parts of the state, which is all very similar to what a process has. Why isn't a thread a process? Well, it sort of is. Threads are often called lightweight processes, which suggests the difference. The threads are smaller, they have less state. The big difference, which is not always there, however, is usually threads all share the same memory space and processes don't. Now, threads always share the same memory space, but processes may or may not. Most of the time they don't, but it's possible on some operating systems to have processes share memory space. So the differences are mainly quantitative. Threads will have smaller state, processes has additional state, signal handlers, and so on. Parent-child process information, processes, threads don't know who the parent is usually. Access restrictions and so on, that's all per process, threads just inherit it on the process. And that touches on the latest difference. Threads are usually contained, if you will, within a process. A process has multiple threads, and they're all part of this process. So the state of the process, the state that isn't part of the thread, applies to all of the threads. On some operating systems, the difference is more pronounced than others. In early versions of Linux, threads really were processes. Before we start actually getting our hands on some threads, let's talk about several different kinds of threads that exist. First of all, there are hardware threads, which are independent execution streams. All threads are that, but these are maintained by the hardware. SMT or hyper-threaded processors have that kind of thread, where one single CPU core, which has the SMT capability, can execute several hardware threads, which means that core has enough hardware to maintain states of several threads, usually one real threads, if you will, and one hyper thread. So it has enough registers, enough other hardware to maintain the state of two threads. Could be more than two. There are, of course, processes like Intel's processes, which have a state for maybe 80 threads for the Xeon Phi. The next kind is the system thread or kernel thread. That's the view of the thread as it's seen by the kernel, by the operating system. They're essentially lightweight processes managed by the operating system. This has nothing to do with kernel access level. This is not privilege. This is about who manages these instruction streams. So kernel threads can do system work, they can do user work, and in fact, all of your program work as a user ends up running on one of these threads or more. User threads is what you actually work with. It's an abstraction which is presented to the programmer by the operating system. Why an abstraction? Because it may not actually correspond to reality. So As a user, you see an instruction sequence executed independently. How it's actually executed, well, you don't know. Could be executed as the sequence, in which case the abstraction is very thin. Could be executed as multiple sequences, could be executed as a part of a larger sequence, and you're just not allowed to peek into that larger sequence. That's why it's an abstraction. Very close to it is the abstraction created by one part of your own program to other parts of the program. That's threads created by the application itself. They're also called fibers. An example would be an application that time slices its own execution and creates this way an abstraction of several sequences of instructions, several sequences of code, whereas in fact the entire application, of course, runs as one process. So in this case, it's a creation of an illusion or an abstraction of threads without an operating system support. Usually, of course, it will be a part of an application managing these threads for the rest of an application, or it will be the library that you use to create these fibers and manage them for the entire application. From the point of view of the rest of the program, doesn't really matter. You see some abstraction, you see some calls you make to start a thread, to terminate a thread, to lock, unlock locks, and so on. So user threads is mostly what you're dealing with. Now, how is user thread different from the kernel thread? Kernel thread is what's really happening in the operating system. This is what OS is actually executing. User thread is an abstraction given to the program, which means user threads do not have to map exactly onto the kernel threads. You think that when you make a call, create thread, you get a new thread started. This may or may not be true. It will behave as if you got a new thread started. Now, why wouldn't it be true? There is a difference between them. It seems very major difference because kernel sees how many threads are really running. Application thinks that there is a different number of threads, different organization of threads. Seems like it should be very important, except usually it's not. Why not? Well, we have to explore this subject of threading model. The most general threading model, when you have a number of user threads and threads, and they map onto a different number of kernel threads. Kernel threads, this is sometimes also called hybrid threading model. A simpler case is when the OS just runs several user threads in one kernel thread. So you have several user instruction sequences that are being multiplexed, so only one runs at a time on a single kernel thread. Yet simpler case is when every time you have an instruction stream from a user, you just create another kernel thread. That's one-to-one threading model. This is what you usually work with. Why? Well, it's very hard to get a working NM threading model. Working is important here. It's almost impossible to get the working threading model. There are several that don't quite work. History lesson in the past, few operating systems came very close. Of all systems, AIX had a reasonably well-working NM threading model. Solaris had an almost working model. Linux and most other Unisys just have POSIX threads, which is one-to-one threading model. Why? It's simple, it's reliable, it just works. If you want to know how it works, read the man pages. There are just a few system calls there. So this is what you need to know about the basics of the threads. Welcome back. We'll continue our work on threads. And this time we will delve into C++ and its relation with threads. C++ now has threads. Since C++ 11, in the standard, there is thread support. You can read about it in the ISO standard. I recommend these two reference websites to learn about C++ as a reference. They don't tell you how to use it well, they just tell you what's in the language. Well, this is cppreference.com. This is what it has to say about std_thread in C++. It's a class, has constructor and destructor and other member functions. C++.com gives us the same information as well as an example. We have a function we want to run as an independent instruction sequence. So on a thread, we have another function. We create a thread, give it the function pointer, and it starts running. When you want it to be done, you call the join. If it's done, it will return immediately. If the function is not done, the function will block. Join will block at this point until the function on the thread is done. If we have already threads in the language, why would I need to show you how you could do the threads? Well, first of all, you may not have access to a C++11 compiler. Second, we're talking about high performance here. For the reasons of getting the best performance of your hardware, you may decide that you need to take control of how the threads are implemented. There may be something you want to put into the implementation that C++ implementation in your compiler does not do. But the most important reason is, even if you end up using C++11 threads, doing it yourself, or at least understanding how it can be done, helps you to understand what goes behind the scenes. Someday you may have a problem and you need to understand something doesn't work well or something doesn't work right. You need to understand what the compiler, what the runtime system, what the library all do to make it just magically appear that you have threads. What's going on and what can go wrong. So let's look at how we can do the threads. First of all, what's a thread? It's a sequence of instructions, so it's a code, and it runs on some data, so we have code and related data, and in C++, a construct for code and data is an object. Same as in the std threads, thread is an object. When you do it yourself, some of the code will be common to all threads, so it goes into the base class, and the user-specific work for this thread will go into a derived class. This is one of the possible implementations. It's not the only one, and it's slightly different from what std thread provides. So I'll just show you a different way to do threads. So the interface will have two parts. There will be public interface. This is for the callers. Construct a thread, destroy thread, start and join. And there will be the interface for actual implementers of the particular thread, which is protected. Let's begin with the interface. Here is a little thread class that I wrote. Ended up being not so little after all the performance-related things were put into it. The standard implementation just does a reasonable work on all of these options. In your specific case, if you need extreme performance, you may want to tweak them in some way. So here is how you would use this class. You inherit your specific class from the thread class, and you implement the protected virtual function run where you put all the work. In your own code, you construct it, you may change options, and then you start the thread to make it run, you join the thread to join it. Why don't we start the thread in the constructor? Well, in the constructor of your own myThread class, you may start a thread. In the constructor of the base class, we can't, because remember that after the constructor of the base class is done, that's when the constructor of the derived class continues its work. But as soon as you start the thread, the virtual run function can begin to execute. So if we put start function into the constructor, thread may start to run before the object finishes constructing. And that's not good because run is a member of that object. It shouldn't begin executing on an object that is not yet constructed. We have some options for this thread. Joinable is the thread on which you need to call join. This is the default. Sometimes you just want to fire off a thread and let it run and let it exit and never worry about it again. So you can make a non-joinable thread. Here is an interesting performance-related option. Threads have, as we discussed, all the state necessary for execution, including stack. How much stack? Well, if it doesn't have enough, your program will run out of stack. If it has a lot, you're using a lot of memory if you create many threads. So if you create a lot of threads, you may want to optimize the stack size. Stack offsets, they affect performance. If you have a lot of threads, you may want to have the stacks of them spaced differently to avoid basically trashing the cache. This is something you may want to experiment with on your specific hardware. There is really no good way to fine-tune this option other than empirically. Guard regions around the stack, this just protects from thread overwriting the stack, exceeding the stack size. So this is our constructor, destructor, start the thread and join the thread. Thread cancellation is a delicate subject. Usually it's best to avoid it. The behavior is seldom defined if you actually cancel threads, but here is where the actual work is done. pure virtual declared in the base class, which means derived classes must provide a concrete implementation of this function, and that's where the work will be. The virtual function as a member function has access to whatever data you put into the derived class, so that's how we communicate data into the thread. The code wouldn't be much good if we didn't test its correctness. So in this class, we're using the Google test framework for testing. If you were to do your own implementation of the threads, you would need a good deal more tests to have good coverage than what I have here. But here is your basic test for the threads. You can start the threads, join a thread, expect that it ran, check the thread ID, and so on. This isn't exhaustive test coverage, but this is an example of how the tests would be set up. Let's take a moment to explore the control flow in a thread because it's a little different from the way classes are executed normally, so it's important to understand this. The object is constructed on what's sometimes called the main thread or the master thread. Basically, this is the thread which you have when you start running this code. The derived class is constructed with the construction begins, of course, with the base class. Then the main thread calls start. At this point, the main thread continues doing other work. The call to start returns almost immediately, but the member function run starts running on another thread. And this will continue until the main thread calls join, at which point the main thread may block if run isn't done yet. And after join returns, the destructor can be called, derived class, and then the base class. So this is the control flow. What do we do now that we have threads? Well, conceptually very simple. You have task. That's some code to run and some data to run it on. You create a thread to run this code. You create threads for all your other independent tasks. Fire them up. When you need the results of one of these tasks, you join that thread. If it's not done, you have to wait. If it's done, join will return immediately. Remember that hybrid end-to-end threading model? That's really why they did it. It was an attempt to give the user that abstraction as kind of the view of the real life. It mostly failed because it didn't quite work well in almost all implementations. So what does work in your actual threading model? What works in the operating system that you have? To see how it works and what it doesn't, we actually have to start running some benchmarks. This is all about performance, and remember the rule about performance, never guess about performance. If I'm telling you that it doesn't work to just create a bunch of threads, one for each task, the first thing you should ask me, why not? And what would happen if you did it anyway? That's what I'm going to do. I'm going to create a bunch of thread objects. Here they are, all derived from the base thread class, and they take some data in the derived class. Specifically, what do? Well, they take a pointer to this array here, and they simply increment elements of the array within their own range. So I have this big array, and I want to just increment every element many times, but I'm going to do it on several threads, so I'll partition the array between the threads. These are totally independent tasks. There is no synchronization, there is no logs here, there is no interaction between the threads, so this is a very simple case of concurrency. I just basically need to increment these elements in the array, and I'm using as many threads as I have to do it, and let's see how well it works on one or more threads. This is the number of threads, so I'll do it on threads 2 and so on, and a lot of threads. One thread over the entire array, 2 threads, faster, so half of an array each. 4 threads, even faster. 8 threads, slower. 512 threads, really slow. The simple attempt of partitioning and giving each thread just a task to do evidently did not work beyond a very simple number of threads. So if you have just 2 tasks or 4 tasks, yeah, go ahead, create 4 threads and be done with it. If you have a lot of tasks that you need eventually done, you can't create just 512 threads, fire them all up, and expect all your tasks to be done faster. Let's see what would happen if we made the tasks smaller. I'll make a smaller array, which means now for each thread there is less of an array to process. It'll recompile. Well, it went, of course, faster on a single thread because I had a lot less of an array, but now it just became slower immediately. Less work, smaller tasks. It became faster on fewer threads, but then it actually about the same. So this kind of suggests to us that there is an overhead, non-trivial overhead, in starting threads. If that's our hypothesis, we have to prove it. We have to, again, measure the performance impact of starting and stopping threads. Well, that's easy to do. We have the benchmark. This time, our work function will be a no work function. We're not doing anything. Going to just start thread, have it do absolutely nothing, and immediately return. And I'm going to benchmark now 3 different ways of doing threads. This is the raw access to pthreads. On this Linux machine, this is what the threads are. Create a thread, join a thread. This is the same thing wrapped inside my thread class. And so here I'm going to construct it. This time I put start colon the constructor, join colon the destructor, and the run does absolutely nothing. Again, no work. And this is the C++11 thread here. I have another function that also does no work. And this is how you create a C++11 thread. It starts immediately, but you have to join it. So this now measures how long it takes to start and join a thread. And you see that basically there is almost no difference between 3 different ways. So it's all about just starting actual thread. The extras that I added in my thread or that C++11 added in their threads are insignificant, but it takes almost 9 microseconds of real time for a thread to start and stop. And there is more CPU time being used, of course, because the thread actually is running and there is some work going on the thread, even if you haven't asked it to do any work, just initializing the thread that is running. If a task that you have takes less than, on this system, 9 microseconds to do, it's not worth starting a thread for. So that's why when you have a lot of tasks, you can't just fire off a bunch of threads because your tasks are small enough. The overhead of creating those threads overwhelms everything else. So threads are fairly expensive to start and join, which means your application must somehow reuse existing threads instead of starting new ones all the time. I said application, but I omitted a very important possible exception. You may have a library that does it for you. From the point of view of operating system versus program, doesn't make any difference. It's all part of the program. From your point of view, it makes all the difference in the world. You don't have to write it. If you have a good threading library, and there are several out there, you may not have to write this code. But if you're tuning performance, you'd have to at least understand what's going on. So that's what we're dealing with in this class, even if you don't end up writing it. I want to give you the understanding of how it works and why it's sometimes fast and sometimes not. Basically, the rest of this entire class will be dealing with, at least as much as we're dealing with concurrency, we'll be dealing with this reuse of threads, how to make tasks execute on threads as inexpensive as possible. But that'll be later. Now let's take a break and we'll come back, continue our work on threads. Welcome back to our lesson on threads. And we finally reached the moment where we learn about the bane of concurrency, the nightmare of multi-threaded programming, the curse of the threads. Yes, data races. Before you can avoid them, you have to experience them. We're going to do something very simple. We have a number that we're going to increment multiple times, and we're going to distribute this work between the threads. So we now have, let's say, 2 threads, and we have 2 times that we want to increment. So we are going to run these increments in parallel. In our actual benchmark, we have more than 2 increments and more than 2 threads, but the illustration gives you the idea. Let's measure how well it works. We're going to do a benchmark. This is just how many times we want to increment, but we're going to start here certain number of threads, and we can control how many threads from the benchmark fixture argument, 1, 2, 4, so on. Well, we already saw on this machine not to create more than 4 threads. It's not going to run any faster. So we fire up all the threads, and each of them will do its share of the increments. But totally we want to increment it this many times, but we divide the work between all threads. And all of our threads, here is the work, they're all incrementing this number. Volatile, very important for benchmarks. The compiler is pretty smart about these things. It sees that I'm incrementing the same number over and over. It'll figure out some optimization. I don't want it to figure out any optimization. I actually want to have this many increments. So I declare it volatile. Compiles, that's good. Runs, that's even better. Our n increments on one thread takes this much time. On two threads, each one doing half as many increments, takes half as much time. The same CPU time, but half of the real time. 4 threads, again, only half of the real time of 2 threads, the same CPU time. Our multi-threaded summation really works. To get an even better measurement, I went to a large machine where I could run 128 threads, and I measure it nanosecond per computation, so per adding, but on all threads. So it takes the same work that I can do 5 nanosecond on one thread. On that machine, didn't scale perfectly, so 4 on 2 threads and so on. It does get faster. So yes, it does scale, but we forgot the first question to ask. Even before the first question about performance, there is the very first question that we have to ask. Before we ask, does it scale? We have to ask, is it correct? Unfortunately, it's not. If you run it yourself, don't expect to reproduce these results exactly. You should get the same number for one thread if you do as many additions as I did in this test, but for 2 and more, you can get pretty much anything. It does something very fast, but it doesn't really do what we want. Why? This is what actually happens, or it's one of the many terrible things that could actually happen. We're doing 2 increments on 2 threads. The first thread and the other thread, they must all read the number, add 1 or increment, and then write the result back. Let's say it happens in this order. So they both read 0, they add 1 to their local copy, and then they write the result back. They both have 1 to write. One of these writes will be done last, and this 1 is what ends up as the result. So this is one of the possible ways it could go wrong. There are others. The point is, this is not correct. This has no chance of being correct. Concurrency is just one thing before, after, or at the same time as another. And what we have just experienced is a data race. So the problem of all data races is essentially the same. 2 or more threads modify shared data, and what do I mean by shared data? Same location in memory at the same time. So in order to have data races, you must have many threads and shared data. At least 2 of these threads access the same memory location at the same time. The general rule of avoiding data races, of correctness of multi-threaded programs, all accesses to the shared data must be done under the lock. On a pthread system, we have pthread mutex lock and unlock functions, which you can call to put a lock around your access to shared data. What's access to shared data? Well, that's that increment. Sum is the shared data. All threads access that region of memory, so operation on the shared data is the increment. In your actual code, please never use the lock directly. If somebody returns from the middle of the locked section or throws an exception there, you will leave the lock locked forever. Use objects, which provide the guarantee that every lock is unlocked. In C++11 or any other object-oriented language, it's known as resource acquisition is initialization, RAII, where in this view, locks are just resources that are acquired and released. I told you before that C++11 provides us with threads. Wouldn't do as much good if it didn't also provide us with locks. And indeed it does. It does have a mutex object, which is an object on which you can call lock and unlock. But you don't want to lock and unlock yourself. You want to use this lock guard, which is also provided to you by C++11. So here is an example. We want to lock this print function. We create a lock guard, and everything within the scope, while this lock guard object exists, everything is locked. So when does it unlock? Well, when the object is deleted, when it leaves the scope, right here. This way, if this throws an exception, the lock is unlocked anyway. If there was a return here, the lock would be unlocked anyway. And you can't forget it, because it hooked up to the destructor of this lock guard. If you wanted to write locking object yourself, you would still use this idea. You would construct an object which would hold a lock as a resource, and when it's destroyed, the lock is released. Before we continue into fixing our data races, something important to understand. It's kind of a general observation, but there is some confusion around it that I want to make sure I dispel. You cannot program with threads if your compiler doesn't support it. You can immediately ask me, but before C++11, the compiler did not support it. Well, that's actually not true. The compiler supported it. It just didn't support it according to the C++ standard. Why? Well, let me show you why. Let's say here is your original code. And the important part to look at here is these mutex lock and unlock calls around the increment, the addition here. Mutex lock, mutex unlock. I did them explicitly. I did what I told you to never do, but I have to do it this way to show you where the actual calls are. Take a look at it from the point of view of the compiler. So you're the compiler, you look at it, and you see mutex lock operates only on this lock data. And mutex unlock operates only on this lock data. Most importantly, none of them operates on anything that the loop changes. As a good optimizing compiler, you should optimize this code. And the optimized code should look like this. Hoisting common subexpressions out of the loop is one of the most basic optimizations all compilers do. Wouldn't you hate it if your compiler did this actually? And why not? Well, why not? Because the compiler actually knows something about the possibility of locks. It doesn't know specifically about these functions by name. Well, it may, but the functions may be hidden inside some other functions. So knowing them by name doesn't help. But it knows that a function that may have a side effect of locking and unlocking a lock, and that shouldn't be moved. And that's part of the compiler complying with standards beyond just the C++ standard. In this case, it's a POSIX standard. It has to disallow certain optimizations precisely because it can't know for sure that you're not locking and unlocking something. In addition to that, not only it can't hoist it out of the loop, it can't actually reorder it within the loop. So you could declare the lock volatile, which would require the compiler to preserve writes and reads. So let's say locks and unlocks cannot be now reordered and cannot be eliminated, but they can still be reordered with respect to other code that doesn't operate on locks. You wouldn't want that optimization either. So again, as a part of complying with both C++ and POSIX standard, your compiler knows not to do this. But now you see why, if your compiler was completely unaware of threads, you wouldn't be able to do the first thing with concurrency. Okay, now we know how to do the increments right. The only thing that was missing in our previous program is this lock and unlock. Now, again, in your actual program, you don't do this. I want to just be fully transparent. I want to show you that nothing other than this is going on in this benchmark. As we have seen before, wrapping pthread calls into object-oriented interface doesn't actually incur significant overhead, so you always want to do this in the interest of full transparency. There is no magic here. This is all that is going on. In addition to the increment, I have added lock and unlock. Wow, that's very different numbers. It's a lot slower. Is it at least correct? I went back to that same large machine and I ran this same test. Yes, the results are correct, and they're also very slow. Without lock on one thread, on that machine, it was 5 nanoseconds per increment. With lock, still on one thread, 21 nanoseconds per increment. I'm already behind. It only gets worse when I use more threads. Well, it's correct, which is good, but it doesn't scale at all. Still, you want correct results. Data races must be avoided at any cost. The rest of this whole course is actually about having your cake and eating it too. Getting correct results and getting them fast. Everything else from this point forward will be essentially about how to solve this problem that we have just seen. Data races must be avoided in order to have correct results. Data races are very expensive to avoid in a concurrent program. So from now on, everything will be about that, ultimately. Won't be a straight path. There will be a lot of interesting detours, but it will all be about how to get correct results quickly. That's what performance is. Before I leave you with that, A bit of independent study. I've shown you C++11 style object-oriented locking. You can put this lock guard object into a scope and protect the access to shared data. This is what some people call magic style locking. Instead of creating the lock guard in the scope, you have this construct. Locked of this mutex, and here is your code. The question, how is it done? Try to figure it out by yourself. You have time before the next lesson. In this class, we will begin considering the interaction of concurrency, specifically the threading, and the memory. This is a very important subject. First of all, concurrency, one of the key tools of high-performance computing. If you're dealing with HPC, sooner or later you will come to rely heavily on concurrency. Of course, we assume that you have already chosen the best algorithm and optimized single-threaded or single-core performance of your code. There are many forms of concurrency, but by far the most commonly used means multithreading. On shared memory systems, multiprocessor, multi-core systems, really concurrency means threads. And multithreaded programs interact with memory in several unique ways. Let's begin by reviewing the architecture of the memory system. On a multi-core system or a multiprocessor system, you have multiple CPUs. Each of them have their own caches. Some of the caches are shared, and underneath all of the caches is the shared main memory. The caches that are CPU specific have to maintain coherency of the data. Somehow all CPUs have to see the same values for the same memory addresses. The caches and the memory that are shared between CPU have their own set of problems. They have to do arbitration, which is when two CPUs access the same location at the same time, something has to happen, somebody has to go first, and that's the arbitration. Obviously, two CPUs at the same time or multiple CPUs using multiple caches means that we have several threads running on several CPUs at the same time. So that's why when you have multithreading and a shared memory system, you have this unique set of issues. The first one is actually very simple. We'll just go through with it to make sure we cover it. If you have one CPU, you get so much memory bandwidth. If you run multiple threads on multiple CPUs, all of these CPUs can saturate memory bandwidth that much faster. This is the plot I obtained on a multi-core system that shows the aggregate memory bandwidth between several CPUs. And in this plot, you can see that once you hit the main memory, outside of all caches, that's this area on the right, when you go from one thread to two, you pretty much double your memory bandwidth. When you go from two thread to four, the memory bandwidth has been saturated. That has very little to do with concurrency itself. It's just multiple threads, which is what you have in concurrent programs, are more likely to suffer from memory bandwidth constraints. Okay, that's good to know, but that's not really the interesting part. The really complex part of memory and concurrency interaction comes when we start dealing with data races. Throughout this class, we will be considering this model problem, concurrent accumulation. Accumulation just means summation, although it doesn't have to be addition, could be multiplication, just a general form of accumulation. In this case, we'll be using summation. So we have a value, and we're going to be adding to this value on several threads, NT of threads. Each thread will do n over NT additions. This is a model problem, but ask the stupid question, get the stupid answer. Is this problem oversimplified? After all, we know the answer to this problem. We don't have to run the summations. Here is a possible real problem where we don't just add one, we compute a new value, which we don't know upfront every time, and we add that. This is a general case of accumulation. It's a very common computational problem. This looks pretty real. Our model problem just avoids the compute value. It doesn't really matter what you add, one or not, the cost is basically the same. Another example is if maybe we're always adding one, but we don't know when exactly we're adding one. We're counting some events, or we're counting something we found, for example, substring matches in a string, anything really, and maybe we just count how many of these events we have found, or we're running until we found an event. Either way, this is again a very common numeric problem. Now, our model problem models the concurrent accumulation part really well. It just doesn't have all the extra computations like the compute value or check for event. So in a sense, it may be the worst case stress test where we're just hammering this parallel sum at maximum speed without any additional computations that are not related to parallel summation. To remind ourselves, what is the data race? How does data race work? Well, we're going to be adding values on multiple threads. So adding means you read the value, add one, write the value back. So here is a data race. Both threads read the value, they get 0. Both threads add 1, they both get 1. And when they write the value back, you're going to get 1. You expected 2. That's the data race. There is a general rule about avoiding data races. All accesses to shared data must be protected by locks. All accesses. A lot of people say that my program accesses the shared value here and then much later there. I don't need to protect it. You may be able to get away with it sometime or even most of the time, but the program is undefined. All accesses must be protected by locks. The definition of same time is actually pretty loose in concurrent programs, so don't count on it. Now, how expensive is it to guard all accesses to shared data by locks? Let's find out. That's what microbenchmarks are for. And this time we will be using Google Benchmarks for multi-threaded benchmarking. Google Benchmark has that capability. It's somewhat limited, but good enough for what we need to do. So let's see what we're benchmarking. This is our benchmark fixture right here. We will be doing n times this calculation. Now, we don't want to benchmark the loop itself, so we have the manual unrolling of the loop. This repeat macro just repeats the content 32 times in our case, which means, of course, that the whole thing is 32 times n. N is just arbitrarily chosen, so it doesn't matter what it is. Just chosen for some reasonable runtime of the benchmark. We're passing threads n argument to the benchmark right here. And when we do that, we don't want to initialize x on all threads. That would be a race condition in itself. There is a thread index being passed in, so thread number 0 initializes x. Google Benchmarks does provide a very important guarantee that basically all threads will cross this at the same time. There is a barrier in there, so the content of the benchmark begins on all threads at the same time. And this is our global shared variable x that we're going to be incrementing. Now, this benchmark actually runs with a race condition, so there is no protection here at all. So we're just kind of measuring the baseline here. Compiles, runs. So this is how long it takes to do however many additions we're doing on one thread, about half that time on 2, a little less than 2x scaling on 4. On 8, not so good, but this machine doesn't actually have 8 real cores. It only has 4 real cores and 4 hypercores, so kind of don't know what to expect from 8 threads. And in any case, it's a race condition, so really you can expect anything here. But this gives us kind of a ballpark number of what to look for. Now the same thing, but done correctly. And all of our accesses to the shared data here are protected by a mutex. This time I'm using C++11 mutex. It's an std mutex here. Instead of locking and unlocking it manually, I'm using a C++11 lock guard, which locks in the constructor, unlocks in the destructor, which you don't see here, but happens right here at the curly brace. Otherwise, it's exactly the same code. The old numbers are still on screen, so let's see. Well, it takes about 10 times longer on one thread, so evidently the cost of locking and unlocking a mutex is about 10 times the cost of just incrementing a variable. Now remember, on one thread, everything is good. We don't have any race conditions when only one thread is running, so this number is a real number. This is how long it takes to do the additions. On 2 threads, it actually takes longer than on 1. And on 4 threads, it takes even longer, and so on. It gets worse on 8 threads. Our concurrent program, even though each thread only does 1/2 or 1/4 of all additions, doesn't scale at all. This is real time. Takes longer to do half of additions on 2 threads than all of the additions on 1 thread. Quite a lot longer. Yeah, we avoided the race condition, but at a very considerable cost. As we have seen, logs can be really expensive. There is a note of caution here. We have been comparing a program with a race condition to a correct program in terms of performance. A race condition introduces undefined behavior, so strictly speaking, it's a flawed comparison. At the low level, we can still ask, how long does it take to run an instruction of add? That answer makes sense. The results don't, but the instruction of add, if you want to run it and you want to ask how long it takes to run it, there is an answer to that, and we found out. Our conclusion about logs being very expensive, that conclusion holds. We have learned so far that on one hand, sharing data between threads leads to data races which must be avoided. On the other hand, avoiding data races greatly reduces performance, at least if you're avoiding it by logs. So we now have a bit of a contradiction on hand. All accesses to shared data must be done under the log. That's the main rule of avoiding data races. The rest of the class, not just this class, but basically everything forward, pretty much is about teaching you how to break this rule. In general, we have 3 options. Option 1, you have less shared data. Remember, race conditions only happen if you have shared data. If you don't have shared data, you don't have data races, you don't have to avoid them, you don't have the cost of avoiding data races. Option 2, well, we have tried std mutex and we discovered that it's pretty slow. It's not the only lock in the world. Maybe we can invent a faster lock. Option 3, maybe we can break the rule about guarding shared data accesses under locks and still have a correct program. Well, let's start with the first option. For our multi-threaded accumulation, we actually do have a very simple way of avoiding data sharing, at least most of the data sharing. We can take advantage of the fact that we don't have to add to the global sum here every time. We can compute the sum of the values that the thread is adding on each thread and accumulate them in a local sum per thread. That is not a shared variable. It's one of each per thread. Now, there is no log and there is no race condition here because this addition is using local data, not shared data. Of course, eventually we need the global sum, so when all of the additions are done, we're going to take a log exactly once and add our local sum to the global sum. If the number of accumulations is large, the cost of this addition is going to be insignificant compared to the cost of actually all of the additions. Well, let's see how well this works. Otherwise, the code is exactly the same. Now, just to remind ourselves, what was the value for one thread for just regular additions? Here it is. Basically the same within the noise of the benchmark for one thread, half of the time for 2 threads, half for 4 threads, not quite half, but still faster for 8 threads. This rewrite of our code almost completely eliminated data sharing. We can say completely eliminated the one data sharing access per thread at the end of computation. Time-wise, it's irrelevant. This is so far our golden result, which is if you can completely eliminate all data sharing, your concurrent program will run a lot faster. And it will be correct because you actually don't have data races. So while avoiding data races can reduce performance, avoiding shared data in the first place greatly improves performance. Unfortunately, it's not always that easy to avoid shared data. For example, if we didn't just accumulate a sum, but we were actually counting events and we needed to know how many were globally counted, maybe we're looking for the first 10,000 events, or maybe finding the next event depends on how many were found before, we would actually need the global counter, and it would have to be updated every time. While it's a good note to remember and try to avoid shared data, that's kind of a cop-out. It's the easy case. We have to actually look really closely at the case when shared data is unavoidable and figure out how to deal with it better. And this will be the subject of our next class. In this class, our exploration of concurrency in memory continues with the study of the true cost of data sharing. This time, no cop-outs, no working around it. We'll actually have true shared data and measure how much it costs. Why didn't we already have that data? Well, because our benchmarks actually didn't measure the performance impact of shared data. It measured the performance impact of avoiding data races in one particular way by slapping mutexes around the shared data. What we have measured is the performance impact of logs. What's actually the performance impact of data sharing itself? To measure this, we somehow need to construct correct accesses without shared data, but without logs. Logs probably have their own shared data inside, at least that's the most common way to do them, so we're not really measuring just the cost of shared increment, for example, in our model when we're using logs. So how are we going to go about it? Again, let's look at the memory architecture chart. We need to measure the cost for the CPU of getting all the way through the caches to that shared global variable, paying whatever the cost of cache coherency, moving this variable up and down the caches as necessary, arbitrating the concurrent accesses. All of that adds up to the cost of shared data. But we need to do that without actually doing logs, because logs don't actually force us to measure how much it costs to access the shared data. They just make the accesses to shared data not at the same time. First one, then the other. In order to do that, we have to use what's called atomic operations, atomic memory accesses. This is a hardware feature, and most CPUs today have it. All multi-core shared memory CPUs must have some form of it. It's hardware dependent. Typically, you would find load store, some arithmetic instructions like add, maybe conditionals. It varies from hardware to hardware. The operations that you do have all have that feature. They enforce cache coherency, and they also enforce that the atomic operations, that's why they're called atomic. The entire operation is non-interruptible, happens in a single transaction. For example, atomic increment. If one CPU increments x from 1 to 2, and that CPU really got x when x was 1, then no other CPU will see 1. If other CPU tries to do atomic increment, it either happens before, and so that CPU did 0 to 1, or it will happen after, and that CPU will see 2 to 3 increment. So the entire increment, which is reading, adding, and writing, happens as a single, non-interruptible atomic transaction. How are we going to go about getting our hands on those atomic transactions? Well, if you have access to a C++11 compiler and you can use it, your life is really easy. You can wrap std atomic template around not quite any data, but we're doing integer addition, so any integer will do. There are other things you can put inside atomic. We're not concerned with that right now. We'll deal with that later. In order to create an atomic integer, all you need to do is say std atomic of long, let's say, starts with 0, and this is of course pseudocode. This isn't like really C++. On one thread, you're going to do ++x, and on another thread, you're also going to do ++x. Now, ++ on an atomic integer is guaranteed to be atomic. That's what std atomic guarantees. If you do this, somehow run ++x on one thread and ++x on another thread, you're guaranteed to have 2. This atomic uses some hardware instructions, whatever compiler has to emit in order to guarantee this, it'll do, but it guarantees avoiding races. If you don't have C++11, but you have older C++ compilers, there is no portable way to do it. Here is how you do it on GCC or any other compiler that supports inline assembler on x86. This is x86 specific. This is the atomic instruction itself. Lock, xadd, q just for the quad word, 8 bytes. So this is the atomic add instruction. The rest is GCC syntax for wrapping inline assembler into a function. So if you call this function, it does atomic increment. It actually emits basically the same code as the C++11 stuff. Okay, so now that we know how to do atomic increment, let's compare the cost of data sharing to the cost of non-shared data. For the baseline, we can use the time it takes to access the local data. So this is how long it takes on one thread, and it scales on 2 and 4 threads pretty much perfectly. On 8 threads, not so much, because as I said, I don't really have 8 cores on this machine. So what I will be comparing with, well, let me actually bring up the other one so you see what I'm comparing. So as you can see, the code is exactly the same, just plus plus x. The only difference is how x is declared. So before it was unsigned long, now it's an atomic unsigned long. Everything else is exactly the same. Okay, now we're getting somewhere. First of all, it takes longer on one thread, so evidently atomic increment is slower than non-atomic increment. Now, it still takes longer on 2 threads than on 1, and a little faster on 4 threads. But remember what it was with locks. So this was on 1 thread. Now it's about 3 times faster on 1 thread. And it became really slow on 2 threads with locks. With atomics, it's slower. It's not quite as bad. So there is a significant cost to data sharing, but not nearly as large as the cost of locks. Okay, so now we have measured the actual cost of accessing a shared variable, correctly accessing the shared variable and using atomic instructions, and we discovered that there is significant cost to it. It's not the cost of locks. So yeah, locks are expensive, but forget the locks. Without locks, just accessing a global variable atomically, there is significant cost to it. So this is it for the cost of data sharing, but there is actually a lot more to data sharing that we're going to learn in the next class. Let's continue the research in our concurrency and memory interactions with some more in-depth exploration of data sharing and its cost. I have to tell you the truth, if you haven't noticed it already, our benchmark of data sharing was correct in what we measured, but it wasn't really accurate in the sense that what we did was we compared atomic increment of a shared variable and a non-atomic increment of a local variable. We also tried non-atomic increment of a shared variable, but who knows what's going on there? It's undefined behavior. You should be skeptical to your benchmarks. You shouldn't assume that basically other things you vary, that they don't matter. So what if it's not the data sharing that costs? What if atomic increment is just an expensive operation in and of itself? We can find that out with another benchmark. So what we should do is we should compare the exact same operation on shared and non-shared data. Since only atomic increment works on both, it has to be atomic increment. Back to the benchmarks we go. Here we still have on screen our atomic increments. Now we're going to make one slight change. You can actually have multiple fixtures in benchmark, so this time I put both of them in just to show you how you can do it so you can compare two things together, just have the baseline. So atomic benchmark fixture does the atomic increment. How do we know that this is atomic? Well, because X is atomic on a global shared variable. Another one, atomic 1, does also atomic increment on a local variable. This will be 1 per thread, so there is no sharing here. Now, this will tell us the actual cost of data sharing. Atomic, remember, this is the data sharing. If the numbers are slightly different, there is some noise in the benchmarks. To get more accurate numbers, you have to ask the benchmark to run longer. It has some parameters for that. But that's not what we're looking here. This is what we're after. 1 thread, shared variable, 1 thread, local variable. In this case, for 1 thread doesn't make any difference. So there is some noise here, but 2 threads, shared variable, 2 threads, local variable. For 2 threads, it's twice as fast. Makes sense. There is absolutely no interaction between these 2 threads. They just each have to do half as much work. These results for atomic accesses to local variables make sense. Every time you double the number of threads, it runs twice as fast because you have half as much work to do on each thread. So from 2 to 4, same thing. Whereas shared variable not only doesn't run twice as fast, it actually runs quite a lot slower. So now we can say, finally, this is the cost of data sharing. So without data sharing, for exact same instruction, atomic increment takes this long. With data sharing, same instruction takes that long. So we have learned that accessing shared data is indeed really much, much slower. remember, you have to be skeptical toward your benchmark. So there is still this nagging bit of doubt. What if there is a difference between global data and local data, the one I declared inside the function? We can put that doubt to rest by running yet another benchmark on global but not shared data. We can just have 2 or 4 global variables not shared between the threads. To construct such a benchmark, we need to have global, not shared data. We could just go x1, x2, but it's not convenient to do with multiple threads, so let's just create an array. We have the thread index here. Each thread will get a different element in the array. Now, we can conveniently combine shared and non-shared tests in one benchmark, so we can run them both together by passing this argument here. If the argument is 0, then all threads are hitting the same position 0 in the array, so it's shared. If the argument is 1, then thread index starts with 0, so they're using elements number 0, 1, 2, 3, and so on. This way, in one fixture, we will easily test accesses to global shared versus global not shared data. This is not quite what we expected. These are still on screen, our tests for one thread is all the same time, but global shared versus local not shared. And here, global shared versus global not shared. Basically, there is pretty much no difference between shared and non-shared when we're dealing with global data. Unless there is something special about adjacent data. Well, let's be thorough in our benchmarking and consider the case of not adjacent global data. We actually have it pretty much ready to go. Remember that we're multiplying thread index by this multiplier. We were using just 0 and 1 to make shared and not shared. But if we pass larger numbers, and I'm going to try 2 and some large number like 8, then we will be using elements of the array that are not adjacent. So the first element is always 0. The second is 1 times this argument, so could be 8, and then it's 16, and so on. So we're still using that global array. We're just spacing apart the non-shared variables. This time we have more to run. This is our shared accesses. Offset 0, so they're all hitting the same element 0. We have already seen offset 1, no change. Pretty much the same for offset 2, which is accessing every other element in the array. But significant difference at offset 8. Same value for one thread we expected, that's still hitting element 0 of the array. But for 2 threads, it's basically twice as fast, which is the same as what we saw when we were using thread local variables, the ones on the stack in each thread. Again, twice as fast for 4 threads. Now, clearly something happened between 0, 1, 2 that behave more or less the same. All behave as if we were doing shared data access, and this number 8, which behaves very differently, but we can't draw conclusions from just one number. So this is the exact same benchmark. We're accessing elements of this array separated by thread index times this offset. But we're now going to always run just 2 threads. 2 threads gave us clear enough difference between shared and non-shared, and we'll scan the range of values of the offset between what first thread and the second thread accesses from 0. This is sharing. This is our 8. Now, this is 8th element of the array, so 0th element and 8th element. And we'll go, let's say, to 20. 0th and 20th element, far enough apart. About the same time for 2 threads accessing shared and adjacent data. Here is where it changes. We got lucky with 8 last time. After 8, really nothing changes, so something happens between accessing elements 0 and 7 versus accessing elements 0 and 8. Perhaps it would help to see a graph of this. Here is our offset. I converted array elements to bytes, and the time relative to the time it takes to access truly shared element, both threads accessing element 0 of the array. When we talk about offsets, remember that each variable takes 8 bytes. So 64 bytes from the beginning of the first variable, the one thread 0 accesses, to the beginning of the second variable, the one thread 1 accesses. 64 bytes from one variable to the next, they're all 8 bytes in size. So in between them, there is something else, something strange. So what's in between these 0 and 64 bytes, and what is the significance of the 64 bytes? To understand this, we have to go even deeper into the memory system. We think of memory as it's organized in words. Now, words can be 4 bytes or 8 bytes. That's what CPU instructions operate on. Add a word, load or store a word. Well, that's what CPU works on, but that's not actually what caches work on. Cache transactions operate on something called cache lines. They are larger. There are multiple words. On x86, they are 64 bytes. So there are 8-byte words. The important part is that caches can only operate on lines. So if the CPU needs one word or even 1 byte, the entire line containing this word is loaded into cache, not 64 bytes starting from this word. The lines are starting from address 0 in 64-byte increments, so whatever line your word falls into, that line is getting loaded. Same thing if we need to send one word to memory, that whole line is getting flushed. Of course, it doesn't mean that adjacent words are getting overwritten. There is some special hardware that reconciles lines coming from different caches and picks the right bytes and writes it into memory, but that all has a cost. That's actually where the cost of cache coherency comes from, figuring out whose bytes take precedence over other bytes. If you have two separate words or two separate bytes on the same cache line, if one CPU acts on the first word, it gets the whole cache line loaded. If the other CPU acts on the second word, that same cache line is loaded into that cache. Now, when they're sending their cache lines back to memory, it's actually the same cache line. So even though the words are different, reconciliation of the content of the two cache lines still has to happen pretty much exactly in the same way as if it was the same word. So two words on the same cache line are effectively shared, even though they're not technically shared, they're not the same word. This is known as false sharing. False sharing has, as we have seen, basically exact same cost as real sharing in terms of performance. At least with atomic operations, accessing shared data or accessing data on the same cache line is much slower than accessing data that is not shared and not falsely shared on separate cache lines. By the way, 64 bytes is enough separation. You don't get anything else by spreading them any further. Now, that's on x86. Other CPUs may have different length of cache lines. But once you go outside of the cache line, to adjacent cache lines or to very distant cache lines, same thing. To be complete in our exploration of the cost of the false sharing, we can ask just one more question. Since false sharing isn't really sharing, we don't have to use atomic operations on data that is falsely shared. There is no race condition there. Remember, false sharing is not about creating a race condition when you don't expect one. There is no race condition there. Your program is correct. It's just the same operations for some reason are suddenly taking longer, and nothing in your code shows you why they would be taking longer. That's how false sharing manifests itself. If we know that we don't have a real sharing, we only may have false sharing, we don't have to use atomic operations. So one last thing to measure is, does false sharing exist with non-atomic operations? That's easy to do. We can construct the same test as we had before, only this time we're going back to an array of plain integers, not atomic ones. And the same thing we're using to access different elements of this array, offset times the thread index. If we do pass 0 as the offset, we will be accessing the same element of the array, which is a race condition. So that's something you shouldn't do in any program you care about correctness. But for any offset other than 0, and we will again try 1, 2, and 8, you don't have data sharing, the program is correct. You may have false sharing, and we're going to find out if it costs us anything. For 0 offset, this is the only number you should be looking at. This is the baseline, the cost of doing all these additions, however many we specified in the program, on one thread. No data race, this is a good number. With offset 1 on one thread, with thread 1, makes no difference. What the offset is, we're hitting element 0. With offset 1 and 2 threads, well, doesn't look like we're being penalized by false sharing quite as bad. We go to 4 threads. Now, if you look at offset 8 here and compare it with, let's say, offset 1 here, you see that there is not a lot of cost to false sharing if you don't use atomic operations. If you have enough threads, there seems to be some. If I had more cores on this machine, that result would actually be more pronounced. But the bottom line is false sharing exists even with non-atomic operations. It's less pronounced, so you shouldn't be paranoid about it, but you should be mindful about it in general. The more of false sharing data you have, we have here only one variable. If you were doing a matrix multiplication and you arranged for 2 threads to always hit the same cache line while accessing elements of the matrix, this would be significantly worse. So false sharing exists. It's not as bad as if you have one piece of data being falsely shared in your program, your performance will go down the drain, but you have to be mindful about it. So what have we learned about the concurrency intersecting with memory? The trivial consideration is that multiple threads all accessing the same memory are more likely to saturate the memory bandwidth. The real focus is on data sharing. If you have shared data and you don't protect it, you get race conditions. If you have shared data and you do protect it, you can end up with significantly reduced performance, especially if you use locks. If you don't have shared data, on the other hand, you don't have race conditions, you don't have locks, you get great performance. Not always possible. Locks aside, there is a significant cost to actual data sharing. Accessing the same variable from multiple threads takes a lot longer than accessing different variables from multiple threads, especially if you do it correctly. What I mean by correctly, be aware of false sharing. Accessing adjacent variables from multiple threads can be just as slow as accessing the same variable. To avoid false sharing, you need to know the cache line size and cache line alignments. 2 variables that are on different cache lines have no sharing problems. 2 variables that are on the same cache line are falsely shared, and you shouldn't access them from the same thread if you can help it. In this class, we will begin to study locks. We will learn almost everything there is to know about locks. Before you ask, isn't it about high performance? So what do locks have to do with this? Everybody else is using locks, so can't possibly be the special high performance stuff. There is quite a lot of difference between locks and other locks. Some of them are very high performing, and in any case, before you can do better, you have to learn what you start from. So you have to learn how the locks work before you can improve on it. So let's start with the most common type of lock. Anybody who did any concurrent programming used this, the mutexes. Now, the purpose of any lock is avoiding data races, avoiding undefined behavior when multiple threads are accessing the same piece of data at the same time. Note that the definition of the same time is very loose. It doesn't have to be at the same clocked wall time. If 2 threads access the same data, there has to be some kind of synchronization, and locks are the simplest one. Otherwise, the program is undefined. Locks are just a particular implementation of synchronization. There are other ways. The key to not having undefined behavior with data races is that all shared data must be accessed in a way that 2 threads, or more than 2 threads, cannot access it at the same time in an unsafe manner. There are 2 parts to it: same time, which, as I said, is pretty loose, and unsafe manner. Locks attack the first option. They prevent accesses at the same time. We will come back to the second possibility later. The advantage of locks is they are common, well understood, easy to use, so let's look at what they are. The most common lock is the mutex. If you work on any Unix system, you have seen it. There is one in pthreads library. It's a pthread mutex, and there are 2 functions to lock and unlock it. In C++, prior to C++ 11, there was nothing at all about threads in the standard, so In practice, the compiler would combine C++ standard with POSIX standard usually, and the pthread mutex is what you would use. C++11 gives us a C++ standard mutex, and along with it a couple utilities to go with it, in particular the lockguard class. Here is the documentation for the C++11 mutex. I'm using c++.com, cppreference.com is another useful site for this. Mutex is what they call a lockable object. What this really means is it has two member functions, lock here and unlock. That's all it takes to be a basic lockable object. A lockable object also has try-lock. It doesn't have to be derived from any common base, it just has to have these three member functions, and then any other C++ function or class that works on lockable or basic lockable objects will work on your own class if you define these three member functions. What this does is locks and unlocks the mutex. We'll see an example in our own code, but they have an example here. So lock the mutex, do some computation. In particular, if you're actually printing something, you always want to lock it, otherwise multiple threads printing at the same time. At best, it will come out all interleaved and jumbled, could actually crash. And then when we're done, we unlock the mutex. As I said, you don't want to use lock and unlock directly in this manner if you can help it. The reason is, what if we have a return here, somewhere between these statements, let's say after this here? We would forget to unlock. And the solution to this is to use the lockguard, which is also part of the standard. Works on any basic lockable type, so needs lock and unlock member functions. Here it is. It's a template, works on any type you give it as long as it has lock and unlock. You need to give it your mutex, or in general the object of this type. When lockguard is constructed, at this point it calls lock. You don't see the call to unlock because it's hidden in the destructor of the lockguard object. So normally it would happen right here. If you have return or throw an exception, or if you were inside the loop and did a break, the object would still have to be destroyed. You're basically jumping to the end of the scope and exiting the scope. No matter how you do it, at the end of the scope, destructor of this lockguard fires, and you cannot forget to unlock the mutex. You should do the same with your own locks as well. So the advantages, as I said, you cannot forget to unlock, you cannot accidentally bypass the call to unlock, and you can always write your own class if your mutex does not have the lockable interface. For example, pthread mutex, unless you wrap it in a class, cannot have lock and unlock member functions. It's not a class. It's some standard pthread mutex t-type. It's a struct of some sort, C compatible. Then you just write your own guard class that locks in the constructor, unlocks in the destructor. So what exactly do the locks do? Let's say we have some shared data that is protected by the lock, and we want to access it from two threads. Both threads hum along, they do their own computation on non-shared data, then they come to the point where they want to access shared data. They do it correctly, they lock the lock first. So let's say thread 1 gets there first, it locks the lock. Now it has exclusive access to the shared data. It will continue working on the shared data until it calls unlock, and then it'll go do something else. The portion of the code between lock and unlock is called critical section. Thread 2 also wants to work on the shared data. It calls lock later, and at this point, lock is already taken, so thread 2 blocks. It has to wait until unlock is done on thread 1. At this point, only thread 2 can enter its own critical section. Could be the same code running on two threads, could be different code working on the same shared data. And thread 2 continues the critical section until it calls to unlock, and then it go work on something else. So you can see that the critical section never runs on two threads at the same time. This way we avoid the race condition and then define behavior. Not just mutexes, all locks work like this. This class is all about performance, so how much does it cost to have a lock? There are essentially two aspects to the cost. First of all, any kind of lock will make part of your program, specifically the critical section, run on one thread at a time. This, of course, reduces your speed up. Remember Amdahl's law, the speed up basically depends on the single-threaded portion of your program, P here. Essentially what it says is that if you have a program where part of it scales perfectly and running on n CPU, you get perfect speed up of n, and the other part doesn't scale at all, so you always get it running on one CPU, you can have the scalable part. Its runtime is divided by n, so it can be reduced, but the single-threaded part always stays the same, so that limits your total runtime. If you had infinite number of CPUs, you still wouldn't be able to run in less time than the single-threaded part. You may think, okay, my critical section is small, how bad can it be? It actually adds up if you have a lot of CPUs, and can be large. For example, let's say you have 128 CPUs, and only 1% of your program is a critical section. According to Amdahl's law, assuming perfect scaling outside of the critical section, your speed up is 56, about half of what you could expect from the number of CPUs, a little less. Furthermore, if you had a million CPUs and you had perfect scaling for the 99% of your program, the total runtime of your program would still be 1% of the single-threaded runtime, the critical section. You went to this heroic effort of acquiring a million CPUs and getting perfect scaling for 99% of your program, and you are rewarded with a speed up of just 100. That's a significant cost to any kind of single-threaded fragment of your program, be it a critical section or just a single-threaded portion between some threaded portions. In the context of our class today, the mutexes, we're interested in the critical section. That's unavoidable, does not depend on the mutex that you use. So the thing to remember is data sharing and critical sections in general, and usually you have a critical section when you have data sharing, costs more when you have a very large system. Effectively, the cost, the time of the critical section is multiplied by the number of CPUs. The second part of the cost of mutexes is the overhead added by the lock. In addition to the length of the critical section itself, which is how long it takes to compute whatever you're computing there, it takes some time to lock and unlock the lock. Also, the threads that are not in the critical section but are trying to get into it, that are trying to get the lock, they are trying to get the lock or doing whatever they're doing to get the lock, so they're probably spending some CPU time. That CPU time is taken away from other threads that are running, doing useful work, and maybe don't care about this lock. There are two kinds of overhead. Now, the answer to how much it costs is actually pretty complex and varied. It depends a lot on what kind of lock you're using. It also depends on the situation. It depends in particular on the what's called contention of the lock, how many threads are trying to get the lock at the same time. So you could ask, for example, how long does it take to take a lock if the lock is currently not locked and nobody else wants it? So we have just one thread, and that thread, just in case, is trying to take a lock. By sheer luck, nobody else happens to be near that critical section at the same time, but we don't know that, so we still have to take a lock. So how long does it take to take a lock when basically you're the only thread accessing it? You could ask another one. How long does it take to take a lock after you have been waiting? So you waited however long you have to wait. Now some other thread unlocked the lock. How long would it take for your thread to actually get that lock? These numbers could be very different. It depends on the implementation of the lock. In general, so the cost of the lock depends on how many threads are waiting. We could measure each step individually. For example, we could take a lock and measure how long it takes to lock it. We could lock it and measure how long it takes to lock it after we unlock it, and all these steps. The problem with such low-level measurements, it's hard to relate them to practice because the actual time in a real program that is added by the locks isn't like a simple sum or some other simple function of these individual times. They combine in strange ways. It depends on how long you wait, how many threads are waiting, how much CPU time is used by the locks and by other things that are going on at the same time. Even if you knew all these individual timings, you really wouldn't be able to conclude anything. So what's more useful in practice is the kind of overall throughput. I have a critical section, all my threads must get through it, it's protected by the lock. How long does it take to perform the computation protected by the lock on a given number of threads? Of course, it depends on how long it takes to do the computation, so basically the question is how much do we add to the cost of computation? Now that we can measure by writing a microbenchmark with some code operating on some shared data and wrapped in different kinds of locks. Let's have a short break now, and then we can see the code, run it, and do our measurements. Welcome back. Let's start right where we left off and run some measurements for the cost of the logs. Let's begin with our basic mutex and its benchmark. This is how we're going to construct the benchmark. We have a value, our computation will be very simple increment of the value, and we have a mutex. For a baseline, we're going to increment on one thread with no concurrency, so no logs. We're going to measure how long it takes to increment x. That's our baseline, and then we're going to run the log version of our benchmark on 1, 2, 4, so on threads, and inside, here's what we do. We acquire the mutex using the log guard, we increment x, and in the destructor of the log guard, we release the mutex. Compile and run this. The baseline, it takes 2 nanoseconds on this machine to increment a 64-bit integer. Incrementing the same 64-bit integer on one thread, but taking a log for no reason in this case, adds another 20 nanoseconds. So just locking and unlocking costs a lot more than simple integer increment. Now that makes sense. There's probably more computation than just adding 1 to an integer when you do lock and unlock. It gets worse on 2 threads now. We have lock contention and so on. Doesn't get a lot worse with more threads on this machine, goes up to 200 nanoseconds because I only have 4 real cores. So at this point, each thread runs on its own CPU. After that, they have to share the CPU, so you don't actually get all 16 threads hammering at the same lock at the same time. Still adds up sometime. Now, this is all real time. The interesting thing is that the CPU time for one thread, it's the same as the real time, but then you can see that it goes up. It goes up more than the real time. So the threads that are not computing, that are waiting, are actually using considerable CPU time, at least to get, we don't know where exactly, but at least to get a lock, to lock and unlock. While they're waiting, well, maybe they're also using CPU time. That depends on how the lock is implemented. There is something interesting about this code that I want to highlight to you, and that is, look at the placement of the shared data, x, and the mutex. They're declared right next to each other, which for most compilers would mean that they're laid out in memory right next to each other. That's a special case. In general, you don't get that unless you try. Well, does it matter? Let's remember something from the previous class. We did talk about false sharing before. False sharing has to do with the fact that while the CPU operates on individual words, like 64-bit words, caches operate on the whole 64-byte on lines, on x86 64 bytes, but usually they're bigger than individual word. What does it mean that cache operates on a line? It means that if I want to fetch 1 byte from memory to the cache and then to the CPU, I actually can't do that. Caches fetch the whole 64-byte line. We talked about it in the context of false sharing. If 2 CPUs operate on different, not shared, bytes, which happen to be on the same cache line, that cache line starts bouncing from one CPU to another, which makes it look like the data is shared, degrades performance. There is a flip side to that. If one CPU operates on 2 words that are on the same cache line, after you work on the first word, the cache line is already there. So the sharing of the second word is almost free, at least much cheaper. In our case, we have the data and the mutex occupying the same cache line. So does that somehow affect our measurement? Well, let's see. So what we need to do is put them in different places. For example, this may be more like real life. We still have the mutex here as a global variable. Well, okay, that's not like real life. Mutex wouldn't be as a global variable, but it's some memory that is different from data. And data is here. I'm actually getting it from the heap. In this code, you may notice that delete is missing. So I'm actually leaking this memory. Well, for this benchmark, I don't care. In any actual program, you would, of course, clean it up. Other than that, it's the same code. So I allocate the piece of data, I create a reference to this data so I can use exact same code like ++x, and it has the same log guard and the same ++x, so it's exact same other than data is in different places. Let's see if that made any difference. Not for one thread when there is no actual sharing, so it doesn't matter whether they're on the same cache line or not. Well, it made some difference. So for 2 threads, the time went from 62 nanoseconds to 91 when I prevented the sharing of the cache line between the data and the log. And it's a little larger after that. It's 195 versus 139. Okay, so if we want to model a situation where you have a mutex somewhere which isn't right next to the piece of data that you are protecting, maybe the piece of data is just large enough, could be some kind of list that is scattered in memory, so you can't have the mutex next to the data because the data isn't next to each other. So let's say that this is a better model of our real life situation. We're going to do this from now on, put mutex and data in different parts in memory. There is not a huge, but some difference between the two. Okay, so remember that this false sharing, it works both ways. If you have two independent shared variables, you don't want them on the same cache line, otherwise you make them shared even if they weren't actually shared between these two CPUs. One CPU was using one, the other one using the other, but they appear to be tied together by the cache line. On the other hand, if the shared variables are actually accessed at the same time by the same CPU, you want to put them on the same cache line, or at least close in memory. Well, there are several other things we can ask about our mutex test. For example, I mentioned that there is also pthread mutex. Is it faster, slower than std mutex? Well, we can try. This is exact same code, only I'm using the pthread mutex. This is how you initialize it. This is the type. Well, this is one of the ways to initialize it. Again, I have the baseline without locks. Now, this time, I had to either wrap it in a class or just call pthread mutex lock and pthread mutex unlock. For simplicity, I chose to do later. In any actual well-written program, you would want to wrap it in a class. Here, I'm pretty sure that I'm not going to throw or issue return. This much code I can visually inspect and be sure of that. Let's see. With logs, you never get exactly the same data twice. There is a lot of randomness involved, but overall, it's pretty close to what we had for the std mutex. And actually, on this machine, on this compiler, std mutex is built on top of pthread mutex. Doesn't have to be this way, so one may be faster than the other in a particular implementation, but often you'll find that it is this way. We're protecting a very, very small piece of computation by this log, just an increment of an integer. In real life, this may actually happen. You may have a counter that needs to be protected, but usually you would have some more meaningful computation protected. So let's say you may have a queue into which multiple threads put data into that queue. So let's see how that would perform. Here is our code. Here is the mutex. What's the queue? For purely technical reasons, I had to wrap the regular std queue, this one here, into a class. I had to give it member functions that have return values. This has to do with how this benchmark do not optimize is written. This is an std queue. For all practical purposes, I'm pushing the numbers and I'm immediately popping back the top number. I did push one number into the queue before, so the queue never goes empty. I don't know what stdq does when it goes empty, and that's probably implementation dependent. It may release all the memory, and I don't want to incur the cost of malloc and free every time I go through this. So to model more accurately the situation where we're adding and removing elements from the queue but don't completely deplete it, I keep the queue populated. So this one push, one pop is the transaction that I'm going to time without the lock and then with the lock. Okay, it's a little longer than a single increment, but it's actually still a pretty short transaction. So this is the baseline, 4 nanoseconds with no threads. 24 on one thread, again, the same as before. Mutex, std mutex adds 20 nanoseconds just for locking and unlocking. And then the same as for increment, it goes up in more or less the same way. Well, what if I had more computation in the critical section, like a lot more? So here what I'm going to do is make a note of this value of n. I'm going to enqueue or push n elements, n is pretty large, and then I'm going to pop them all. Same thing with the lock. So I'm pushing onto the queue and then taking from the queue a lot of elements. Now, we already know that such a long critical section is not good for overall scalability of the program. because that critical section will be running single-threaded with any kind of lock. But setting that aside, how long does it take now? 5,000 nanoseconds without any threads. Basically, this is within the noise. It appears to be a little faster, but that's just fluctuation of one test to the other. You would have to run this test several times and average the results to get a good value. And I'll show you this data later in this class. It goes up a little bit as we go to more threads. So there is some contention, but basically the critical section now takes so long that most of the time threads come into it one at a time without waiting. They just get the lock and go do their stuff. So what have we learned about mutexes specifically for C++? Since C++11, we have a mutex, finally. It may be just a wrapper around pthread mutex, doesn't have to be. Whether it is or it isn't, you can mix different locks, so you can have both pthread mutex and C++11 mutex in the same program. Obviously, one critical section has to be protected by a particular lock that all threads use for that critical section, otherwise it doesn't work. But different pieces of shared data can be protected by different locks. You are entering a danger territory here. As soon as you have several different locks, you may end up in a deadlock where each thread holds one of these locks and then wants to get some other one, and nobody can get anything. We will talk about that in great detail later. This comes to the end for our lesson on mutexes, not locks, just mutexes. There are other locks that we'll go to next. Mutexes are simple, not inexpensive, but how important it is that they are not inexpensive depends on how long is the critical section. In particular, if you have long critical section, you don't care. If you have short critical section, you're more sensitive to overhead. Of course, if you have long critical section, your scalability of the program is shot anyway. We'll continue next with other locks. Welcome back to our classes on locks. Now that we've dealt with the boring mutex, we can get to the really good stuff, other locks. And we continue with spin locks. The motivation here is to find a cheaper lock. As I said before, mutexes provide simple protection for shared data, but it's not particularly cheap. Mutex is actually a rather complex entity. It has to do a lot of stuff. So what happens when a thread is waiting on a mutex? It could be suspended. It goes to sleep, which means it's not constantly checking for the mutex. But when the mutex is unlocked, that thread must wake up, so somebody else must do it. The kernel does it, the scheduler. So we must have a list of threads waiting on this mutex, somehow attached to the mutex. To know which one thread to wake, we may need their priorities, we may need to know how long they wait, and so on. There is quite a lot of data associated with all of that that is hanging off the mutex and need to be handled. If you have a long critical section, that's what you need. But if you have a short critical section, let's say one operation like that increment we've seen, it doesn't really pay off to have all that machinery to protect such a short computation, because basically all the threads will get through it quick enough, no matter what we do with the lock, as long as we somehow prevent them from all getting at that integer all at once. If we just can stagger their accesses in time, it'll be very quick, 2 nanoseconds per increment, and then the thread unlocks the mutex, so next thread goes in. Not worth doing anything in that time. Well, we can try a simple lock. Let's say we had a Boolean, and the meaning of this Boolean L is if it's false, then the lock is unlocked. So L means locked. True, it means locked. False, it means unlocked. So if we want to lock it, we just write true into L. If we want to unlock it, we write false into L. And if some thread wants to write true into L, but L is already true, it means that the lock is already locked. We have to keep reading L until we get false. Now, of course, in order for it to be an actual working lock, all of these operations have to be atomic. You have to both read the current value and write the new value into L at the same time without the possibility of interruption. We have atomics now in C++, starting from C++11. There were ways to get them before using inline assembly, for example. So let's do this. Let's see the simplest lock in action. Such lock, by the way, is called spin lock. And the reason it's called spin lock because you're spinning on that Boolean. Well, in C++, we have in particular something called atomic flag. An atomic flag has really just two operations, well, two that matter for us at this moment. Test and set. It guarantees to be atomic. What it does is it sets the value of the flag to true, no matter what it was before. and it tests it and it returns true if it was true already, and it returns false if it wasn't true. Now it is true. And then there is clear, which sets it back to false. So all we need to do to lock is wait for the value to become false. As long as it's true, we're going to just spin on it. And to unlock, we're going to set it back to false. Now we don't have to wait for anything because we already got the lock. Nobody else is changing it. So we have our unsigned long value that we will be incrementing. It's somewhere in memory. We have our global spin lock object. Note that I wrote it to be interface compatible with the std mutex. It has lock and unlock, which means in C++11 terms, it's basic lockable. Here is our baseline, just an increment with no locks running on one thread. Here is our actual measurement using lock guard of the spin lock type. Used to be std mutex, now it's spin lock. As long as it has lock and unlock, doesn't matter. Here is the lock guard on that spin lock S. In the constructor, we lock. In the destructor, we unlock. Within the critical section, we increment. And again, we're going to run it on one. This is just our baseline, runs on one thread. The lock 1, 1, 2, 4, and so on. Compile and build and run. Well, that's pretty bad, actually. For comparison, let's run the Mutex benchmark again. We don't have to build it. We already did. This is the one where the data and the mutex are not close to each other. Same thing, if there is no contention, takes 20 nanoseconds to lock this thing. But after that, the spin lock, this is the spin lock. The spin lock behaves a lot worse than the mutex. Didn't I promise that this will be a faster lock? And in particular, look at the CPU time. CPU time is like 10 times worse. Well, real time is also 10 times worse. So it's spending a lot of time on all the threads. Now, the fact that it's spending more time by itself isn't surprising. It's busy trying to get the value of true out of the Boolean. But the fact that it performs worse than the mutex, that's not what I promised you. There is actually a reason for that. And I know what it is, so I'm just going to show you. So let me show you the fixed version. This is the spin lock class. It has the same flag test and set, and the same clear and unlock, but this is what was missing. This is new. In this case, I count to 8, and then I call this library function called nanosleep. Nanosleep puts the program calling threads specifically to sleep for the specified time, and the time is in nanoseconds. Well, this would be seconds. That's 0. So I'm asking to sleep for 1 nanosecond. It probably can't sleep for 1 nanosecond just because it can't measure that short of a time interval. So it'll sleep for as short time as this operating system and this hardware can provide. It'll be a few nanoseconds. I'll explain in a moment what it does, but let's see if it actually fixes anything. Same 2 nanoseconds for increment without lock, extra 20 for the lock. But now, again, let's compare this with mutex. Look at the real time. Well, we're doing pretty good. We're far ahead. It actually went down as we had more threads, 128 threads running on just 4 CPUs. I mean, that's abuse. It never peaked anywhere near what the mutex was, 47 seconds. Well, 100 seconds. Okay, it's kind of close. For 2 threads, it's roughly the same. This is within noise between 90 and 106. Then it went down, and at, let's say, 16 threads, it's 1/10 of what it was for the mutex. And the CPU time is actually decent too. This is not bad. So why did putting the thread to sleep, making it slower, why did it actually help? There are several caveats. We have just blundered it into a very obvious one when dealing with spin locks. You must remember, spin lock implements what's called busy waiting. All the threads that are not currently in the critical section that are waiting on the lock, they use CPU all the time. All they do is they read the value of the flag over and over. Obviously, if critical section is long, so the wait is long, this is going to be pretty bad because one thread is doing computing, all the other threads that are waiting on the lock are also doing computing, just the useless kind of computing. But it's even worse than that, because a thread that is 100% computing appears to the operating system scheduler as doing useful work. It doesn't know that it's just spinning on the lock. The OS will be reluctant to interrupt it. And that's one of the big problems we run into. the threads that were waiting are more busy. They're even more computing than the threads that are actually in the critical section doing their own computing, because the thread that is waiting is doing a very simple computation, just reading the same value over and over again. It's 100% CPU load. Waiting threads don't get interrupted, don't yield the CPU easily. That's why when we had a lot of threads, they basically saturated the CPU. They crowded the poor one thread that was doing the useful computing and was the only one which actually had a chance to unlock the lock eventually. They kicked it right off the CPU and were all doing the useless wait. There is another problem here. Take a look at this while line. This is common to all spin locks. We're spinning for as long as lock is locked. When we finally get the lock, L will be false. Until then, for all our previous attempts to get it, it was true. All modern CPUs have this very important component called branch predictor. Branches are expensive in modern CPUs, so what the CPUs do is they predict what the outcome of the branch check will be, based on what it was last time and the time before that. And then they don't wait for result of the branch calculation to come back. They begin speculatively evaluating the predicted branch. So you come to something like if. The hardware remembers, okay, the last 10 times if was true. Let's begin evaluating the if clause. If this time it's false, well, that's too bad. We have to flush all the results from the true clause and go into else clause. But if the branch prediction was correct, then by the time we confirm that it was correct, we already have several instructions. Evaluated, great, speed up, great acceleration. Note that you have a branch misprediction every time immediately after the lock is acquired, because when the lock is acquired, the value of L is going to be different from what it was for all the previous checks. The branch predictor will remember, okay, tried L, true, tried L, true, tried it 10 times, true. Okay, probably L is always true. Tries it 11th time, prediction is true, and this time it's false. You go into the critical section, and you begin your computation with a branch misprediction. This is about as bad for a branch predictor as it gets. You have to introduce into the spin lock something to both yield the CPU to the thread that is actually doing real computing, as opposed to the busy waiting, and reset the branch predictor. There is more than one function that does it. There is actually a pause instruction on x86 that you can stick in using inline assembly or maybe compiler intrinsics. There is the nanosleep that I used. There is another function on Linux specifically called schedule yield, which yields the scheduler to another thread. There is no single best choice. It may depend on the hardware, it may depend on the operating system, it may depend on the context, how heavily you're hammering the lock, and so on. I found that nanosleep with the minimum time is a kind of safe choice. It may sometimes not be the best, but it's never the worst. As far as I know, by the time you listen to this class, you may have some hardware I have never seen before, so it may actually be the worst choice. But you know how to benchmark it now. You can find a better choice for your hardware. For a generic x86 machine, I use nanosleep, and it works okay. There are several other complexities. Don't just go and write your own spin lock just yet. In this course and later chapters, we'll cover some of these complexities. There is more that you need to know before you can write a good one. Also, we can do several optimizations. We can probably get another 50% easily out of that spin lock that I have shown you. In addition to that, there are many strategies for backing out of the lock. What it means backing out is you try to get the lock, you couldn't, you have to wait. So how long do you wait? How long until you try again? In our log that I have shown you before, I was trying to get it 8 times, and then I called nanosleep for the minimal possible amount of time, and that was all I did. You could, first of all, why 8 times? I measured it 8, 16, 4, doesn't matter, 1 or 100, that's worse. On different hardware, there may be a difference. Then, if you couldn't get it for a long time, maybe you should wait longer. So there are all these different strategies. You can read about them online, or there are some books on this. It will depend on your hardware and on the workload. There isn't single best solution here, but if you want a generic solution, we'll improve on this spin lock later in the class, and it's pretty good. Let's continue our exploration of spin lock. We did one using this atomic flag. Well, what's inside atomic flag, we don't really know. Well, we could look inside and find out. The standard doesn't say. The important thing about the spin lock, well, it doesn't have to be Boolean. Basically, anything that switches between two values will do. For example, we could just have an integer and write 0 and 1 into it. Why not? Here is one that does that. Now I have an atomic unsigned int. And instead of the test and set, I'm going to atomically exchange the value that is in with the value of 1, and exchange returns the previous value. Initially, it was 0. So if I get back 0, it means that my thread is the first thread to put 1 into that lock, so I got the lock. If I get back 1, it means that I haven't really changed anything. I exchanged 1 to 1, but it means that somebody else currently has the lock and I have to wait. And I'm doing the same back-off strategy. I have non-sleep call after 8 times. Other than that, it's exact same code. So just instead of the atomic flag, I'm using atomic integer. For all we know, atomic flag may be implemented using atomic integer. Well, here it is. Just for a reminder, this is what we had with the atomic flag. Basically the same thing within the noise. As I said, it's very likely that atomic flag is implemented using an atomic integer. If you want to know what your compiler does with atomic flag, look at the assembler. This is a spin lock that is protecting a very short critical section. Doesn't get any shorter than simple increment. We tried several longer critical sections with our Mutex. In particular, we tried this Q. This is the same Q. This is the same spin lock. This one uses atomic flag. Since it didn't show any difference from atomic integer, I'm going back to atomic flag here. 1 push, 1 pop on the Q. That's our critical section. And for the threaded version of the benchmark, we're protecting it with the spin lock. This is what we get. Again, for comparison, STD Mutex, protecting exact same Q. Well, quite a bit longer for a large number of threads, a little more than 10 times longer. So the spin lock really works for this small workload. It's larger than an increment, but it's not very large. And if we had a larger workload, this is our model large workload. So this large N, and what the workload is, we're pushing that many numbers onto the queue, then taking them right back out. Exact same spin lock as before. It was the atomic flag. Okay, and for comparison, that same large workload with STD Mutex. Well, that's basically the same numbers. Okay, so workload was large. Actually, Mutex was a little better for large number of threads, and it makes sense, especially look at the CPU time. CPU time for the spin lock is significantly larger than for the Mutex because for such long waits, the pthread Mutex or STD Mutex will put the waiting thread to sleep. Spin lock will just keep reading the integer or the Boolean out of the atomic flag over and over again, uses more CPU time. Using that much CPU time has to eventually, for large number of threads, start costing you some real time, and it does. What have we learned about locks other than mutexes? Mutexes do have considerable overhead, which matters a lot if your critical section is short. Spin locks are a viable alternative. They're very simple. Write 1 into an integer, write 0 into an integer. Doesn't get much simpler than that. They have low overhead by themselves. Locking and unlocking is as cheap as it gets. Waiting, on the other hand, is not cheap at all if you have to wait a long time. If you don't have to wait a long time, if you have just one increment, well, one thread is doing an increment, the other thread is doing maybe 2 reads of L of the flag during that time. That's okay. If you have a waiting for a long time, spin lock isn't the right approach. All spin locks must pause somehow to both yield the scheduler from the waiting threads and reset the branch predictor. Otherwise, it's going to get really bad. For now, this is all on the spin locks. Don't go write your own spin lock just yet. There are several things I have to teach you before you can go and do that. But I can't teach them to you right now. It's a matter for several chapters in this course. For now, this is all we have to learn about a spin lock. Welcome back to our class on locks. There are even more locks for us to consider and some other ways to synchronize accesses to shared data, so let's cover what's left. We covered mutexes, we covered spin locks, but there's a lot more interesting things you can do with the spin lock. In a more general view, what spin lock does, it basically has a token. There is only one of these, and at most one thread can own this token. And in order to enter the critical section, the thread must have the token. You can pass the token from one thread to another, but you can't multiply them. For the case of spin lock, that token is the value of flag equal to 0. At most, one thread will see flag equal to 0, everybody else will see 1. So if you got 0 from a flag, you have a token, you can go into the critical section. What this means is you don't have to have that flag as a token. You can have anything as long as there is only one of it. This lets you integrate spin locks into your existing data structures. So let's say you have a pointer to data and you will do some work on this data. In order to access data through this pointer P, you need the pointer P. P is the natural token to access this data. You can't possibly access the data if you don't have P. So if you were somehow to own P so nobody else can get it, then that thread that owns P would have exclusive, protected access to the shared data. And everybody else would have to mill around waiting for the token P to be released. We can modify our benchmark of a spin lock. We actually have a pointer to data, and we have a spin lock. That was our old spin lock benchmark. We can modify it. We now don't have a dedicated spin lock. Our pointer to data now must be atomic. It's still a pointer on sign long star, but it's an atomic pointer. Why does it have to be atomic? Well, the control variable of the spin lock has to be atomic so we can do the atomic exchange on it. And since we're now going to use this P for double duty, both as a pointer to data and as the spin lock, that one has to be atomic. So how are we going to take exclusive ownership of P? Well, that's very easy. We're going to atomically exchange whatever is currently in P with null. Null doesn't point to any data, so if one thread successfully does this, it now has stored in this P save the only copy of true P in existence in the entire program. Everybody else will see null. So instead of the spin lock, we have to create some pointer lock. It's basically a spin lock on a pointer. I need a reference to the pointer P that I'm going to spin on, and I need to capture it as a reference. I don't want a copy of it. I want a reference to the original one because it's the one that is shared between all threads. And I need a place to save it. That one is per thread. Whichever thread currently owns the lock will save the true value. My function lock now returns that value of the pointer. That's the one you own. Everybody else sees 0. My function unlock has to just put it back. I can do it using exchange. I could also assign to it, but in this case, it was an exchange. We don't care about the return value. We actually know what the return value is. It's null. We're going to put the saved value back to unlock. Don't have to return anything. Otherwise, it's exact same thing, only now P is atomic, so we have to modify our code a little bit. To get the value of the pointer out of the atomic, we have to call load, and then it used to be X. Now, what was X now is star P, what the pointer points to. Okay, so we're going to increment that. And for our baseline, no locks, we're just going to load the pointer, capture it in a local variable, and increment. For the locked one, well, we're going to initialize it to 0 the same way. Then we create this PTR lock. Now, PTR lock isn't shared between threads. Each thread has its own PTR lock. What is shared is this atomic P, because all the PTR lock does is it grabs the P into exclusive ownership and puts it back. So here it is. We can't use a std lock guard because the lock function returns value now. It's not void anymore. In your actual program, you would write your own lock guard to work with that kind of lock. Here, for simplicity, I'm neglecting that, which means I should not neglect writing manually unlock at the end. Lock does two things. It takes the value out of P and returns to me, and it makes it exclusive to my thread by overwriting it with null. If I exit it from lock, I have the only copy of real P in existence in the entire program, and I'm not afraid to increment what P points to. Everybody else is staring at this null waiting for it to change. When will it change? When I call unlock. Let's run. These are the numbers that I'm getting. Now, what should I compare it with? Well, spin lock without the pointer. So this is the test where I had the same increment, but I had a separate spin lock. That's a little better for small number of threads anyway. So for 4 threads, it's still better. After that, when you have more threads than I have CPUs, it seems to be worse. In any case, it's a kind of close call. It's very close to the noise margin. I would have to run multiple tests an average to get more accurate values to see if this trick paid off or not. Now, for incrementing integer, you may not even have a pointer to the integer. You may just have integer somewhere in your program. For example, for the q, well, we did have a pointer to the q. So we can play the same game on the q. We always had a pointer to the q, only now it will be an atomic pointer to the q, starts its life with being null. This q lock is exactly the same as the pointer lock we had before, only it's hard-coded to work on the q pointers. If you wanted to have something like this in your program, you would make it a template. Again, our workload is one push, one pop, and our lock protection scheme now looks like this. We create a q lock from that shared atomic pointer q. This is our critical section. We begin it by taking exclusive ownership of the entire queue. We replace the original, the shared atomic, by null, and we store the old value in our local variable ql, which is now the only true pointer to the queue in the entire program. Since it's the only true pointer to the entire queue, we can push and pop to our hard content. Nobody else can interfere with the queue. There can't be a raise condition. When we're done, we'll unlock. We're going to run these measurements for the single push and pop and for the large workload that we have seen before. Instead of one push and pop, we're doing this many. Just to show you that I'm really doing it. Here we are. Otherwise, it's exact same code. Well, here it is with the q lock, where the q pointer does double duty as a spin lock. For comparison, separate spin lock. A little slower for small number of threads. Seems to be a little faster for the number of threads significantly exceeding the CPU. Okay, so there is something to it. Exactly how much you would have to benchmark carefully. Not a huge dramatic improvement like it was going from Mutex to spinlock, but maybe something to look at. So what we have done here is what you might call an invasive spinlock, meaning a spinlock that invades into your data structures. It uses part of the data structure for the flag it spins on. Pointers are particularly good for it, since that's your natural token to access data. You don't have a pointer, you can't access anything. But you could have other data elements. Maybe there is a version number in your structure, and the version numbers are 1, 2, 3, 4, 5. You could say if the version number is 0, it means somebody else owns that structure. You have to wait for the version number to become non-zero before you can get in. Counts. You have n elements of something. If you get -1 as a count, it means somebody else is in the process of adding an element. Index, same thing. Any number that has a invalid or reserved value. The access token must be a shared variable originally. It doesn't have to be an atomic shared variable because it was protected by the spinlock before, but it must be a shared variable. Why? Well, because if it was not shared, then you don't gain anything by making it into a spinlock. You just converted a non-shared variable into a shared variable, which is what spinlock did anyway. If it was also shared, then you gain something. You had two shared variables, your pointer, let's say, and the spinlock. Now you only have one shared variable, the pointer. So you reduce the number of shared variables. Well, of course, it saves memory. And it could be significant if, for example, your entire data structure is a pointer and a number. Cutting out an extra 4 bytes for the spinlock could be significant. It may save time because you're now working on one shared variable instead of two. You have to measure whether it actually does save time or not. In our benchmarks I have just run for you on my small machine, it seems like if you have few threads, that invasive spinlock is faster. If you have many threads, it isn't. That's not a universal conclusion. You have to measure your own. It's still a spin lock, but it's a kind of interesting, non-trivial spin lock. There are other ways we can manipulate shared data. So this is an interesting spin lock, invasive spin lock variant on the traditional spin lock, where you use a portion of your own data structures to spin. This is true in general for spin locks. Anything that can be used as access token you can spin on may save you memory and time. This isn't the only way to access shared data. There are other ways. Let's talk about them briefly. We will talk about them more later. Remember, we started by saying to avoid race condition, shared data must not be accessed by 2 or more threads. At the same time, in an unsafe manner. So far, we dealt with the same time part of that sentence. Any kind of lock, including the spin lock, prevents two accesses at the same time, which is enough to make it correct. But what about unsafe manner? It implies that you could access shared data at the same time if you just did it right. And that's true. There are ways to access shared data simultaneously, concurrently, without locks, and still get well-defined behavior using atomic operations. Let's see the simple case after a short break. Welcome back. Let's see a very simple case of synchronization without locks. We keep working with this very simple critical section, an increment of an integer. For that one, we happen to have an atomic operation. So here it is. We'll just make x our shared variable that we're going to increment. We'll just make it atomic. Plus plus on an atomic variable is atomic. It reads, adds 1, and writes in a single transaction that cannot be interrupted. So this std atomic here guarantees that increment is atomic. That's just how std atomic is defined. It only works for integer types, but it wouldn't compile if it wasn't an integer type. Plus plus wouldn't compile. Atomic would. So now we can do it without any locks at all. And you see here, we don't have any locks. We just have plus plus. That's our critical section, except it's not really a critical section now. We're just doing it atomically. Let's compare this with our best spin lock so far. The non-atomic increment. I just created a local variable called x and did plus plus on it. There are no threads here. There's just one thread. So this is just to remind us what the cost of a non-atomic increment is. That's the only purpose of that code. So the non-atomic increment, obviously on one thread, 2 nanosecond, atomic increment on one thread, 7. No thread contention here. It's just the extra cost of the atomic increment. It's a different hardware instruction than your plain increment. 7 goes to 20-something when you have contention. Let's compare it with our pointer-based spin lock. Still 2 nanoseconds if we didn't have any locking at all, so that should be the same. It's just the increment with no protection. 15 nanoseconds on one thread to spin on the pointer. So to take the exclusive ownership of the pointer atomically with an exchange, and to add 1 and release the exclusive ownership of the pointer, 15 nanoseconds, versus 7 nanoseconds to just do atomic increment. The difference continues and gets significantly more as we go up in the number of threads. So atomic access here, for example, let's look at some large number of threads. Atomic access, especially for large number of threads, is significantly faster than our best so far spin lock. Now, our best so far spin lock isn't really the best spin lock yet, so we can narrow down this difference, but it still shows you that if you can get away with not using locks, there is great potential for optimization. Just about anything other than the simple increment, even our next example, pushing into the queue, is a lot harder to do without locks. There is a whole large area called lock-free programming, and we'll return to it, but this is a matter for another day. There are a few other things we need to learn first. But this is just to whet your appetite. If you can pull it off, you can get a lot better performance than from locks. I did mention several times that the cost of the lock overhead is more noticeable when you go to more CPUs. The cost of any single-threaded computation is more noticeable when you have more CPUs. So what would happen if I did have more CPUs? I actually went to a large machine and ran the same benchmarks. So let's see the results. Increment, that's our increment of a 64-bit integer, measuring real time versus the number of threads, how long it takes to increment, with the mutex, the top line, versus spin lock, the squares, versus the pointer lock, these crosses here. So spin lock is better, significantly better than mutex. Pointer lock isn't its official name, it's just how I'm calling spin lock, spinning on a pointer. It's really still a spin lock, just I have to distinguish it from the spin lock. Atomic increment is quite a bit faster on just one thread. then it's kind of in the same ballpark as the pointer lock. So it's still better than the spin lock because spin lock has to deal with two shared variables, and both pointer lock and atomic do an atomic operation on one shared variable. As long as we have only one shared variable, atomic operation is an atomic operation. We get more or less the same results until we go to enough threads that we actually have to wait a lot on the pointer lock. So it's not just one atomic operation anymore, we're spinning on atomic operation often because the thread contention is high. This machine has 120 CPUs. Still, the odds of spinning on the lock are considerable for a large number of threads. Almost all 128 threads or all 64 threads are running on their own CPUs. Atomic operations become a bit more expensive than on one thread. So we saw it went from 15 nanoseconds to something like 25. Similar numbers here. This machine is a little faster. So goes from about 7 nanoseconds to maybe 16. Stays at 16 even for the large number of threads. Now that's real time. CPU time, well, we can see that CPU time always goes up with the number of threads. Mutex is worse than anything else. This is logarithmic scale, by the way, so this is a large difference. The interesting thing here is that atomic actually consumes more CPU time than the spin lock. Probably has to do with the fact that the spin lock actually goes to sleep sometimes. In atomic, the hardware will just keep trying to do this atomic operation until it succeeds, but it still ends up being faster in real time. For a large number of threads, eventually the cost of spin lock adds up and overwhelms the cost of atomic. Usually you're interested for high performance in real time, just how long do you have to wait, how fast can you do the computations. On the other hand, if your concern is, for example, the power, if you are in a low power multi-core system, then the CPU time is a reflection of how many computations are done, so how much power is consumed. So this may be of interest to you in some cases. Okay, this is our shortest critical section, the increment. For the queue, one in queue, one DQ, we don't have a lock-free version of it, at least not yet. Mutex is considerably slower in real time until we get to the large number of threads. Here, the costs basically evens out when you have a large number of threads. This just shows you that your results do depend on how many CPUs you have, how many threads you have. On some systems, there won't be much advantage between spinlock and mutex. On the other hand, on the system that I was using live before you, there was. Using this Q lock, which is the spin lock on the pointer, doesn't do us anything for small number of threads, seems to give us some advantage at large number of threads. This workload is several times longer than a simple increment, so the slight difference in overhead between spinning on a different shared variable and spinning on the same shared variable isn't as significant as it was for a very short critical section. Same thing for the CPU time, only for the CPU time, Mutex still uses more CPU time than a spin lock. And very large workloads. Now, this is actually interesting. Our large workload was done using a queue, but it's just a large workload for our purposes. So this is real time, and take a look, the Mutex. Well, the Mutex takes some time here. Spin lock gets a lot worse. We have a long workload, and everybody who is not computing the large workload is busily spinning. That has to eventually come up somewhere, and it does. If we have fewer shared variables, it's not growing quite as fast. It looks like it would have also crossed the Mutex eventually, but we don't have that many CPUs. Again, highlights hardware-specific differences, along with some general trends. For small number of threads, spin locks are consistently better. For the CPU time, consistently, any kind of spinning on a very long workload is more than the Mutex CPU time, because Mutex for long waits will put your threads to sleep. Spinlock obviously never does. What does this all show us, in addition to the fact that you actually have to run your own benchmarks? It shows us that the spin locks work well for short workloads, for short critical sections, where their low overhead is their strength. Mutexes gain when long wait is necessary, when you have a long critical section. But of course, if your long wait is necessary, your overall speed up is not going to be great anyway. Invasive spin locks use fewer shared variables when they use already shared variable from your data structure as an access token, and gain some advantage over spin locks that use a separate flag to spin on. How much advantage depends on your data structure, on your contention. And if you can avoid locks and use atomic operations, well, then more power to you. I'm going to try to teach you how to do that easier and with better results, but that's a matter for another day. If you want to explore this material on your own, here is something for you to consider. Remember, we talked about false sharing. Two independent shared variables on the same cache line behave performance-wise as if they were shared. There is the reverse side of the false sharing. Two actually shared, dependent shared variables that are used by one CPU, so shared, cost less if they're on the same cache line than if they were on separate cache lines. We did measure the cost of the false sharing before, but we never actually measured this gain of putting multiple shared variables on the same cache line. So this is something you can try using the microbenchmark. Try accessing two or more shared variables. Well, you have to actually access all of them at once, one after the other, as a function of distance between them in memory, right next to each other, far apart, a little bit apart. See how putting them on the same cache line or adjacent cache lines, how that affects performance of sharing. Welcome to the next lesson on high performance and concurrency. Today we're going to talk about the memory model. This is going to be a class that is pretty heavy on theory and definitions. For the first time, there won't be any code, but we reached the point where in order for us to be able to talk about more complex things that are related to high performance, we have to know the vocabulary. Otherwise, we'll be forever talking about this thing that happens before that other thing. Now let's go study the memory model. Now, before we go out into the definition of the memory model and what goes into it, let me point out by way of an introduction that it's actually impossible to write a multi-threaded program on a compiler that doesn't have explicit support for it, even if the language itself knows nothing about threads. Case in point is C++ before C++11. The standard didn't say a word about threads or concurrency. Nonetheless, we were writing multi-threaded programs, and that's because the compiler actually went beyond the C++ standard to support it. Let me illustrate why such support is necessary. So here is some small program that increments a counter. It's a shared counter between several threads, so we have to protect increment by the lock. There is the lock and the unlock. I'm making it explicit just to illustrate the point here, to make it everything visible. So this is a valid concurrent program. The important thing to note here is that these two functions operate only on this lock variable. They don't have anything to do with the counter, and incrementing the counter does not involve lock in any way. This is the kind of situation that calls for an optimization on the part of the compiler. Not only the lock isn't used in the counter, the lock actually doesn't depend on the loop variable either. The lock is declared up here. The I doesn't go into the lock or into any of the functions. So this is a valid optimization from the compiler's point of view. In fact, it's the one that the compilers very commonly do. It's called hoisting a common subexpression. We had a common subexpression lock and unlock inside the loop. Now, compiler realized that it doesn't depend on the loop and pulled it out, evaluated only once in front of the loop. Needless to say, this would be very bad if it actually happened. Now, you could point out that lock may actually have side effects. For example, lock could be volatile, and maybe it is actually declared volatile inside. It wouldn't be invalid. It may or may not be, but let's say it is. Then the compiler operates under restrictions. Volatile reads and writes cannot be reordered with respect to each other, and the number cannot be changed. If the program says read the same volatile variable 3 times, you have to read it 3 times. That's the definition of volatile in C++. So now the compiler cannot hoist the common subexpression out of the loop. Well, it can, but it can't change the number of the calls. However, nothing says about reads and writes of volatile variables with respect to non-volatile variables. So this is a perfectly valid optimization. Pull up everything operating on the lock, do it once at the beginning of the loop, and then forget about the lock. Nothing in C++ standard prevents this from happening. You could go one further and pull up all of this out of the loop as long as you do it n times. Nonetheless, the original program was a valid program and it worked, so there must be something going on beyond the C++ standard. In this case, it's a POSIX standard. and most compilers that support threads in C++ written to the combination of both C++ and POSIX. But the point is, a multi-threaded program requires support from the compiler at least to recognize the transformations that would be valid in a single-threaded program and are not valid in a multi-threaded program. These restrictions need to come from somewhere. In this case, it comes from a POSIX standard, but in general, concurrency has to have some guarantees from the compiler, otherwise you can't write any correct concurrent programs. So now we can come to memory model. We already know that the compiler must provide certain guarantees. The same is true for the operating system. The same is true for the hardware. Those guarantees may be strict or loose. Those guarantees may take a form of don't do this, but you have to know what you can and cannot do. The set of these guarantees essentially is what forms the memory model. A more formal way is to say that memory model describes the interaction of threads through memory. This is actually a very useful definition for our purposes, because all the way through this class up until now, we were talking about threads and memory, shared data, and so on, but threads interacting with memory. This definition shows you why this interaction with memory is so important. It has its own name, and it's one of the central concepts for concurrency. The guarantees of the memory model are necessary for understanding and proving correctness, but also for efficiency. In addition to saying what's guaranteed to be true, what restrictions are available, memory model also defines what can be optimized without breaking correctness. Interaction of threads through memory, there is a lot of things bundled into that one sentence. So what's in it? A big set is ordering guarantees. What are the guarantees given for relative order of memory reads and writes, other operations? Usually these guarantees are not kind of uniform. These guarantees say, well, for the most part, very little is guaranteed, but there are some synchronization points, and then more is guaranteed. So what are the synchronization points? How to trigger them, and what exactly do they do? Another part of memory model, to some extent, it's another view of looking at the memory model, is what's called a consistency model. Consistency model is a more general term than memory model because people can talk about consistency models for data on disk, consistency models for databases, and so on. But if we say consistency model of memory, we are pretty much talking about the memory model, and the general perspective of this is to look at it from this point of view. What memory state is guaranteed to be seen by multiple threads as consistent or identical or as different? So if one thread sees memory in a certain state, what can we deduce about how another thread sees the same memory at the same time? Now, there are several players in the memory model business. First of all, hardware has a particular memory model. If you're running on some kind of emulated or interpreted or virtual machine language, your runtime or VM has a memory model. Language defines a memory model for this language, and any standard compliant implementation must provide that memory model one way or another. Compiler may provide additional guarantees that go beyond what language requires. Case in point, any C++ compiler prior to C++11 that supported concurrency provided POSIX standard or some other standard for concurrency. Compilers must avoid transformations that would violate the memory model, the guarantees provided by the memory model. That primarily comes into play because it limits optimizations. Compilers have to implement the memory model of the language or the combination of standards that they decide to use. They use the available hardware, so your C++ code gets translated into machine instructions. Compiler knows the hardware is generating the code for. It knows the memory model of that hardware, so it's going to use that memory model to give you the guarantees that the language requires. This may require some more work on the part of the compiler than just generating the instructions for the code if the hardware memory model is less restrictive than the language memory model. Now, if the hardware memory model is more restrictive, there is very little compiler can do about it. You would get the guarantees that the language requires. You would also get some more guarantees that weren't required, but that's how the memory models work. A more rigorous, more restricted memory model is kind of a superset of guarantees of the less restrictive memory model. If you get more guarantees, you're definitely getting the guarantees you asked for. You may be getting some others. In general, you think of memory model as a property of the entire system. It doesn't really matter who provides a particular guarantee between the compiler, the runtime support, and the hardware. They all somehow get it worked out. Hardware has a memory model, which basically determines what instructions and other events, such as memory visibility, can be reordered in this hardware. Compiler reorders instructions all over the place. That's what optimizers do. It does reordering that would not be available in the hardware. For example, compilers, as we discussed before, can do common subexpression, hoisting and elimination. Hardware wouldn't do that normally. Compiler has to obey the memory model while doing that. A runtime system that sits between your code and the hardware may help enforce some guarantees. Depends on the language and the system you're using. So what is important to remember from here is, first of all, you need a thread-aware compiler to write multi-threaded programs, and that the interaction of threads and memory is called the memory model. It's a property of the entire system you're using. Everything from the compiler to the hardware pitches in to provide you with this memory model. This is enough for memory models in general for now, and let's take a break. When we come back, we will talk about how does all of this apply to C++. We have discussed what a memory model is. Now it's time to apply this knowledge to C++ and talk specifically about the C++ memory model. C++ prior to C++11 had a very simple memory model. Boiled down to, what's a memory model you're talking about? Didn't mention a word about it. C++11 has a rigorous memory model specified in the standard. So if you go either to the standard, that's pretty hard reading, or to one of those documentation sites like CPP reference, you can read about the memory model. Well, this is what cppreference.com has to say about C++ memory model, and it's talking about C++11 memory model here. We're not going to read this whole thing right now, but there are several important points to notice. There is this concept of memory location, and memory location has the granularity of a byte. It's down to a byte. So memory location is basically your variable, arithmetic type, pointer type, so on, but it's what we call variables. So the interesting thing about memory location is that operations on different memory locations are guaranteed to not interfere with each other if they're done from multiple threads. The standard has a formal way of putting it, but that's the bottom line. So C++ memory model, as specified in the standard, has two key concepts. We're focusing on the memory location. The other one is memory order. We'll come back to it in a moment. Now, memory location is important. It says that concurrently writing into non-overlapping variables is well defined. I am translating standard to common speech now. Standard has a very formal and necessary to be rigorous way of putting it, but that's what it boils down to. Now, why is this so important? Seems obvious. Well, C++03 and C++98 had no such guarantees, well, for the lack of memory model in general. On x86, for example, writing adjacent integers of 4 or 8 bytes is always safe, but writing adjacent bytes, like bool or char, may not be safe. So if you have two bool and you write true into one of them, the one right next to it may change. It will not change forever. So if you're running on one thread, you have an array of bool, you're writing into element 0, then you go look into element 1, it will not change. But if you do it on two threads at the same time, and you happen to catch it at just the right moment, basically what happens is thread 1 writes the first Boolean using some operation that perturbs its neighbors. It then does another operation, or maybe that's just how hardware works in multiple steps, that puts everything except the Boolean you wanted to write, everything except the first Boolean, puts it back together. On one thread, you can never observe that happening because that's one instruction, or that's the group of instructions generated by the compiler. When you come to your next C++ statement, this is all done over, all the other adjacent bytes have been restored, and you'll never see them change. But if you have another thread running, you can get lucky and peek into that Boolean array while it's being changed and put back together. And then you can see that writing into one byte changes the next byte. If you go out and try it right now, it may or may not work. Depends on the compiler you're using. Maybe depends on the hardware. As a rule, recent compilers that support C++11 and its memory model will support that memory model even when they're running in C++03 mode. So you go, for example, take GCC 5. As far as I know, you can't see this. On an older compiler, you can. There is a difference between well-defined and good, or in our case, efficient. Remember the false sharing. Two adjacent bytes definitely, or almost definitely, occupy the same cache line. Well, almost, because one byte could be at the very end of the cache line, the next one would be at the beginning of the next one. But usually two adjacent bytes occupy the same cache line, which means you can write into them from two different threads, but you're paying the price for the false sharing. However, in C++11, it's guaranteed to be correct. Okay, back to the C++ memory model. The other part of the memory model has to do with the memory order. And you can read this or the standard part corresponding to this on your own. But the important thing is, you see it talks a lot about synchronized with and happens before, and all of this related to the order happens before one thing happens before the other. So this is all about the memory order. In fact, memory order is one of the major portions of any memory model, including C++ memory model. Let's take a specific look at that. C++ memory order has several different options for order. So they're all listed here. You can read about them here. All the definitions you can go read in the standard. The important part is they start from relaxed order, which basically means nothing is guaranteed. One thread does sequence of operations. Another thread can see these operations in any arbitrary order. Anything can be reordered. And the strictest one is the sequential consistency memory order, which basically means that there is a single total order in which all threads observe all modifications. If you run one thread and observe the memory and you say, okay, what's the order of changes that I see? Well, first X was written, then Y was written, then so on. Then you run another thread, observe modifications from its point of view, from that thread, yep, all in the same order. First X was written, then Y was written, everything agrees. That's sequential consistency. And there are several orders with partial ordering guarantees in between. We're going to study them in a lot more detail later, so you can go read about them on your own if you want. We'll study some of these orders in the next class. There are also dependency-related orders, which is if B depends on A, then A has to be done first. Seems obvious. Sometimes it can be reordered. And there are several other ordering guarantees, but it's bigger than the rest of memory model. This page is bigger than the previous page. And that's because memory order is really like 80% of the memory model. Since memory order is so important for any memory model, including C++ memory model, it deserves a class of its own. So let's take a break and come back to study memory order. Welcome back. Let's talk about perhaps the largest component of any memory model, the memory order. You have seen it referred to in the standard, but I want to take a more practical, more applied point of view now. Let's talk about how the memory order manifests itself from the point of view of the programmer. How do you think about the memory order from practical point of view when you write the programs? One way to look at the memory order is what can and cannot be reordered. So different hardware platforms provide different ordering guarantees with respect to which operations can be reordered. For example, let's say I have two reads. First I read one variable, then I read another variable. They're not dependent variables. If you read dependent variables, usually you have to read the first one first. But let's say I just have X and Y, and I read X, I read Y. In the program, I have written read X, read Y. Can that be reordered by the hardware? Well, it can be reordered by the compiler unless I make them volatile. But let's assume the compiler generated two reads in a certain order, X first. Can the hardware reorder it? Depends on the hardware. Read-write. Can the hardware move read after the write? Write-read doesn't necessarily work the same way as read-write. These are different reorderings. Some hardware have one and not the other. Two writes. If I write X, then write Y, can the hardware actually write Y first? Here's an interesting one, dependent reads. Let's say I read a pointer and then I read what the pointer points to. Can that be reordered? You would think that it's impossible. Dec Alpha did it. If the hardware could figure out that the pointer hasn't changed since the last time you read it, it could reorder it. A memory model actually has a lot more ordering guarantees. There are some of the more exotic ones. there is a read and then there is an atomic read. On some hardware, it's different operations. So the ordering guarantee for read-read isn't the same as read-atomic read. Write atomic write, read atomic write, and so on. Here's an interesting one. Write versus instruction fetch. If that guarantee is not given, you can't write self-modifying code. Probably you shouldn't anyway. In this class, I have been using an x86 machine for all the demonstrations, so what does that machine have for memory model? Turns out that there are two things that can be reordered. Write-read can be reordered as read-write, not the other way around. And it has what's called incoherent instruction pipelining, which boils down to write and instruction fetch can be reordered. Here goes my idea to write self-modifying code on x86. This wasn't entirely true across the whole history of x86. You may, depending on the hardware you have, discover some interesting bugs in the memory order, which will lead you to a lot of interesting debugging. We will have something very interesting. But that's what x86 should provide, and all non-buggy CPUs do that. Pretty much all current CPUs that you have, Haswells and Halems, Sandy Bridge, they'll do this. One way to look at the memory model, what can be reordered. Another way is what's the complete set of guarantees for all of the memory operations. Remember all these exotic memory ordering like read, atomic read. When you say complete set of guarantees, you have to remember to include atomic operations and locks and so on. One thing that we have skirted around so far is we were talking about order of memory operations. Well, how would you know what the order of memory operations is? You have to actually be inside the memory to see what the true order of memory operations is. That's not really an interesting point of view for you as a programmer. When you're debugging the hardware, maybe, but as a programmer, you can't actually know what the order of memory operations is. What you can know is what's the observed order of memory operations is. And that's why if you look at the standard specifically talks about visibility of memory operations. That's what it means. It means what's happening in memory as a black box, who knows? What do I see happening? And how do I see it? Well, I run some code on the CPU and I can observe memory change. I read from memory, I can observe memory changes. That's what visibility of memory operations is. So that's the only thing as a programmer you can know. When we talk about what can and cannot be reordered, what we really mean is what can be observed as reordered. And we won't always be stressing this, but that's what we mean. Another way to look at it is which parts of memory, at which times maybe, are guaranteed to be seen consistent by all threads, and which parts of memory can be seen at the same time in different states by different threads. We have already seen this as the consistency model for memory. Memory models will require certain consistency and will allow some amount of inconsistency. All of these three views, interaction of threads and processes through shared memory, we didn't talk about processes, but basically the same thing if you have shared memory, complete set of guarantee on the order of visibility, and what can and cannot be seen as reordered if you want to be pedantic. We'll shorten it to what can and cannot be reordered for the most part. In practice, these are three more or less equivalent views of seeing the same thing. When you write a program, if you are doing a language standard, if you are studying computer science, these are not exactly the same thing. So there are contexts in which you have to be careful in what you're talking about. But when you write a program, for the most part, you can think of it in whatever terms make you more comfortable, gives you the same results. As we discussed earlier, hardware and the compiler and everybody else pitches in to provide you the memory model you actually work with. In hardware, as we've seen before on x86, only write-read can be reordered. Everything else is ordered. If you have ARM or PowerPC chip, you live in a much more interesting world, in the sense of may you live in interesting times. All four read-write sequences can, in general, be reordered. There may be some particular CPUs where it's not true, but in general, it's a very limited, very weak memory model. In addition to the normal reads and writes, there are these atomic reads and writes. So atomic operations support atomic or non-interruptible operations. Could be as simple as reads, or could be increments, something that cannot be observed in an incomplete state by another thread. What you see on an atomic variable, either it stayed before the operation or after, but not in between. x86 has 32 and 64-bit integers, which in general have to be properly aligned. on 32 or 64-bit boundaries. On ARM, well, now that you have 64-bit ARM, there are now 64-bit integers, for the most part, 32-bit integers. Just because you have an atomic type doesn't mean that every operation is atomic. You can invoke a non-atomic hardware instruction on an atomic 32-bit integer. It'll perform as a non-atomic instruction. There is nothing magic about that location in memory. Atomic, what makes it atomic is that you're using the atomic instructions. Well, we have learned about the memory order in general, a little bit about x86 and other memory orders. Now, none of these are, of course, specific to C++. C++ as a portable cross-platform language has to use whatever hardware you're running it on. So let's have a break, and then we'll talk about specifically C++ memory order. Welcome back. Let's talk about C++ memory order now. Which memory ordering guarantees can you expect from C++? It's time to dive either into the standard or into the reference documentation, and we're going to do the latter. Okay, let's look at some of these memory order types that C++11 provides from the point of view of what we were discussing, the memory order. The ones of interest to us will be these two, acquire and release. Acquire, now look at how it's formulated. A load operation with this memory order. So it's like a modifier on another operation. So you have an operation that is both load and acquire. So such an operation performs acquire on the affected memory location. So what does it mean? No memory accesses in the current thread can be reordered before this load. So anything that happens after has to stay after acquire. Anything that happens before, no guarantees about that. It talks about all writes and actually all reads to memory accesses, all writes and all reads that happen after the acquire. Release is kind of the reverse of that. It talks about the store operation. Now, by the way, you can have load with release and store with acquire. It's just not common. But in principle, nothing prevents you from invoking these release or acquire memory barrier on operations other than load and store. The hardware may not support it and may end up generating something that gives you a more strict guarantee, but it's a valid thing to talk about. So release is the reverse of the acquire. Anything that happens before the release must be seen before the release. And then there is the bidirectional barrier, acquire and release. This combines the two barriers, acquire and release. All memory access is done after the operation with this memory order, must be seen after. Read, modify, write isn't required. Just your plain write with an acquire release barrier will have the same properties. Just read, modify, write is the most common one to carry such barrier because reads are usually acquire reads, stores are usually release stores, so a read write would combine both of them would be acquire release. It's usually the case that that's what you would want. It's not required to be this way. You could ask for acquire and release on the right and you're going to get it. There are other memory orders, and that's just what C++11 defines. In other languages, other possibilities are defined, but these are the ones we will need later. What's the bottom line on C++ memory models? Prior to C++11, none. C++11 and going forward, we have a memory model in the standard. There have been some corrections after C++11, minor tweaks for the most part. Two main pieces to that memory model in C++11. One, it defines a memory location, which is actually very important. As I said, in C++03, you could observe race conditions between two adjacent bytes if you write them from different threads. So C++11 defines that that's not happening. That's as far as memory location. As far as order, by default, you get no order guarantees from the language. Now, it doesn't mean that there are no order guarantees. It just means that the language doesn't require any. Your hardware may have some. The compiler, of course, may do some reordering and weaken those guarantees. But the language doesn't require any guarantees. You can explicitly ask for particular memory order on specific operations, and you have choices from relaxed, which is no guarantees, to the total sequential, which is everybody sees the same order. In practice, if you ask for a weaker memory order, it doesn't mean that you're going to get that. You will get that or a stronger memory order, depending on what's available on your hardware. Case in point, on x86, write cannot be reordered, which means if you ask for a memory order that permits reordering of write, it's still not going to be reordered. You just can't be sure when you look at the C++ program. This is pretty much what we need to learn about the memory model. The main points I want you to remember from this is that, of course, the definition, the memory model describes the interaction of thread and memory. The entire system is what's important. All the components from compiler to the hardware contribute to the memory model. C++11 has a rigorous definition of the memory model, which includes memory location and memory order. It helps to understand, at least, if not memorize what that is. That's the minimum guarantee. Whatever you're required by the standard is the minimum guarantee. You can get stronger guarantees on a particular system. Just don't count on it or you'll make your program non-portable. That's it for the memory model. If you want to become more familiar and improve your understanding on the memory model, here is something to try on your own. Write a program that demonstrates a permissible reordering, that actually shows that the program did two operations in one order, in one thread, and was observed in a different order on another thread. Several things to warn you about. First of all, you have to deal with the compiler first, because compiler can also do its own reordering. Declaring your variables as volatiles is a surefire way of preventing compiler reorders. Depending on what hardware you have, this may be harder or easier to observe. On x86, you only can see write-read being reordered. It makes one thing easy. In order to see something reordered, you will have to do reads. So read-read cannot be reordered, at least. So if something gets reordered, you can be sure that it wasn't the reads. But it's not that easy to see write-read reordered. And more importantly, maybe reordered doesn't mean gets reordered every time. It means the hardware can reorder operations when it somehow improves efficiency. Doesn't have to. You could run a million times and not see it happening. Another important thing to point out, the code that you will write is, from the point of view of the standard, is undefined behavior. Well, its implementation is platform specific. We're specifically targeting a particular platform, knowing what's reordered on this platform. So once you finish writing it, we'll never do that kind of code again. But it may be interesting to see how a memory model guarantees actually manifest themselves in practice. Welcome to the next lesson of the High Performance Computing in C++ course. We covered some of the memory ordering issues before. Now it's time to dive head-on into the tool that you as a programmer need to use to control memory order and synchronization in your concurrent programs. This is again going to be pretty heavy in terms of terminology and definitions and concepts class, but I'll make it up to you toward the end of this lesson, I promise. Let's start with a very kind of roundabout introduction to memory barriers. And let's start with a specific example that at first seems to have nothing to do with memory barriers. We're going to talk about the problem of singleton initialization in a multi-threaded program. Singleton is an object that has to exist in exactly one copy. So one instance of this object exists in the entire program for all threads of this program. Well, let's see this example. We have a class widget that has a thread-safe function transmogrify. Well, we're just given a guarantee that it's thread-safe. What does it mean, thread-safe? It means that if two threads call transmogrify on the same widget at the same time, it works correctly. We have this function called operate widget. It's not a member function, it's a standalone function that does two things. It creates a static instance of the widget. This is what makes it a singleton. So in a C++, static variables, including the ones that are local in a function, so static local, are created the first time the execution goes through this line of code. And from that point forward, you should get that copy, that instance that was created on the first pass. And then we'll call transmogrify on that one and only singleton widget. And after that, it's all easy. Transmogrify is thread safe. So the question is the whole operate widget function as a whole thread safe? Obviously, transmogrify is, so our focus is going to be on the first line. The key point here is, by design, there should be only one widget. So what happens if multiple threads attempt to initialize the static at the same time? In C++11, the standard actually does say what happens, and the answer is you get one copy of the widget and all threads see that one copy. So everything works exactly like you want it to work. It's a singleton. In C++03, the standard doesn't say anything about threads, so the answer is possibly. Well, let's say either you're writing it on C++03 compiler or you're doing some more complex but still a singleton initialization. Let's dive deeper and understand what's going on inside, whether the compiler is doing it for you or you have to do it by hand, but how is the static initialization, the singleton initialization, implemented and what happens when multiple threads need to initialize the singleton. So this one line of code is basically what we'll be focusing on for the rest of this section. This line of code unravels to something like this. First of all, we have a pointer, and initially this pointer is null. Usually it would be what's called linker initialized, which means it's null when the program is loaded into memory. The first time execution goes through this line of code, we do the check. Is the pointer null? The first time, the answer will be yes, it is. And if it is, we're going to construct new widget and store the pointer to this new widget in the widget variable. The second time we go through the same code, this check will be, is the widget null? Well, no, it isn't now because we just stored a pointer. So nothing will happen and we're just going to use this pointer again and again, and that's how Singleton works. Let's look at that same thing happening in two threads. So two threads are running that code that you saw on the previous slide. And let's say thread 1 gets to the check first, then thread 2 gets to the check, and we have a data race. Because they both see null, so they both go and construct new widget, and they both go and assign their new widget to the pointer. Well, one of them wins this race. The prize isn't really worth winning. The first one lost its pointer to the second one. This memory, there is no pointer to it anymore, anywhere in the program. This result of this allocation here will be leaked. Now, that doesn't seem so bad, but consider now the fact that in addition to actually leaking this, the first thread could have actually done some operations. It could have had enough time to call transmogrify on this first widget before the second thread does the second and final assignment to the widget. Not only you have leaked one widget, but your calls on the singleton may not be on the singleton, because there is a window here between the first assignment and the second assignment, and any call to transmogrify that is done within this window was done on the first widget, and everything else in the program was done on the second widget. You have violated the design constraint that this should be a singleton. The fundamental problem here is that this comparison, which is a read, we read the variable, load into register, and compare it, and this assignment, which is a write, they're not done atomically. We do the read, then there is some time for the variable to change, and only then we do the write. Concurrent, non-atomic access to shared data is what race condition is pretty much defined as. So we have a race condition. Which also means that static initialization without any kind of protection is not thread safe. I did say that C++11 static initialization is thread safe. All it means that C++11 static initialization does not boil down to the code we just saw. What could it be done? Here is a simple example. This will make it thread safe. We have a mutex, we take a lock, we do the check and the assignment, and we unlock. Now, this is guaranteed to be thread safe. Only one thread can be within the section between the lock and the unlock. So only one thread will do both the comparison and the assignment at a time. The next thread will not go in until unlock is called. So the next thread will see the result of the assignment and will not do the new widget. There is no tricks here. This works. This is guaranteed to be thread safe. There is a downside. And the downside is every time you go through this code, you're going to take a lock, do a comparison with null, and every time except the first time, you're just going to ignore this and do the unlock. Now, to do the comparison with null, you don't actually need a lock. If all you wanted is do a comparison with null and it's going to fail, you don't need a lock for that. Other than your first initialization and possibly any other initialization that happens at exactly the same time, and that's not many, all other times in your program when you run through this section of code, you're taking this lock for nothing. You are still prevented from doing this line concurrently. So you're still serializing your threads, but now there is no need to do it. So this is rather inefficient for what you need to do. Let's take advantage of the fact that if you read from the widget and you don't get null, then there is nothing to do and you didn't need the lock. We can take advantage of it explicitly. We'll say, okay, let's read from the widget. And if we didn't get null, we're done. If we did get null, there could have been a race condition. So now we're going to take a lock, read again, and this time we'll know the true value of the widget without the race condition. And if it's still null, we're going to assign a new widget. And if it's not null, then, well, we just wasted a log, but this is going to happen only at the very beginning of the initialization when the first time it's initialized. Once or twice we'll get an extra lock, maybe, and after that we'll be fine. So the lock is acquired only once. This is efficient. This is thread safe. Well, except for one slight problem, it's not. Previously, we looked at this one line, the static assignment. Now we have to dive even deeper and take apart what's called new expression. It's just these two words, new widget and the assignment. So this is new expression, this is assignment of the result of the new expression. What does it do? Well, it does, in general, two things. It allocates memory for the widget, and it calls a constructor of the widget. And the assignment then stores the pointer in the variable, the widget. So it probably does this. It allocates the memory, and just for writing this, let's say that the allocation of the memory is stored in some temporary variable, probably stored in a register. Then it calls the constructor. This is in C++ called placement new. It doesn't actually allocate any memory. It's not like regular new. All it does is invokes the constructor of widget on this memory location. If you could write temp arrow widget paren, that would be it. You can't call a constructor as a member function, but that's how the syntax looks like for calling constructor on a given memory location. So allocate memory, call the constructor, and then assign this temp pointer, which now holds constructed widget, assign it to the widget. We have to be valid C++, we have to do a cast. If another thread comes in the meantime, and it happens to come in right here before this assignment, it looks at the widget pointer. It will see null, because we haven't assigned yet, which means it will try to do a lock. The first thread that is actually initializing Singleton already holds the lock. So the second thread will try to take a lock, it will wait, and everything will be fine. By the time it wakes up from the wait, the widget is already assigned, so it will read the widget again. Remember, we read before the lock first time and after the lock the second time. After the lock, we'll read it again. This time it will not be null, and nothing will happen. Any thread that comes in here after the assignment and reads the widget, sees non-null, sees whatever we got here for the memory, it will just use the widget, everything is fine. This seems to work. So what's the problem? The problem is that the implementation of this new expression may not look like we have just written. Here is another valid implementation. Allocate the memory, store the address of the memory into the widget pointer. Now we're not storing a pointer to the widget object. There is no widget object yet. We haven't constructed it. We're just storing address to the memory. And then construct the object in this memory. Why is this valid? Well, it's all happening inside this new widget. By the time you come out, you will see the widget pointing to a new widget. What's happening inside? Well, the compiler gives you no guarantees on that. The language standard gives you no guarantees on that. Now we have a window of vulnerability. Another thread that happens to read the widget pointer right here between the assignment and the placement new will see a non-null pointer, but that pointer doesn't point to an object. It points to uninitialized memory. So another thread will come in and call a member function uninitialized memory. Anything can happen. The problem here is that the compiler can basically reorder the components or the parts of the new expression any way it wants, as long as the result is the same. Scott Meyer says, the ingenuity of a C++ programmer knows no bounds. We can try to force our way with the compiler. The first step would be to actually take apart the new expression and do it ourselves. This is what we wanted to do, so let's do it. First, we'll call malloc. Then we will construct an object. What we don't want is the assignment to happen second. Okay, the assignment is not happening second. We will call the constructor ourselves if we have to. And then we will do the assignment. There's just one problem. Temp here is an unnecessary temporary variable. Eliminating unnecessary temporary variables is basically what the optimizers live for. That's their favorite thing in the world. After the optimizer has a go at this code, you end up with this. Let's eliminate the unnecessary temporary variable temp altogether, says the optimizer, and store the result of the malloc directly in the widget pointer. And then let's call placement new on the widget pointer. This is a valid optimization, except from the order that we wanted, we happen to go right to the order that we didn't want. The assignment is first. That creates a window of vulnerability until the construction is done. Any other thread that reads this memory right at the semicolon here at this point in time will see pointer to uninitialized memory. So it wasn't as easy as we thought. Well, still, the ingenuity of the C++ programmer knows no bound. We're ready for round 2. We have to do it by hand ourselves with extreme prejudice. Let's declare the variable volatile. What does volatile do in C++? C++ standard tells us what volatile do in C++. Reads and writes of volatile variables cannot be reordered by the compiler. So now this is a write into the temporary. First of all, it cannot be eliminated to begin with. So this write has to happen. This is a read. We have to read the value from temp to get the memory location where to call the constructor. So this is a write. It has to happen. It cannot be eliminated. This is a read. It has to happen after the write. This is another read. We're reading temp and storing it in the widget. This read has to happen, and it has to happen after this read. The widget is not volatile, but we're storing the result of this read, and this read has to happen. Well, maybe this wasn't so easy, but we're finally won. Take a short break to enjoy this victory, because it will not be long-lived. Well, let's continue right away with our investigation of singleton initialization. By the way, this way of initializing a singleton is so common that A, it's worth talking about, but B, it has a name. It's called double check locking pattern. Why double check? Because we check the singleton variable twice. First outside the lock and second inside the lock. So we're checking the widget pointer here. The widget pointer, we're checking it twice. Abbreviation DCLP. So here is our code that we finally forced the compiler to respect. First, we allocate the memory. We store it in some temporary location. Then we construct the object that's writing into memory. Here is this memory of the object, widget. The constructor will initialize this memory and construct a valid object in this memory location. And this will happen first, because volatile. And then we will finally do assignment of the widget pointer from the temp. And again, temp is volatile, so reading from temp has to happen last, which means the assignment has to happen after the reading. So this will happen second. Still enjoying the victory? Okay, let's look at this one more level deeper. This is what actually happens in hardware. The previous view was from the compiler point of view. We have the processor and the memory. The hardware has this thing called cache, sits between the memory and the CPU, stores recently accessed parts of memory. We've seen this before. The CPU has no choice. It will write the widget object first and the pointer to the widget second. Volatile writes cannot be reordered, and volatile reads and writes in our case. But that cache is specific to this CPU. Nobody actually sees it other than the CPU. What other threads running on other processors see is this memory. And how does the memory trickle down from cache into main memory? Well, the answer is in whatever order the hardware wants. For example, in this one. First, the hardware decides, let's write these bytes into memory. Now this pointer is already pointing to this location of the widget, but this memory hasn't been initialized yet. It's still sitting in the cache. Later, the hardware goes and writes this memory. A lot of memory to write, big object, takes time. Well, that may not be the reason why, but you don't need the reason. It's hardware algorithms for flushing cache are complex and rather unpredictable. We won the battle with the compiler just to lose it to the hardware. Other threads running on other CPUs will still observe a non-null pointer pointing to uninitialized memory, at least for a certain window of vulnerability. At this point, you should be thoroughly confused, because basically I have just explained to you why locks cannot possibly work. Why did I just explain to you how locks cannot possibly work? Let's go back to the lock implementation. Forget the efficiency. Let's figure out why it's correct at all. Here is our line that we're trying to protect, and here is the lock. Inside the lock, there may be a lot of stuff, but fundamentally what the lock boils down to is there is a flag. It's 0 if it's unlocked, it's 1 if it's locked. Going to basically keep reading it. If you read it, if it's 1, it means the lock is locked. Well, keep reading. If you got 0, yeah, you have to write 1 so everybody else knows that the lock is taken, but this part is what's interesting right now. I have just explained to you why there is no order between cache and memory. So what happens when somebody got the lock and wrote 1 into the lock, but that's in cache, hasn't trickled down to the main memory yet. So another thread comes in, reads the value of flag from the main memory and still gets 0 and proceeds assuming that the lock is not locked and tramples all over this widget that was already created. So basically, this code implies that flag inside the lock is written first and the widget is written second. If the cache to memory transaction can reorder the writes, why can't flag be written second and the widget first? Well, the answer is this never happens with locks, and we have to understand why to go any further. This confusion is useful. It actually deepens your understanding. So let's take a break while you can focus on this confusion and hold on to it. In the next lesson, I'll explain why it doesn't happen and how you can actually write correct programs. Welcome back to the class on memory barriers. I wouldn't want to leave you dispirited and confused for long, so let's figure out why locks actually work. The reason the locks work is this concept called memory barriers that is in the title of this class, and we're just now getting to it. I can't just jump in and tell you why locks work. I have to define the memory barriers because they're the reason. But you have already seen that synchronization of data accesses, which is what locks do, locks prevent two threads from accessing the same data at the same time, would not be possible at all if we couldn't control the order of memory accesses, control it in a global manner across all the CPUs. This control is provided by this feature called memory barriers. It's fundamentally a hardware feature. It translates into language. It's a feature implemented by the hardware. It's invoked through specific hardware instructions or sometimes through modifiers on other instructions. You can't get to it in a portable way unless the language provides some kind of universal portable API. How do you get to it in your code? You have to write these processor-specific instructions. Very often, they are kind of attributes on reads and writes operation. Well, we have just seen it on the example with lock. That operation that reads the flag and the operation that sets the flag of the lock changes it from 0 to 1, that's the point where we would like to have a memory barrier. That's the synchronization point, because that determines the boundary of what's affected by the lock. Everything within the lock-unlock section must be synchronized by the lock. Everything outside we don't care about. For the lack of threads in the first place, C++03 didn't say anything about memory barriers either. C++11, as a part of its memory model, provides some standard memory barriers. We discussed memory model and specifically memory order before. Memory barriers, as you will see in a moment, almost exactly mirror this memory order. They're really what ensures the memory order. Memory barriers in C++11 live in this header called atomic, and they're related to the atomic variables. So I told you just now that memory barriers are usually modifiers on existing operations such as read and write. So in C++, they're specifically modifiers on operations on atomic type. So you can have atomic, it's a template of a struct, std atomic of an integer type. Well, they have some predefined versions of it, but never mind that. What are the member functions? For example, there is load. It's a read. Let's look at the signature of the load. It's a member function of atomic. It returns the underlying type. So you have atomic int, you get back an int. But this is the interesting part. You have this optional argument, well, it's defaulted argument, memory order. So you can write load of a value, and the value is actually the memory order. It has nothing to do with the value of the variable. It determines the memory order. It's defaulted to sequential consistent. Now we have to go look at the memory orders. So these are the same memory orders as we saw in the memory model. These really literally are the same memory orders. They're defined in the atomic header. In addition to being part of the memory model, they are the parameters to atomic operations such as load. And by default, you get the highest memory order sequential consistency. You can ask for a lesser order, and then you will get fewer guarantees on this load. Well, that was load. Let's look at the store, for example. I won't make you go through all of them. Store has the same thing. Now, store doesn't return anything. It takes the value that you want to be stored into the object, and it has a second optional argument, which is again the memory order. Same thing by default, it's sequential consistency. You can ask for a lesser order if you want. And the same is true for other operations on atomic variables. We'll see some of them later. Let's not go through all of them right now. What we just saw actually was the memory barrier. The memory barrier is defined in C++ by this memory order attribute on loads and stores. And what it means is that this particular load and store will not just be a load, but it will be accompanied by a memory barrier. Some kind of memory barrier is necessary, unavoidable. You have to use it in order to write any correct concurrent program. Whether you write it explicitly or not, that's a different story. Here are the memory barriers that you need to know about. You have seen several in the C++11 memory order page. Well, I'll simplify it for you a bit. So we'll focus on these two. There is acquire memory barrier. What acquire memory barrier guarantees is that all memory operations, that's all operations, both read and write, that are in the program order scheduled after the barrier. In the program order just means in the code that you have written. So you have load with acquire, and then you have some x equal 1, y equal 2, and so on. That's after. All of these operations become visible after the barrier. Note that it refers to all operations, not just operations on that same variable that you were loading, but on the entire memory. It's a global transaction. Let me illustrate. We have our program order. We're going to read some variable, write some variable. Here is our read or load with acquire barrier, and then there is more writes and reads. What's the actual order? Well, this is a possible actual order. Before the acquire read, there are no ordering guarantees, so the write could actually be moved before read. Furthermore, there are no guarantees on the operations that happen before acquire read that they can't be moved past. They can be moved down. The guarantee you have is that the operations after acquire read cannot be moved up. Again, there is no protection against reordering of those operations, as long as they both stay after the barrier. So what happens after the barrier must happen after the barrier in any order. And what happens before the barrier can happen anywhere. That's how acquire barrier works. Well, if there is acquire, there must be release. The release barrier is kind of inverse guarantee that all memory operations scheduled before the barrier in the program order become visible before the barrier. Again, note all operations, which means reads, writes, and on all the memory. So let's illustrate. I have some reads and writes before a release barrier, and let's say this release barrier is on a write operation, and I have some reads and writes after the barrier, and this is a valid, not the only valid, but a valid actual order. Anything that was before is still before the barrier, could be reordered, but has to happen before the barrier. Anything that was done after the barrier can be reordered anywhere, possibly before the barrier. How does it help us with locks? Here is our program order, and let's say that we read the lock with an acquire barrier. So reading the lock actually not only reads the lock, but it also sets the lock to locked. It's the read, modify, write operation. And it's done with an acquire barrier. So that's where the name of the barrier is coming from. We are acquiring the lock. Then we do some reads and writes, and then we release the lock. Now you see why it's called release barrier. You're releasing the lock. Given these two barriers and their guarantees are anything that happens after the acquire barrier has to stay after the acquire barrier, anything that happens before release barrier has to stay before release barrier. We have these two barriers, and they're unidirectional. Acquire barrier prevents operations from going up. Release barrier prevents operations from going down. So this is a valid actual order. You will notice that reads and writes that were within the locked section. By the way, this is called the critical section, between the acquire and release of the lock. Reads and writes that were within the critical section are still within the critical section. They cannot move up, they cannot move down. Reads and writes that were outside of the critical section can move into the critical section. So this is how locks work. Anything that was done within the critical section between lock and unlock has to become visible within the critical section between lock and unlock. That's why you cannot have reordering that pulls operations on shared data from outside of the critical section. Memory barriers are essential component of the lock. So far, we have focused on the lock as we looked at this flag. If flag is 0, lock is not taken, you can take the lock and go compute. If flag is 1, you have to wait. Well, that's only half of it. The other half is this memory barrier. Acquire barrier is used when the lock is acquired, and release barrier is used when, you guessed it, the lock is released. These two barriers together define the critical section between lock and unlock. Nothing can leave the critical section. Within the critical section, there is no additional guarantees. Well, not due to the lock itself, if you have dependency guarantees, of course. Operations can be reordered within the critical section, but what guarantee you have is if all your access to the shared data is within the critical section, then it cannot be moved out, which means another thread cannot do any operations on the shared data while the lock is held by some other thread. Why? Because operations on shared data are all within the critical section and they cannot be moved out. Even though you haven't seen any memory barriers yet in any of the programs we've looked so far, and maybe you wrote a lot of concurrent multi-threaded programs and haven't seen a single memory barrier. They're there. They were absolutely critical for your success as a programmer of multi-threaded programs, and most of the time they're invisible to you. They're implicitly provided by the locks. Next, we're going to cover the other, less of the time, cases when they have to become visible. Let's continue with the memory barriers and see how they're used. Well, obviously they're used for synchronization of memory accesses. Most of the time, they're used without you ever having to do anything about it because you're using locks, and the locks have been written correctly with the memory barriers most of the time. It's very important to observe a certain protocol when dealing with memory barriers. There are tricky subjects, have to be addressed with reverence. Specifically, memory barriers provide their guarantees only if all processors or all threads participate in this handshake if they all use appropriate barriers. This is conceptually the same as it is for locks. If you have one thread that locks access to the shared data and another thread that doesn't lock access to shared data, that lock is useless. When people think about memory barriers, somehow that very same notion is harder to imagine. Maybe part of it is the language, and the way the barriers are described is the memory accesses that happen after the barrier, or acquire barrier in this case, become visible after the barrier. That has this hint that it's a global thing, that it somehow forces this property onto everybody else. Well, it doesn't. The other thread has to play by the same rules. Specifically, it has to also use the barriers, just like the other thread has to also use the locks. Let me illustrate. We have one thread that is doing a write, then the release write, then another write. The release barrier in this case guarantees that the first write, write 1, becomes visible before the release barrier. Here is how thread 2 will take advantage of this guarantee. It has to do acquire read, or another operation with an acquire barrier. If it does the acquire read, and then it will read the first variable, it will see, it's guaranteed to see the results of the first write. So write 1, whatever that wrote into memory, that's what you will get when you do read of the first variable. You're doing write 2 to a different memory location somewhere, that's after the barrier, there are no guarantees for that. You may or may not see the results of write 2. But the first write to its memory location will be seen if you do a read after an acquire read. What happens if you don't do an acquire read? Anything can happen. So for example, you do a read after an acquire read, and you can see the state of the memory as it was before the first write. Even if you're doing this read after the first write, the state of the memory you will see will be as if it was before the first write. That's why we talk about memory visibility. You may have done the write, but it hasn't become visible because your other thread has not respected the memory barrier protocol. Now, fortunately, the memory barrier protocol is actually very easy to remember. If you're doing a release barrier in one thread, there has to be an acquire barrier somewhere else. Otherwise, your release barrier is useless. And the same is true if your thread has an acquire barrier, you have to look for another thread that does the release barrier, and that's between these two threads is what synchronization provides its guarantees. If you have a thread that does not do any barriers and still accesses the shared variables, that's a mistake. So for every release barrier, there must be an acquire barrier somewhere else. And for every acquire barrier, there must be a release barrier. When they're provided implicitly by locks, that happens automatically because every time you take a lock, it's an acquire. Every time you release a lock, it's a release. If you're doing your own memory barriers, you have to respect that memory barrier protocol. Now, here is a very important point. The memory barriers, they're implied not by the code that issues them, but by their actual use. What do I mean by that? This is an atomic exchange operation on x86. it boils down to this one instruction. This is the actual atomic exchange. The rest is just inline assembly on GCC. This is atomic exchange. Let me ask you a question. Does this atomic exchange provide any memory barriers? Well, you could go into x86 documentation and find out, but that's the wrong way to look at it. The question really here is, do you need this atomic exchange to provide any memory barriers? And you can only figure it out by looking at how you use it. Here is our lock. In this case, it's some sort of spin lock. Inside the spin lock, we have this flag variable, let's go lock variable. And when we acquire the lock, we do an atomic exchange. We store 1 into the lock while atomically getting the old value back. And when we release the lock, we just need to store 0. We can just do a store, or we can do another atomic exchange and ignore the return value. Atomic exchange by itself guarantees atomicity. It says that read of the old value and write of the new value will happen non-interruptible way. Nobody can see the state of this variable after you read it, but before you wrote into it. That's the only guarantee that is provided by the atomicity. That guarantee only applies to this data that you operate on, this lock, whereas memory barrier guarantee applies to the entire memory. What about the memory barriers here? Well, the memory barriers are implied by how you use this. They don't really have to be associated with atomic operations. Usually they are in practice. What can you deduce about the memory barriers? What can you deduce is this acquires the lock, and in order for the lock to function correctly to begin the critical section, you need an acquire barrier. This releases the lock, and in order to bound the critical section from below, you need a release barrier. This is necessary in order for the spin lock to correctly protect this increment. So again, the barriers, acquire and release, are implied by how I use this atomic exchange. The two atomic exchanges look very similar, but they need totally different barriers. Whether the instruction that I had before actually provides these barriers, that's a different story. If it doesn't provide these barriers, then I had the wrong code. I used the wrong atomic exchange. On x86, it happens to provide both barriers at once, but you cannot deduce anything from this fact about the correctness of what's necessary for the correctness of the program. Once you understand what barrier requirements are for the correctness, you can understand if this hardware instruction provides the necessary barriers. But just because it provides them doesn't mean that they have to be there. So to understand the actual protocol for the memory barriers used in this program, you have to look at how they're used. So for example, this is an acquire barrier. The instruction for atomic exchange on x86 also gives you a release barrier. Don't go look for another thread for a matching acquire barrier to this release. It's not there. It doesn't need to be there because this release barrier is accidental. We don't count on it. It's okay for us to not have a matching acquire barrier because we don't mind violating the release barrier that may accidentally happen over here. Now, this release barrier is a different story. There has to be a matching acquire barrier. These two are pair. So this is very important when you write your own memory barriers. You have to respect the memory barrier protocol. Every time you are acquiring something, it must be released to you by the corresponding barrier in another thread. When we know all we need to know about memory barriers, it's time to go look at some code finally and make use of them. And let's take a short break before we do that. Now let's go look at our locks that we have seen before in the context of the memory barriers. We did see a lock of our own a couple classes earlier, and this is one of the locks we have experimented with, and we did it with an atomic integer, and the lock used atomic exchange. We atomically exchange the value of the flag for 1. If we get back 0, it means that the lock wasn't locked and we just successfully locked it in a single atomic non-interruptible transaction. And if we didn't get back 0, we got back 1, it means that the lock was already locked. Well, we exchanged it for another 1, which means we didn't really change it at all, so we just keep spinning. And to unlock it, we just wrote 0 into it. Well, we did this before we knew about memory barriers. So now we have a big uncertainty. Was this lock actually doing anything? Remember that atomically operating on the flag is only half of what lock needs to do. In order for the lock to actually protect anything other than the flag itself, it has to issue the correct memory barriers in order to maintain the critical section. So locking has to have somewhere in it an acquire memory barrier so that all the accesses to shared data cannot escape from the critical section. Let's go look at our critical section. This is the critical section, the increment, and we have a lock here. Unlock is in the destructor of this object. It happens right here. Lock has to have a acquire barrier, otherwise this ++x can leave the critical section, be moved up, and not be protected. Unlock has to have a release barrier for the same reason, otherwise our increment can move down out of the critical section. Fortunately, this actually was correct code. And why it was correct code? Because by default, exchange on atomic in C++ uses a bidirectional memory barrier, the strongest memory barrier that they have, which is actually stronger than acquire-release combination, but that's unimportant for our purposes right now. Let's say it uses acquire-release barrier. Same for this assignment. Now, this assignment, you don't even know explicitly directly. You have to read the documentation, because exchange takes, as we saw, the second argument, just like load and store. Exchange takes the second argument, which defaults to sequential consistency, the strongest memory order. This assignment, of course, doesn't take the second argument, but the standard says that this has implicitly sequential consistency memory order, and you can't change it. So this was correct. It was unnecessarily restrictive. We were taking acquire release, or actually sequential consistency memory barriers in both lock and unlock, but at least acquire barrier was here, well, plus some other barrier, but acquire was here, and release was here, so this code was correct. If we did it explicitly with just the memory barriers that we need, then this is how it would look. So here is our exchange, and now we have to be explicit about the memory order, and we're saying memory order is acquire. We can't do assignment of 0 as an assignment and have a memory order, but we can do store. So store is the same as an assignment, but there is a place here for the memory order argument, the second argument, and this one is the release. So now we're explicitly saying, okay, lock, it has acquire barrier, unlock has release barrier. This also has to be correct, but this is less restrictive barriers. Well, let's see if it made any difference in performance. It won't make any difference in correctness. This is our old lock. It compiles, it runs, the timings are maybe slightly different from what we saw when we ran it last time. There are some fluctuations run to run, but this is the ballpark. And this is the same lock, but with the minimum necessary barriers. See the big difference here. Even at one thread, there is actually a difference, which means that barrier modifier, or the barrier instruction that was necessary for bidirectional barrier, takes extra time even when you have no other threads. Well, that's x86 specific thing, although it would be even worse on like PowerPC. On two threads, having two bidirectional barriers was much more expensive than having just acquire barrier on lock and just release barrier in unlock. And then it kind of stays lower with minimal barriers than with excessive barriers. We also had last time another spin lock where instead of having a separate flag, we were spinning on the pointer to the variable that we're incrementing. Let me remind you. So what we have here is a pointer to the variable x that we increment. Let's go back up and see it. So we have an atomic pointer because we're actually going to be using it also as a spin flag. So it's an atomic pointer. Before we start running, we initialize what it points to 0. Then we have this pointer lock, which is like a spin lock, but it uses the pointer as a flag. We'll see the class in a moment. When we lock it, we both get the value of the pointer, store it in a local variable, and make this pointer unavailable to all other threads. How do we do that? Well, we exchange atomically the pointer with null, which makes, of course, the pointer not point to the variable that we're going to increment anymore. By the way, where do we get the variable that we're going to increment? Well, here is operator new. So we allocate memory for unsigned long. So we're atomically exchanging the pointer with null, simultaneously grabbing the old value, and we return this old value here. It returns a pointer to unsigned long, which is the copy of what we grabbed atomically from the pointer. To unlock, we just store the old pointer back. After we successfully locked the lock, this atomic shared pointer is now null, and the thread that called the lock and got back the return value is now in possession of the only copy of the real pointer. So it can proceed to dereference the pointer and increment without any fear of race conditions. Again, the exchanges here have full barrier, the sequential consistency bidirectional barrier. We can trivially modify this code to use the minimum necessary barriers. See, now they'll be different. Acquire in lock. Remember, we saw before for example, CPP reference webpage talks about release barrier on a read modify write operation. Well, this is a read modify write operation. I told you doesn't have to be release barrier. You can put acquire barrier on a operation that is essentially a write, and it's fine. And here is store with the release. Other than that, there are no changes in this code. We can expect similar performance improvements. The pointer lock, as we call it, is a little faster than the spin lock because it has one shared variable instead of two. Spin lock has a spin lock itself, and the data we increment is still shared. It's just synchronized. Now pointer lock has only one, the pointer. Using the minimum necessary barriers makes it significantly faster. There is one more optimization we can do here. So let me show you what it is and then explain. I told you that exchange is a read modify write. It's also atomic, which means it combines read and write in a single operation, and in fact, it always writes. See, this is an unconditional write. We're always writing one. The only reason it sometimes behaves as if nothing happened is because sometimes we write one where there already was a one. But the hardware doesn't know that, which means from hardware's point of view, it's always a write. When you do a write, you write it into first the local cache of the CPU, and then it has to propagate all the way to the main memory. Remember, this is atomic operation, which means all other CPUs are guaranteed to see the final result of this operation. So once you start writing, no other CPU can see this memory until the write finishes, until the value from the cache trickle down all the way to the main memory. This takes a long time. We've seen this before. So every time I do this atomic exchange, and another CPU is trying to read the value from flag, the other CPU has to wait for the results of the atomic exchange to trickle down through the main memory. This is critical when flag changes from 0 to 1. Well, when flag changes from 1 to 1, if the other CPU saw the old one or the new one, 1 is a 1, it makes no difference. We can make this optimization to try to read only from the atomic variable first. So we're going to read, and of course, if we read 1, it means that it's locked and we have to read again. Now, if we read 0, we can't just go and write 1 into it because that would be non-atomic. Somebody can come in between the read and the write and take the lock. So to avoid this non-atomic window of vulnerability, if we got 0 from the read, we have to read again. And this time we read atomically, and there is a chance that the second time we read, it's going to be 1, which means somebody stole a lock from us right between load and exchange. Well, that's too bad. We have to read again. Now, this looks very similar to the double-check locking pattern, but this one is correct because we're using the proper memory barriers that prevent the hardware from doing undesired reordering. Also because we're never actually going to go and take the lock just with the load. If the load succeeds meaning give us back 0, we're always going to do acquire. And acquire is going to do acquire memory barrier. I mean, we're always going to do exchange with acquire memory barrier. We don't need any memory barriers at all on the load. It doesn't matter because sometime before the lock call is over, we're going to take acquire memory barrier. It doesn't have to be here. The load can be relaxed. Nothing depends on it. Okay, so this is an optimization. We're going to be basically trying the load. As long as we get 1, we're going to keep trying the load. If we get back 0, we're going to jump in with an atomic exchange. If it's still 0, we atomically write 1. This basically locks down all the caches until that 1 propagates to the main memory. This is necessary this time. This is good. This is what we want to happen. But if it was 1 to begin with, then we're not going to do this exchange. For the store, there is nothing to do. Storing 0 will have this global effect, and all the other CPUs will have to wait until 0 propagates to the main memory, and that's how it has to be, because unlock is unconditional. We're just changing it to 0. Everybody has to see that it now became 0. Now, you can have the same thing for the pointer lock, of course. Again, you can load the pointer instead of the spin lock flag with the relaxed memory order. If you got back null, it just means, well, we don't have the pointer. Keep trying. If you got back non-null, okay, we have to do the atomic exchange with the acquire memory order, and there is a chance that we missed it. Then we have to spin again. We have here on screen the non-optimized version of the pointer lock, so let's try the optimized version of the pointer lock. Seems more or less the same for small number of threads. It looks like it's getting a bit better for large number of threads, but it's not very definitive on this machine because it's not a very large machine. It only has 4 CPUs. To help us see the effects of the barriers and the effects of the read-read-write optimization, this is what it's called, because instead of just doing read, modify, write, you're doing kind of pre-read, and then you're proceeding with the read-write. So it's read-read-write. We're going to look again at the performance chart that I have obtained from a large machine with 120 cores. So this chart we have seen before. This is the old chart. There's nothing new here. We're comparing mutexes with the spin locks, and as a sort of golden reference, we have the atomic increment, which is a single hardware instruction, does not need a lock, just does atomic increment on an integer. Let's go and add new values. There is a lot of new values to add. We have the barriers, we have the pointer lock with barriers, and we have the optimized version of them. So let's look at this in groups. First of all of our spin locks. This is just spin locks, no pointer locks. At the top, the squares are the old spin lock. Then the triangles are the atomic. And the 2 new data sets are the spin lock with the correct barriers. That's the crosses. And the optimized read-read-write spin lock, also with the correct barriers. That's the circles. Now, as you can see, the barriers make a lot of difference. We have seen this before, using correct barriers. Using the read-read-write optimization now on this large machine also makes quite a bit of difference. And the interesting thing is the optimized spin lock is actually running pretty close to the atomic. This is the same, but for the pointer locks. The top line, the crosses, is the old pointer lock with our bidirectional barriers that happened to be there by accident. We just got lucky that it was correct at all. Then the circles and the squares are the 2 pointer locks with the correct barriers. The squares is the optimized one. And again, the atomic it's in the middle of it. It's not showing that great of an advantage. So now let's just pick the best of them all. Well, atomic is a kind of golden reference, except it doesn't look so golden anymore. And here are our spin locks and pointer locks with the correct barriers and their optimized version. So I cut off the plot at the top at 128 threads. Just the barriers alone, don't cut it. Both the spin lock and pointer lock goes way up there when you have that many threads. But the interesting thing is that with the correct use of barriers and the read-read-write optimization, the spin lock is actually holding their own against atomic really well. It's often faster than atomic by probably statistically significant margin. The standard deviation on these measurements was something about 2 nanoseconds plus minus. So it actually looks like it's real data. Now, this is hardware dependent. On other platforms, I've seen the difference between atomic and this read-read-write spin lock to be much closer, but the important part is it's not losing. So now we finally have a very good implementation of a spin lock. This one you can actually use. Last time I told you, please don't use the spin lock I've shown you before. Well, this is why. You can use this one. What have we learned from this experiment with the spin lock? From this moment of panic, which we had when we realized when we did not use the proper memory barriers with our spin lock last time, and we only got lucky by accident, we should learn that memory barriers are absolutely essential for correctness of any concurrent program. Fortunately, they're often implicitly provided by the locks. If you have to use them, you have to use them on all threads accessing shared data, and which barriers you mean to use depends on the role in the code. If you're acquiring the lock, it's an acquire barrier. Our spin lock happened to have a bidirectional barrier in that place. That wasn't what we wanted, and we were paying a price for it. Stronger memory barriers in general are more expensive. Is not always the case on all hardware, but in general that's true. So it does pay off to use just the minimum necessary barriers that are implied by the use in the code. This is all about the theory of the memory barriers as well as their use for synchronization with locks. As you have seen, it makes quite a bit of difference that you use correct memory barriers. For the rest of the class, we're going to be using just these three memory barriers. Acquire, that barrier prevents memory accesses from going up above the barrier. Release prevents all memory accesses from going down past the barrier. Acquire and release is a bidirectional barrier, combines both of these. There are others. On some hardware, they actually make a difference. Meaning on some hardware, it boils down to acquire release or acquire release, but on other hardware, it actually gives you subtle distinctions. It's complex enough without adding more types of barriers, so for the rest of the class, we're going to be using these three. Good enough for most purposes. Now, if you need more barriers, well, there are stronger barriers. They are usually very expensive, but if you need total consistency, you can get it. There are weaker barriers. On some platforms that actually have it, they may be more efficient than acquire and release barriers. On other platforms, it won't make any difference. On x86, you can use acquire release, and that's basically all you get. If you want to become an expert on memory barriers and just learn it by heart, you may want to do some practice. So here is what I suggest. So far, we have measured the effects of the memory barrier mostly on the exchange operation, also a bit on the assignment. And we have only seen the effects of using the correct memory barriers versus the strongest memory barrier that we got kind of by accident. If you want to learn more, do a systematic study of different kinds of memory barriers on a particular operation, load, store, exchange, from the point of view of its performance. So load, relaxed, load, acquire, load, release, load, acquire, release. How long does each one take? A helpful hint to you, your results will greatly depend on which hardware you're using, because some hardware doesn't have all of these barriers separately. So when you ask, for example, for a lesser barrier, like you may ask for consume, you're going to get acquire. In order for you to find out whether your results make sense, it may be helpful to you to look at the machine code. If you have two different memory barriers in your C++, but the machine code is exactly the same, it just means that on your hardware, you don't have these barriers differently. The stronger version is given for both of them. On Linux, you can do objdump to get the disassembled machine code in x86 mnemonics. It's not object code, not in binary, but easier to read. Debuggers will help you disassemble it on other platforms. If you do load with two different memory barriers and you get exact same timings, look at the machine code, see if the two different memory barriers actually are different memory barriers. This will give you a really good practice and use of all the different memory barriers and a feel for their cost. And you'll be ready for the next class where we actually get to use the memory barriers in our program in non-trivial ways.